The Ultimate Modern Data Quality Scenarios Interview Guide.
If your goal is to pass modern data quality engineer or analytics engineer interviews, interviewers are moving away from asking what is data quality and instead ask real production scenarios. They want to know how you handle silent null spikes, metric drift, and semantic layer conflicts. In this masterclass, we will cover 155 real-world data quality and pipeline scenarios that test your true production readiness.
The production mindset behind these scenarios. What interviewers are really evaluating.
Modern data quality interviews are no longer about memorizing validation rules or explaining theoretical concepts. Every production incident typically belongs to a specific data quality dimension, such as completeness, duplication, accuracy, semantic correctness, consistency, freshness, schema evolution, or data integrity. Throughout this masterclass, we will not simply solve individual incidents. We will learn how to recognize these underlying failure domains and apply a repeatable production response methodology. By the end of this series, you will think like a production data engineer or data quality engineer rather than someone who has simply memorized interview answers.
Part 1 and Part 2. Core quality to staff level.
To make this massive data quality curriculum digestible, we have divided it into two parts. Part 1, the core pipeline and business reality. This part covers the first 80 scenarios, focusing on fundamental data quality dimensions like completeness, duplicate data, mathematical accuracy, semantic consistency, and schema evolution. Part 2, the modern data platform. This part covers the remaining 75 advanced production scenarios, focusing on staff and principal-level engineering challenges including lakehouse reliability, data observability, governance, security, privacy, AI and RAG pipelines, feature stores, data mesh, data contracts, enterprise reconciliation, and Gen AI-powered data quality systems. Let's look at how we will tackle Part 1.
Part 1. Mastering core quality realities.
Welcome to Part 1. In these first 80 scenarios, we focus on the foundational pillars of enterprise data quality. We will tackle the everyday realities of production data platforms, from isolating missing records and deduplicating streams, to catching silent business logic failures and drifting semantic definitions. Mastering these core dimensions is the absolute prerequisite for passing any technical data interview.
The 4-phase incident response framework.
To answer these scenarios like an elite data quality engineer, we will not just recite generic fixes. We will use a strict 4-phase production response framework. For every single incident, we will walk through detection, investigation, targeted resolution, and long-term prevention. This structure ensures every answer you give in an interview demonstrates real architectural maturity, cross-functional awareness, and strict quality governance.
The 8 categories of Part 1.
Here are the 8 fundamental data quality categories we will cover in this video. Category 1, data completeness and missing data. Category 2, duplicate data and idempotency. Category 3, data accuracy and business logic. Category 4, semantic quality and business rules. Category 5, consistency and end-to-end reconciliation. Category 6, data freshness and SLA. Category 7, schema evolution and data contracts. Category 8, validation and data integrity. Let's begin our journey with Category 1.
Category 1. Data completeness and missing data.
Interviewers evaluate how you handle the most fundamental question in data quality. Did every expected record successfully arrive and become available for downstream business consumption? In Category 1, we will explore 10 high-frequency production scenarios covering dropped regional dimensions, late arriving streams, silent extraction skips, and time zone truncation bugs. Strong candidates must demonstrate how to isolate the exact missing segment and establish strict completeness validations.
Category 1. Data completeness and missing data scenarios.
Here are the 10 production completeness scenarios we are going to solve in this category. Scenario 1. Daily sales pipeline loads only 72% of expected records. Scenario 2. One regional branch completely disappears from today's report. Scenario 3. Customer email addresses suddenly become null for 45% of records. Scenario 4. API intermittently skips pages during extraction. Scenario 5. Late arriving data causes dashboards to fluctuate throughout the morning. Scenario 6. CDC misses transactions during database failover. Scenario 7. Partition pruning accidentally excludes yesterday's data. Scenario 8. Source table is truncated before ingestion completes. Scenario 9. Orchestration pipeline succeeds even though one extraction task loads 0 rows. Scenario 10. One upstream microservice silently stops publishing events. Let's deep dive into Scenario 1.
Scenario 1. It is 8 a.m., and the finance team reports that today's sales dashboard looks unusually low. The overnight ETL pipeline completed successfully, but only 72% of the expected sales records are available in the warehouse, delaying executive reporting. How do you investigate, resolve, and prevent this data completeness incident?
Answer. When an ETL pipeline reports successful completion despite missing 28% of the expected records, I execute a structured 4-phase response plan like below. Phase 1. Detection and validation. 1. Validate the anomaly by comparing today's volume against a 30-day historical moving average for that specific day of the week. 2. Check automated observability alerts to see if the missing 28% was flagged by volume monitors before business users reported it. 3. Run a segmentation query on the gold layer to see if the drop is uniform or isolated to a specific region, product, or time window. Phase 2. Investigation root cause. 1. Perform a cross-layer reconciliation source to bronze to silver to pinpoint the exact stage where the record silently dropped. 2. Inspect Airflow orchestration logs and CDC stream offsets to ensure no tasks were marked successful despite empty payloads. 3. Audit the incremental extraction logic for time zone skew or incorrect high watermark boundaries that excluded late arriving events. The goal is to isolate the exact stage where the data loss occurred rather than assuming the ETL job is at fault. Phase 3. Targeted resolution. 1. Correct the underlying extraction bug, such as shifting the watermark window to capture the bypassed records. 2. Execute a targeted overwrite on the affected iceberg or delta partitions to ensure idempotency and avoid a massive full table backfill. 3. Run a final reconciliation check on total sales amounts and order counts to guarantee parity with the source before notifying finance. Avoid reprocessing the entire pipeline unless absolutely necessary, as it may increase downtime and duplicate data if idempotency is not handled correctly. Phase 4. Long-term prevention. 1. Implement a circuit breaker in the orchestration DAG that intentionally fails the pipeline if row counts drop below a 95% threshold. 2. Embed automated source to target reconciliation queries that run as a final quality gate before data is published to the gold layer. 3. Establish a data contract with the upstream software team to prevent unannounced API changes that cause silent extraction failures. Role perspective and boundaries. 1. Data engineer traces the data loss through the infrastructure, patches the extraction logic, and safely backfills the missing partitions. 2. Data quality engineer defines completeness rules, builds reconciliation tests, validates restored datasets, and verifies business metrics before downstream consumption. Pro tip: never confuse data volume with data quality. A pipeline can successfully load 100% of the expected rows while silently excluding an entire business region and duplicating another. Always validate business KPIs such as total revenue, order count, and regional distribution, not just row counts.
Scenario 2. The daily performance report has published, but the entire EMEA branch is completely missing from the dashboard. The overall pipeline succeeded, but this massive slice of data vanished. How do you investigate, resolve, and prevent this silent data loss?
Answer: when an entire business dimension disappears while the pipeline reports success, the issue is usually caused by a filtering error, failed regional extraction, transformation logic, or schema changes. To isolate and recover the missing data safely, I follow a structured production response like: Phase 1. Detection and validation. 1. Validate the dashboard filters and queries to ensure the branch was not accidentally excluded at the BI presentation layer. 2. Query the underlying gold layer tables directly, grouping by the region column, to confirm if the records are physically missing from the warehouse. 3. Verify in the upstream source system that transactions for the EMEA region were actually generated and committed successfully before investigating downstream pipeline stages. Phase 2. Investigation root cause. 1. Perform a reverse lineage trace from gold to silver to bronze, running partition-level counts for the specific region at each hop. 2. Inspect the extraction logs for the regional source system, or AP, Idempotency to verify whether the extraction failed, timed out, was skipped, or returned an incomplete dataset. 3. Verify whether the region identifier or reference mapping changed in the source system, causing downstream joins or filters to exclude the affected records. At this stage, you should know exactly where the regional data disappeared, either during extraction or during downstream transformations. Phase 3. Targeted resolution. 1. Fix the root cause, whether it is updating a mapping table, fixing an inner join, or correcting a filtering clause. 2. Trigger a targeted backfill only for the affected regional partition after confirming the fix, avoiding a full pipeline rerun that increases compute costs and recovery time. 3. Validate the backfilled partition against the source system totals before manually refreshing the affected executive dashboard. Ensure that recovering this missing dimension does not accidentally duplicate records for the other branches that loaded successfully. Phase 4. Long-term prevention. 1. Implement anomaly detection monitors that track row counts not just globally, but grouped by critical dimensions like region or product category. 2. Implement automated dimensional completeness validation that compares expected and actual record counts for every critical business dimension before publishing data downstream. 3. Add data freshness alerts on a per-region basis to catch regional extraction failures immediately before downstream pipelines execute. Role, perspective, and boundaries. 1. Data engineer. Investigates the regional extraction logic, fixes the filtering or mapping issue in the ETL code, and orchestrates the targeted backfill. 2. Data quality engineer. Defines dimensional completeness rules, builds automated reconciliation checks, and validates the restored regional data before reporting resumes. Pro tip: global row counts can hide serious business failures. A 5% drop in total volume might seem insignificant, but if that 5% represents your entire EMEA business, it becomes a critical production incident. Always monitor record volumes by key business dimensions such as region, product, customer segment, or sales channel, not just overall row counts.
Scenario 3. During daily monitoring, you notice that customer email addresses are suddenly null for 45% of incoming records in the gold layer. The ingestion pipeline executed without throwing errors, but downstream marketing campaigns and notification services are at risk. How do you investigate, resolve, and prevent this data quality issue?
Answer: when a critical attribute like customer email suddenly becomes null while the pipeline reports successful execution, the issue is commonly caused by upstream schema evolution, failed reference data joins, field mapping errors, or incomplete source payloads. To isolate the root cause, safely restore the missing values, and to prevent recurrence, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the gold and silver layer tables to measure the exact null rate for the customer email field across recent partitions and compare it with historical baseline values. 2. Validate whether the 45% null spike is uniform across all incoming traffic or isolated to a specific client application, sign-up source, or region. 3. Check automated data observability metrics and column-level null threshold alerts to verify when the anomaly first started. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a column-level attribute quality incident. Phase 2. Investigation root cause. 1. Perform a column-level lineage check from gold back to bronze and raw landing zones to locate where emails turned into nulls. 2. Inspect raw JSON payloads or source API responses in the bronze layer to verify whether field names, nesting structures, or payload formats changed unexpectedly during ingestion. 3. Audit recent silver layer transformations and joins against customer master reference tables to verify whether missing join keys, unmatched reference records, or recent transformation changes cause the email attributes to become null. By completing this investigation, you have isolated the root cause and determined whether the null values originated from the upstream source, schema evolution, field mapping, or downstream transformation logic. Phase 3. Targeted resolution. 1. Fix the root cause, whether it is updating the JSON parser field mapping, fixing a broken join, or adjusting upstream schema handling. 2. Reprocess only the affected silver and gold partitions after validating the fix, using idempotent processing to restore missing email values without creating duplicate customer profiles. 3. Rerun column-level null checks on the updated gold partition and verify email completeness before notifying marketing and notification service owners. By completing these recovery steps, the missing email attributes have been safely restored, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement strict column-level null threshold tests in DBT or Great Expectations that block gold table publishing if null rates exceed acceptable limits. 2. Establish a formal data contract with upstream producer teams to enforce schema compatibility and prevent unannounced field renames. 3. Add automated schema evolution monitoring that immediately detects missing fields, unexpected payload structures, or incompatible schema changes during ingestion. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Traces field-level lineage, fixes JSON mapping or join logic in the transformation code, and executes the partition backfill. 2. Data quality engineer. Defines column completeness rules, configures null rate monitoring and observability alerts, and validates the restored email attributes before downstream consumption. Pro tip: a technically successful pipeline does not guarantee business-ready data. Even with 100% pipeline success, missing attributes like customer emails, tax IDs, or payment tokens can render downstream applications ineffective. Always monitor column-level completeness, null rate trends, and business-critical attributes, not just pipeline execution status.
Scenario 4. During daily audits, you discover that a REST API ingestion pipeline is intermittently skipping pages of records during extraction. The pipeline completes with a success status, but downstream tables are missing transactions. How do you investigate, resolve, and prevent this pagination extraction issue?
Answer: when an API extraction pipeline skips pages while reporting successful completion, the issue is commonly caused by pagination logic errors, rate limiting, expired cursor tokens, retry failures, or changes in the vendor API behavior. To isolate the root cause, safely recover the missing records, and prevent future page loss, I follow a structured production response like Phase 1. Detection and validation. 1. Compare the total records extracted into the bronze layer with the total record count reported by the upstream API to confirm whether complete pages were successfully ingested. 2. Inspect pagination state logs to identify whether page skips follow a pattern tied to specific execution times or payload sizes. 3. Run sequence gap detection queries on auto-incrementing IDs or transaction timestamps in the landing layer to locate missing page boundaries. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an extraction pagination completeness incident. Phase 2. Investigation root cause. 1. Inspect ingestion logs and HTTP responses to verify whether rate limiting, gateway timeouts, authentication failures, or retry exhaustion caused page requests to be skipped. 2. Review the pagination logic to confirm that page offsets or cursor tokens advance only after the current page has been successfully retrieved and validated. 3. Verify whether the upstream API recently changed its pagination behavior, response format, authentication requirements, page size limits, or cursor expiration policy by reviewing vendor documentation, release notes, or API version changes. By completing this investigation, you have isolated the root cause and determined whether the page skips were caused by unhandled HTTP status codes, cursor drift, or flawed pagination code. Phase 3. Targeted resolution. 1. Fix the ingestion code to implement exponential backoff, retry logic, and atomic cursor updates that only advance after payload verification. 2. Re-extract only the affected page ranges or time windows after confirming the fix, avoiding unnecessary full reloads of successfully processed data. 3. Validate total record counts, sequence continuity, and business-level reconciliation between the bronze landing layer and the upstream API before notifying downstream consumers. By completing these recovery steps, the missing API pages have been safely restored, business continuity has resumed, and downstream systems can reliably consume the complete dataset. Phase 4. Long-term prevention. 1. Implement automated pagination completeness checks that compare the expected number of API pages or records with the actual data extracted before publishing downstream. 2. Route malformed or failed API page requests to a dead letter queue with automated retry mechanisms instead of continuing silently. 3. Configure orchestration workflows to respect vendor rate limits, implement adaptive throttling, and automatically retry failed page requests without skipping data. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors pagination logic, implements exponential backoff retries, and orchestrates the targeted re-extraction of affected page ranges. 2. Data quality engineer defines extraction completeness rules, builds sequence gap monitoring tests, and validates that all expected records have been successfully recovered before downstream consumption. Pro tip: treat your pagination state as a checkpoint, not a counter. Never advance a page number or cursor token until the current page has been successfully received, validated, and committed. Otherwise, a transient API failure can permanently skip records without triggering any pipeline errors.
Scenario 5. Business users report that the daily revenue dashboard fluctuates wildly throughout the morning. The numbers change every time they refresh. The pipeline is technically succeeding, but the instability is eroding trust. How do you investigate, resolve, and prevent this late-arriving data issue?
Answer: when executive dashboards fluctuate due to late-arriving data, the issue is typically caused by processing time versus event time mismatches, aggressive watermark boundaries, or micro-batch scheduling that ignores upstream network latency. To isolate the root cause, stabilize the reporting layer, and safely incorporate delayed records, I follow a structured production response like Phase 1. Detection and validation. 1. Compare the physical ingestion timestamps against the business event timestamps in the bronze layer to measure the exact latency gap. 2. Validate whether the fluctuations impact all metrics uniformly or are isolated to specific upstream mobile clients or offline point-of-sale systems. 3. Query the dashboard's underlying gold layer views at different intervals to document exactly which partitions are restating and by what volume. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a temporal completeness and late-arriving data incident. Phase 2. Investigation root cause. 1. Inspect the streaming window definitions or incremental batch logic to check if late records are configured to update current day aggregates instead of their actual historical dates. 2. Audit the watermark configuration to see if the pipeline allows late data to pass through without triggering a controlled restatement of downstream tables. 3. Check upstream source systems and network gateways for sudden spikes in queuing or batching delays. By completing this investigation, you have isolated the root cause and determined whether the fluctuations were caused by overly strict watermarks, upstream network latency, or incorrect event time windowing. Phase 3. Targeted resolution. 1. Update the transformation logic to aggregate records strictly by event time rather than pipeline processing time. 2. Recompute the affected historical partitions using a controlled backfill to permanently integrate the late arriving events into the correct historical dates. 3. Publish the dashboard with a clearly visible data as of timestamp or temporarily freeze the executive view until the agreed completeness threshold is reached. By completing these recovery steps, the late events have been safely integrated into the correct time windows, business continuity has resumed, and downstream systems can reliably consume stable metrics. Phase 4. Long-term prevention. 1. Implement robust watermark logic that explicitly defines how late data is handled. For example, append to a new version, drop if too old, or trigger a managed restatement. 2. Publish a data as of timestamp on all executive dashboards to clearly set expectations about data completeness. 3. Configure pipeline alerts that monitor the delta between event generation time and ingestion time, triggering warnings before SLA thresholds are breached. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the windowing logic to use event time processing, adjusts the pipeline watermarks, and orchestrates the historical restatement. 2. Data quality engineer defines acceptable latency thresholds, builds alerts for arrival time drift, and ensures dashboards correctly communicate data freshness constraints. Pro tip: never build executive dashboards using pipeline processing time. If a transaction occurs at 11:59 p.m. but hits the pipeline at 12:01 a.m., processing time logic will assign it to the wrong day, causing endless reconciliation nightmares with finance. Always partition and aggregate by event time.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 6. After a planned database failover on the primary operational system, you discover that the data warehouse is missing thousands of transactions. The change data capture CDC pipeline continued running, but a gap exists. How do you investigate, resolve, and prevent this replication loss?
Answer. When a CDC pipeline misses transactions during an upstream database failover, the issue usually stems from lost transaction logs, broken log sequence number LSN offsets, or replica desynchronization. To isolate the root cause and safely recover the missing transactions without duplicating downstream data, I follow a structured production response like Phase 1. Detection and validation. 1. Compare primary key counts between the source database and the bronze landing layer specifically for the time window surrounding the failover event. 2. Validate whether the data loss is isolated to a specific table or affects all tables monitored by the replication connector. 3. Check automated sequence gap alerts on incrementing transaction IDs to confirm exactly when the pipeline stopped and resumed capturing events. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a CDC replication completeness incident. Phase 2. Investigation root cause. 1. Inspect the CDC connector logs to verify if the connector successfully re-authenticated and found the correct transaction log offset on the newly promoted database node. 2. Audit the database configuration to determine if the failover node retained the identical transaction log WAL or binlog history as the primary node. 3. Review the orchestrator or connector state file to see if the offset cursor was accidentally reset to latest, instead of resuming from the last acknowledged checkpoint. By completing this investigation, you have isolated the root cause and determined whether the data loss was caused by purged transaction logs, orphaned offsets, or a misconfigured failover node. Phase 3. Targeted resolution. 1. Reconfigure the CDC connector offset to a safe historical point just before the failover event, forcing it to reread the missing logs if they are still available. 2. If the transaction logs were purged, execute a targeted snapshot backfill, a direct query strictly for the missing time window to recover the lost records. 3. Utilize upsert or merge statements in the target warehouse to ensure that reprocessing the overlapping time window does not create duplicate entries. By completing these recovery steps, the missing transactions have been safely restored, business continuity has resumed, and downstream systems can reliably consume the complete dataset. Phase 4. Long-term prevention. 1. Implement a heartbeat table in the source database that receives inserts every second to continuously verify end-to-end replication health. 2. Configure the CDC connector to fail loudly and halt replication if it detects an invalid log sequence number, preventing silent data drops. 3. Configure transaction log retention to exceed the maximum expected CDC recovery window, ensuring connectors can safely recover after planned or unplanned outages. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer investigates the log sequence offsets, manages the connector state, and orchestrates the targeted snapshot backfill to bridge the gap. 2. Data quality engineer implements primary key reconciliation checks, monitors the heartbeat table, and validates that the backfilled data perfectly aligns with the source. Pro tip: change data capture is not inherently immune to database failovers. If the newly promoted database node purges old transaction logs before the CDC connector reconnects, the data is gone forever from the stream. Always implement a heartbeat table. If the warehouse stops receiving heartbeat records, halt the pipeline immediately.
Scenario 7. The morning pipeline finishes successfully, but yesterday's data is completely missing from downstream models. You check the raw landing zone, and the data is physically there. How do you investigate, resolve, and prevent this silent exclusion?
Answer: when data physically exists in the raw layer, but is completely excluded from downstream models despite successful pipeline execution, the issue is commonly caused by time zone mismatches, off-by-one errors in dynamic date filters, or strict partition pruning bugs. To isolate the root cause and safely recover the excluded partition, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw bronze tables directly to confirm the exact row count and timestamp boundaries of the ingested data for yesterday's date. 2. Review downstream dashboard queries and silver layer models to verify if the data drop is isolated to a specific reporting time zone or affects all global users. 3. Check partition level volume metrics to confirm whether the target partition exists and whether it contains the expected volume of records. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a partition filtering and boundary completeness incident. Phase 2. Investigation root cause. 1. Review the SQL transformation filters for incorrect comparison operators, date boundary logic, or partition predicates that may unintentionally exclude the target partition. 2. Audit the execution environment's time zone, for example, UTC versus local time, to see if the orchestrator passed a date string that shifted the partition window by several hours. 3. Inspect the macro or template variables in the orchestration tool that generate the dynamic execution date to ensure they align with the expected data window. By completing this investigation, you have isolated the root cause and determined whether the exclusion was caused by time zone skew, off-by-one date logic, or incorrect orchestration template variables. Phase 3. Targeted resolution. 1. Correct the partition filter logic in the transformation code to properly encompass the full 24-hour boundary. 2. Trigger a targeted rerun of the transformation logic specifically for the missing date partition, avoiding the need to re-extract data from the upstream source. 3. Recalculate the affected downstream aggregates using the corrected date boundaries and manually refresh the dependent dashboards. By completing these recovery steps, the missing daily partition has been safely restored, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Standardize all orchestration servers, databases, and transformation layers strictly on UTC, handling local time zone casting only at the BI presentation layer. 2. Implement boundary edge case testing in the CI/CD pipeline to validate partition macros against leap years, daylight saving transitions, and month ends. 3. Deploy continuous partition level reconciliation tests that explicitly fail the pipeline if a newly created gold partition contains 0 rows. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Standardizes the time zone logic, fixes the partition pruning macro in the transformation code, and orchestrates the partition rerun. 2. Data quality engineer. Implements partition-level volume assertions, builds boundary tests in the deployment pipeline, and validates the restored metrics. Pro tip: the most common cause of missing daily data is a mismatch between the orchestrator time zone, usually UTC, and the database storage time zone. If Airflow thinks yesterday ended 5 hours ago, your pipeline will silently exclude an entire block of data. Standardize everything on UTC and explicitly cast to local time only for end users.
Scenario 8. You extract a massive table from an upstream operational database. The ingestion pipeline completes successfully, but row counts are 80% lower than usual. The upstream team started a bulk reload or maintenance operation, while your ingestion pipeline was actively reading the table, resulting in an incomplete extraction. How do you resolve and prevent this concurrency failure?
Answer: when a pipeline extracts partial data because it was interrupted during an upstream maintenance or reload operation, the issue points to a lack of read isolation, decoupled scheduling between operational and analytical systems, or missing database locks. To isolate the root cause, recover the missing data, and safely prevent future concurrency collisions, I follow a structured production response like: Phase 1. Detection and validation. 1. Measure the exact number of extracted rows against historical daily averages to confirm the magnitude of the payload drop. 2. Check the database extraction logs for sudden end-of-file markers, connection resets, or unexpectedly short query execution times. 3. Validate with the upstream database administrators the exact timestamp of their maintenance or reload operation to confirm the overlap. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an extraction concurrency and completeness incident. Phase 2. Investigation root cause. 1. Audit the database transaction isolation levels, for example, read committed versus snapshot to determine why the extraction query did not preserve a consistent view of the data. 2. Review the scheduling overlap between the source system's maintenance jobs and the ingestion pipeline execution window. 3. Inspect the extraction connection strings for missing read-lock configurations that could have prevented the upstream operation from overlapping with extraction. By completing this investigation, you have isolated the root cause and determined whether the incomplete extraction was caused by overlapping maintenance windows, insufficient read isolation, or a lack of operational coordination between source and downstream data teams. Phase 3. Targeted resolution. 1. Coordinate with the source database team to identify when their maintenance or reload operation is complete and verify the table is fully populated. 2. Execute a complete re-extraction of the affected table, intentionally overriding the partially ingested bronze files to ensure a clean state. 3. Rerun the downstream transformations and validate the final gold layer row counts against the fully restored source table. By completing these recovery steps, the missing data has been safely restored, business continuity has resumed, and downstream systems can reliably consume the complete dataset. Phase 4. Long-term prevention. 1. Implement snapshot isolation for all database extractions to guarantee a consistent point-in-time view, regardless of concurrent maintenance operations. 2. Shift large, volatile tables away from batch extraction and move toward an append-only CDC change data capture architecture. 3. Establish API-driven orchestration where the source system emits a data-ready event to trigger ingestion, rather than relying on uncoordinated schedules. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Upgrades the extraction script to utilize snapshot isolation, coordinates the re-extraction, and transitions the pipeline to event-driven triggers. 2. Data quality engineer. Builds volume variance alerts to instantly detect unusually small payload sizes and validates data parity after the reload. Pro tip: never extract massive batch queries directly from active operational tables that undergo frequent maintenance or bulk reloads. Always extract from a read replica using snapshot isolation to protect your extraction state, or better yet, abandon batch extraction entirely in favor of an event-driven CDC architecture.
Scenario 9. The orchestration pipeline glows bright green, indicating complete success. However, business users complain that today's metrics are entirely missing. You check the logs and realize one critical extraction task loaded exactly 0 rows, but didn't fail. How do you fix this silent orchestration failure?
Answer: when an orchestration pipeline reports overall success, despite a critical task silently loading 0 rows, the issue is typically caused by swallowed programming exceptions, empty valid payloads, or misconfigured downstream trigger rules. To isolate the root cause, safely re-execute the failed logic, and prevent silent skips, I follow a structured production response like: Phase 1, Detection and Validation. 1. Review the orchestrator, run logs to pinpoint exactly which extraction task processed 0 rows while returning a successful exit code. 2. Query the target landing table to physically confirm the complete absence of today's records. 3. Validate downstream data models to measure exactly which executive metrics and business domains are degraded by the missing data. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an orchestration and task-level completeness incident. Phase 2. Investigation root cause. 1. Review the task execution logs and implementation to determine whether exceptions were caught and suppressed instead of propagating a failure to the orchestrator. 2. Verify if the upstream system correctly returned an empty array or null payload that the script simply interpreted as a technically successful, albeit empty, execution. 3. Check the orchestrator DAG trigger rules, for example, all_done versus all_success, to ensure a skipped upstream task didn't improperly trigger downstream dependencies. By completing this investigation, you have isolated the root cause and determined whether the silent failure was caused by application exceptions that were caught but never propagated to the orchestrator, empty source payloads, or misconfigured trigger rules. Phase 3. Targeted resolution. 1. Modify the extraction script to explicitly raise an exception if a payload is completely empty when data is strictly expected. 2. Clear the state of the failed task and all of its downstream dependencies in the orchestrator to prepare for a clean rerun. 3. Retrigger the pipeline execution and validate that the data flows correctly into the final gold tables before notifying the business users. By completing these recovery steps, the skip task has been correctly re-executed, business continuity has resumed, and downstream systems can reliably consume the complete dataset. Phase 4. Long-term prevention. 1. Implement minimum row count validation thresholds within the task logic, forcing the script to fail loudly if the extracted volume is below a critical limit. 2. Deploy anomaly detection checks on task output volumes that integrate directly with the orchestrator to halt downstream execution upon variance. 3. Enforce strict code, review policies to ban silent catch-all exception blocks in data pipeline code. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the extraction logic to fail loudly on empty payloads, removes silent exception blocks, and fixes the orchestrator trigger rules. 2. Data quality engineer configures orchestrator-level data quality operators to immediately halt the pipeline if completeness thresholds are not met. Pro tip: the green pipeline illusion happens when an extraction script handles an error internally without returning a non-zero exit code to the orchestrator. Never swallow exceptions. Always raise explicit errors for unexpected empty datasets, forcing the pipeline task to turn red and trigger immediate pager alerts.
Scenario 10. Your streaming pipeline ingests events from 20 different microservices. You discover that one critical microservice silently stopped publishing events to the message broker 3 days ago. The overall stream volume looked normal, so alerts never fired. How do you resolve this producer-level completeness failure?
Answer: when a single microservice silently stops publishing events while the aggregate streaming pipeline appears healthy, the issue is commonly caused by producer-side network partitions, rotated authentication credentials, or application-level panics. To isolate the root cause, safely recover the missing events, and prevent future silent drops, I follow a structured production response like: Phase 1. Detection and validation. 1. Monitor the incoming topic metrics on the message broker, explicitly grouping the message volume by publisher ID or schema source. 2. Query the downstream landing tables to confirm a complete absence of the specific event type over the last 72 hours. 3. Confirm with the upstream software engineering team whether the microservice is still active and processing operational traffic. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a producer-level streaming completeness incident. Phase 2. Investigation root cause. 1. Inspect the microservice application logs for connection timeouts, broker authentication rejections, or memory exhaustion errors. 2. Audit the producer configuration for acknowledgement policies, retry settings, batching behavior, or queue overflow conditions that may silently discard events. 3. Review recent network security deployments to verify if a firewall or VPC route change blocked the microservice from reaching the broker. By completing this investigation, you have isolated the root cause and determined whether the silent drop was caused by expired credentials, producer queue exhaustion, or a network partition. Phase 3. Targeted resolution. 1. Coordinate with the backend team to restart the microservice, rotate credentials, or fix the network route to restore the real-time connection. 2. Trigger a historical replay of the internal outbox table from the microservice database to push the missing 72 hours of events into the broker. 3. Ingest the recovered events into the warehouse using idempotency keys to ensure late-arriving events do not duplicate state. By completing these recovery steps, the missing microservice events have been safely restored, business continuity has resumed, and downstream systems can reliably consume the complete dataset. Phase 4. Long-term prevention. 1. Implement the transactional outbox pattern on the microservice side to guarantee events are persisted locally before attempting broker delivery. 2. Configure publisher heartbeat monitoring that expects a minimum frequency of events per specific producer ID, rather than relying on aggregate topic volume. 3. Establish topic-level freshness alerts that trigger a high-priority page if any registered producer ID goes completely silent for more than 15 minutes. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer coordinates with backend teams to replay from the outbox table, ensures idempotency during recovery, and configures producer-level metrics. 2. Data quality engineer establishes producer-level volume baselines, configures SLA freshness monitoring, and validates the integrity of the replayed data. Pro tip: in distributed streaming architectures, never monitor message brokers purely by overall topic volume. A high-volume producer can completely mask the death of a low-volume, highly critical payment service. Always set up freshness and volume alerts, grouped by the specific producer or schema ID.
Category 1 Conclusion: Data completeness and missing data.
In Category 1, we established that a pipeline's green execution status never guarantees data utility or business readiness. We mastered systematic investigation techniques across 10 distinct completeness failure modes, ranging from row-level dropped partitions and silent microservice drops to column-level null spikes and temporal watermark fluctuations. By applying a structured 4-phase incident response framework, we learned how to isolate root causes, execute targeted backfills without downtime, and implement long-term quality safeguards before downstream business users report corrupted metrics.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition. Category 1 with data completeness and missing data to Category 2, duplicate data and idempotency.
We are now pivoting from data absence to data inflation, moving from completeness failures directly into duplicate data and idempotency. While missing records erode trust and create gaps in reporting, duplicate records are significantly more dangerous because they actively corrupt financial metrics, double count revenue, and trigger unauthorized real-world customer actions through operational APIs. Mastering this shift requires moving away from reactive data cleaning and instead designing architectures that guarantee idempotent execution regardless of how many times a pipeline retries or replays. Data.
Category 2 overview. Designing for idempotency.
In Category 2, top-tier tech interviewers evaluate whether you can build system architectures that handle at least once delivery guarantees without corrupting destination state. We will explore 10 high-frequency production scenarios covering pipeline retry duplications, Kafka topic offset replays, CDC log rereads, SQL merge cardinality explosions, and operational reverse ETL side effects. Strong candidates must demonstrate how to combine atomic staging rights, deterministic surrogate hashing, and sliding window deduplication to ensure system state remains perfectly consistent across retries.
Category 2. Duplicate data and idempotency scenarios.
Here are the 10 production duplication scenarios we are going to solve in this category. Scenario 11. Duplicate orders appear after pipeline retries. Scenario 12. Kafka message replay doubles yesterday's transactions. Scenario 13. CDC reprocesses already committed records. Scenario 14. Merge operation creates duplicate customer profiles. Scenario 15. Late arriving events create duplicate fact table entries. Scenario 16. Multiple ingestion jobs accidentally run simultaneously. Scenario 17. Missing idempotency causes duplicate invoice generation. Scenario 18. REST API sends duplicate pages. Scenario 19. Surrogate keys regenerate after historical reload. Scenario 20. Webhook retry creates duplicate business events. Let's deep dive into Scenario 11.
Scenario 11. An overnight batch pipeline failed midway due to a transient network timeout and automatically retried. The retry succeeded, but finance reports that today's order count and revenue metrics are exactly double what was expected. How do you investigate, resolve, and prevent this retry duplication issue?
Answer: when pipeline retries generate duplicate records, the root cause is typically a lack of right idempotency, non-atomic append operations, or missing staging boundaries. To isolate the root cause, safely deduplicate the dataset, and enforce retry idempotency, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the target table using group by on business primary keys such as order ID to measure the exact count of duplicated records. 2. Check the ingestion metadata timestamps to confirm whether the duplicate records share identical order creation times but different pipeline load times. 3. Verify downstream gold tables and executive dashboards to measure the exact financial metrics impacted by the double-counted orders. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an ingestion retry duplicate incident. Phase 2. Investigation root cause. 1. Review the target write strategy to determine whether retries append data instead of performing idempotent merge, upsert, or partition override operations. 2. Inspect the task execution logs to confirm if the initial failed run committed partial writes before crashing, which were then appended again by the retry run. 3. Audit the staging boundary to see if temporary loading tables were cleared prior to re-executing the failed task. By completing this investigation, you have isolated the root cause and determined whether the duplicates were caused by non-atomic append writes, missing write audit publish boundaries, or uncheckpointed retry states. Phase 3. Targeted resolution. 1. Execute a targeted deduplication query using window functions, such as qualify row underscore number over partition by order underscore ID order by load underscore timestamp desk, to isolate unique records. 2. Atomic overwrite the affected partition in the warehouse with the deduplicated dataset to immediately correct downstream reporting. 3. Rerun data reconciliation tests between the landing layer and final gold tables to confirm row count and revenue parity. By completing these recovery steps, the duplicate order records have been safely deduplicated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Convert all target loading steps from simple appends to idempotent merge statements or partition-level dynamic overwrites. 2. Implement the write audit publish pattern, so pipeline retries write to isolated staging locations that are audited before committing to production. 3. Deploy automated primary key uniqueness assertions in DBT or Great Expectations that halt downstream jobs if duplicate keys are detected. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Converts target write statements to idempotent merge logic, refactor staging cleanups, and executes the partition deduplication. 2. Data quality engineer. Defines primary key uniqueness tests, builds automated volume reconciliation alerts, and validates financial metric recovery. Pro tip: never use raw insert or append operations in batch pipelines that have automated retry logic enabled. If a job fails at 99% completion, an append retry will duplicate 99% of your data. Always design for idempotency by using merge, upsert, or atomic partition overrides.
Scenario 12. To recover from an upstream consumer crash, the streaming team reset the Kafka consumer group offset back by 24 hours. The message replay succeeded, but downstream real-time tables now contain duplicate transactions for yesterday. How do you resolve and prevent this stream replay duplication?
Answer: when replaying a streaming log causes transaction duplication, the issue stems from uncheckpointed state, missing event deduplication windows, or non-idempotent streaming syncs. To isolate the root cause, deduplicate the real-time layer, and enforce idempotent stream processing, I follow a structured production response like Phase 1. Detection and validation. 1. Query the real-time table using event transaction IDs to verify the extent of the duplicate entries generated by the 24-hour offset replay. 2. Validate whether the duplicates are present in the raw stream landing layer, the transformed real-time table, or both. 3. Check streaming consumer lag metrics to verify if offset rereading has caught up to the live event head. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a stream replay duplicate incident. Phase 2. Investigation root cause. 1. Inspect the streaming sync implementation to determine if incoming events are written using append-only logic instead of idempotent upserts. 2. Audit the deduplication state store such as RocksDB or Delta Lake logs to verify if the deduplication time window was shorter than the 24-hour replay period. 3. Review consumer offset checkpoint logs to confirm why the consumer crashed and failed to commit its offset prior to the reset. By completing this investigation, you have isolated the root cause and determined whether the duplication was caused by uncheckpointed consumer offsets, missing event ID deduplication keys, or an intentional full topic reread. Phase 3, Targeted Resolution. 1. Execute a batch deduplication job on the affected target partitions, grouping by the unique event ID and selecting the latest processing timestamp. 2. Configure the streaming sync to perform idempotent writes using the event business key or another immutable event identifier. 3. Validate transaction totals between the raw Kafka topic message count and the deduplicated target table for the replayed time window. By completing these recovery steps, the replayed transaction records have been safely deduplicated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4, Long-Term Prevention. 1. Implement a sliding window deduplication layer in the streaming engine that caches unique event IDs across a configurable lookback period. 2. Configure streaming syncs to use transactional writes or idempotent storage formats such as Iceberg or Delta Lake that natively drop duplicate primary keys. 3. Establish strict operational runbooks that require disabling downstream sync triggers before manually rewinding streaming consumer offsets. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Configures sliding window deduplication in the streaming framework, refactors sync connectors to use upserts, and performs batch cleanup. 2. Data quality engineer. Builds stream to storage reconciliation tests, monitors event ID uniqueness, and validates data consistency post-replay. Pro tip: never assume a message queue guarantees exactly once delivery end-to-end. Kafka guarantees at least once delivery. The responsibility for exactly once processing lies at the storage sink. Always ensure your storage layer handles duplicates natively using event ID deduplication or idempotent merge operations.
Scenario 13. Due to a transaction log offset reset, a change data capture CDC pipeline reprocessed 3 days of database wall logs. Instead of updating existing rows, the target table appended duplicate records for every historical update and insert event. How do you resolve and prevent this CDC duplication?
Answer: when a CDC reread creates duplicate records instead of updating state, the root cause is a mismatch between append-only ingestion logic and CDC change event semantics. To isolate the root cause, consolidate the change log, and enforce proper stateful CDC processing, I follow a structured production response like Phase 1. Detection and Validation. 1. Query the target warehouse tables to check if historical primary keys appear multiple times with different change sequence metadata. 2. Measure the ratio of duplicate primary keys across the 3-day log reread window to determine the scope of table inflation. 3. Confirm whether downstream analytical views are querying raw change logs directly instead of materialized current state tables. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a change data capture replay duplicate incident. Phase 2. Investigation root cause. 1. Inspect the silver layer transformation code to verify whether raw CDC change events insert, update, delete were ingested using raw append statements. 2. Audit the CDC metadata headers such as log sequence number, transaction commit time, and operation type to confirm the ordering of the reprocessed events. 3. Review the target table schema to check if primary key constraints or merge key definitions were omitted during recent migrations. By completing this investigation, you have isolated the root cause and determined whether the duplicate records stemmed from log sequence number resets, append-only target inserts, or missing primary key merge semantics. Phase 3. Targeted Resolution. 1. Build a deduplication query using qualify row underscore number over partition by primary underscore key order by LSN underscore number desk. Commit underscore timestamp desk to isolate the latest record state. 2. Materialize the deduplicated latest state records into a clean target partition, overriding the inflated table state. 3. Update downstream reporting models to query the materialized current state table rather than the raw change log. By completing these recovery steps, the reprocessed change logs have been safely consolidated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Separate CDC storage into a raw append-only bronze changelog layer and a deduplicated silver current state layer powered by automated merge logic. 2. Implement automated log sequence number ordering tests that ensure out-of-order or duplicate CDC events never overwrite newer record states. 3. Configure CDC ingestion jobs to use native upsert or merge primitives based on primary key constraints rather than basic file appends. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Implement stateful merge logic for CDC processing, builds current state materializations, and deduplicates the inflated tables. 2. Data quality engineer. Defines primary key uniqueness rules on silver tables, verifies CDC commit sequence ordering, and validates final state parity against source. Pro tip: never expose raw CDC append logs directly to business users. A CDC stream is a change log, not a state table. Always land raw CDC events into bronze and use a stateful merge or windowed qualify statement to materialize a deduplicated current state silver table for analytics.
Scenario 14. A nightly merge operation designed to update customer profiles unexpectedly multiplied the total row count in the master customer table by 3 times. The job completed without throwing SQL errors. How do you investigate, resolve, and prevent this merge cardinality explosion?
Answer: when a SQL merge operation multiplies row counts without throwing syntax errors, the issue is caused by non-unique join keys in the source dataset, null key collisions, or unhandled many-to-many match conditions. To isolate the root cause, repair the corrupted table, and prevent cardinality explosions, I follow a structured production response like Phase 1. Detection and validation. 1. Query the target master customer table to measure total row count growth compared to historical baseline values. 2. Run duplicate key detection queries on the target table's primary key such as customer_ID to confirm key fan out. 3. Validate downstream dimension tables and join models to identify which dependent business reports are reporting inflated customer metrics. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a merge-join cardinality duplication incident. Phase 2. Investigation root cause. 1. Inspect the incoming staging source table to check if duplicate records existed on the merge-join key prior to executing the statement. 2. Review the merge on clause logic to check if join keys contained null values that caused Cartesian matches across multiple unassigned profiles. 3. Audit recent upstream source system updates to see if a key generation bug began issuing non-unique customer identifiers. By completing this investigation, you have isolated the root cause and determined whether the profile duplication was caused by non-unique merge join keys, unexpected null join keys, or unhandled many-to-many source matches. Phase 3. Targeted resolution. 1. Restore the master customer table from a pre-merge table snapshot or time travel state to immediately eliminate the corrupted 3 times fan out. 2. Deduplicate the incoming staging dataset using row underscore number over partition by customer underscore ID order by updated underscore at desk to guarantee strict 1-to-1 match cardinality. 3. Re-execute the merge operation using the deduplicated staging source and verify row count parity before releasing the table for downstream query access. By completing these recovery steps, the duplicated customer profiles have been safely consolidated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Add mandatory pre-merge assertions that fail the pipeline if the staging source table contains duplicate join keys. 2. Update the merge on clause to explicitly filter out or handle null values in join keys, for example, on target.id equals source.id and source.id is not null. 3. Utilize modern lakehouse table constraints such as primary key uniqueness enforcement or merge match safeguards that abort execution on cardinality fan out. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer fixes the staging deduplication logic, refactors the SQL merge on condition, and executes time travel table recovery. 2. Data quality engineer implements pre-merge key uniqueness tests, sets threshold alerts for row count anomalies, and validates post-merge dimension metrics. Pro tip: in SQL, a merge statement does not automatically guarantee a one-to-one match. If your incoming staging table contains duplicate join keys, the merge statement will silently duplicate matching rows in your target table. Always enforce primary key uniqueness on your staging dataset before calling merge.
Scenario 15. A batch job processes late arriving sales events from last month. When joining against the slowly changing dimension SCD Type 2 customer table, the query matches multiple historical dimension records, duplicating the fact table entries. How do you resolve and prevent this join fan-out?
Answer: when late arriving events duplicate fact entries during dimensional joins, the root cause is a point-in-time lookup failure where event timestamps fall across multiple historical dimension version windows without proper date range boundaries. To isolate the root cause, fix the join logic, and deduplicate the fact table, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the process fact table using order IDs to identify records that generated multiple rows with different surrogate dimension keys. 2. Measure the total revenue inflation in affected historical fact partitions caused by the duplicated transaction entries. 3. Validate whether the duplication is restricted to late arriving records or affects standard daily batch processing. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a late arriving dimension join fan-out incident. Phase 2. Investigation root cause. 1. Inspect the dimensional SQL join clause to check if the fact event timestamp was matched against the dimensions effective_start_date and effective_end_date range. 2. Audit the dimension table to verify if open-ended historical versions contain overlapping or null effective_end_date values. 3. Review the surrogate key assignment logic to determine if late arriving events defaulted to joining on natural keys without versioning constraints. By completing this investigation, you have isolated the root cause and determined whether the duplication originated from missing effective date range checks, overlapping dimension surrogate keys, or unversioned point-in-time joins. Phase 3. Targeted resolution. 1. Rewrite the dimensional join query to explicitly enforce point-in-time matching. For example, event_timestamp is greater than or equal to effective_start_date, and event_timestamp less than coalesce with effective_end_date, 31st December 9999. 2. Execute a targeted deduplication on the affected fact table partition, retaining only the record matched to the correct historical surrogate key. 3. Reconcile aggregate fact totals against source transactional totals to confirm financial metric accuracy. By completing these recovery steps, the duplicated fact table entries have been safely pruned, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Create point-in-time PIT lookup helper tables or optimized DBT macros that handle SCD Type 2 joins safely across all historical fact models. 2. Add automated schema validation checks on dimension tables to prevent overlapping effective date ranges during dimension updates. 3. Deploy post-join row count assertions that verify fact table row counts match incoming transaction volume exactly before publishing. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the dimensional SQL join logic to enforce point-in-time boundaries, fixes effective date logic, and re-executes fact partition loading. 2. Data quality engineer. Builds dimension date overlap tests, verifies fact-to-dimension join cardinality, and validates financial metric parity. Pro tip: joining late arriving facts to an SCD Type 2 dimension, using only the natural key, is a guaranteed recipe for data duplication. You must always perform a point-in-time PIT join, using the transaction event time mapped between the dimension's effective start and effective end timestamps.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 16. Due to an orchestrator scheduler glitch, 2 identical instances of the hourly file ingestion pipeline ran at the exact same time. Both jobs processed the same landing files, writing duplicate records into the target warehouse table. How do you resolve and prevent this concurrency race condition?
Answer: when concurrent job executions process identical landing files simultaneously, the issue stems from a lack of distributed job locks, missing file lease mechanisms, or unfenced worker retries. To isolate the root cause, purge the duplicate execution outputs, and enforce concurrency safeguards, I follow a structured production response like: Phase 1. Detection and validation. 1. Inspect landing zone files and target table metadata to confirm if identical file paths were processed simultaneously by 2 distinct job run IDs. 2. Query the target warehouse tables to measure the percentage of duplicate records created during the concurrent execution window. 3. Check orchestrator concurrency logs to verify why 2 worker nodes acquired processing locks for the same schedule. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an uncoordinated job concurrency duplication incident. Phase 2. Investigation root cause. 1. Audit the orchestrator DAG configuration settings to check if max_active_runs or concurrency limits were set incorrectly. 2. Review the file landing layer logic to determine why the first job did not move or archive process files before the second job initiated execution. 3. Inspect connection logs to check if a worker node lost heartbeats, triggering a secondary worker execution while the original job was still actively committing records. By completing this investigation, you have isolated the root cause and determined whether the double ingestion was caused by overlapping cron schedules, missing distributed lock leases, or unfenced worker retries. Phase 3. Targeted resolution. 1. Identify the specific run ID associated with the secondary concurrent job and execute a targeted purge of records tied to that run ID. 2. Archive or move the landing zone files into a processed folder to prevent any subsequent automated retries from rereading them. 3. Rerun reconciliation checks on the target partition to confirm that row counts match the exact source file manifest. By completing these recovery steps, the concurrently ingested duplicate files have been safely purged, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Enforce strict orchestrator-level concurrency limits, for example, max_active_runs equals 1, and implement distributed lock leases, such as distributed lock manager on file directories. 2. Shift file ingestion frameworks to atomic move patterns, where files are immediately moved to a processing directory before extraction begins. 3. Utilize target storage formats that enforce file-level idempotency by tracking ingested file hashes in a metadata table and dropping duplicate files automatically. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Configures orchestrator concurrency limits, implements atomic file moving patterns, and executes run ID targeted purges. 2. Data quality engineer. Builds file manifest reconciliation checks, monitors job lock acquisition alerts, and validates target partition row counts. Pro tip: never read landing files directly from an Active Directory without an atomic move step. Always move incoming files to an isolated processing /folder first, or use a distributed lock manager. If two workers scan the same folder at the same time, both will process the exact same data.
Scenario 17. A reverse ETL pipeline pushes billing metrics from the warehouse to an external payment gateway. A network retry during pipeline execution caused the API connector to submit identical billing payloads twice, resulting in duplicate real-world invoices sent to customers. How do you resolve and prevent this operational duplication?
Answer: when a reverse ETL or operational data pipeline generates duplicate real-world side effects during retries, the issue stems from missing API idempotency keys, uncheckpointed target webhooks, or pipeline reruns against unflagged operational tables. To isolate the root cause, remediate the operational state, and enforce strict API idempotency, I follow a structured production response like: Phase 1. Detection and validation. 1. Correlate warehouse billing IDs against payment gateway transaction logs to identify the exact customer accounts subjected to duplicate invoice generation. 2. Immediately pause the reverse ETL pipeline execution to prevent further automated duplicate submissions while investigating. 3. Work with finance and customer support teams to quantify the financial impact and identify which external invoices were successfully processed versus pending. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an operational side effect idempotency incident. Phase 2. Investigation root cause. 1. Inspect the API connector code to check if HTTP requests were transmitted without including a unique, deterministic idempotency key in the request headers. 2. Audit the reverse ETL execution logs to determine if network timeouts caused the connector to assume failure and retry payloads that had actually succeeded downstream. 3. Review the warehouse source table to check if processed records were flagged as sync_completed atomically during execution. By completing this investigation, you have isolated the root cause and determined whether the duplicate invoices were triggered by missing client-side idempotency keys, uncheckpointed target webhooks, or pipeline reruns against active operational tables. Phase 3. Targeted resolution. 1. Issue an automated cancellation or void request via the Payment Gateway API, specifically for the duplicate invoice IDs created during the retry execution window. 2. Update the warehouse synchronization tracking table to correctly mark affected customer records as processed, preventing re-triggering upon pipeline resume. 3. Validate operational state parity between the warehouse billing records and the payment gateway balance before resuming the reverse ETL pipeline. By completing these recovery steps, the duplicate operational requests have been safely canceled, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Mandate that all operational and reverse ETL connectors pass a deterministic idempotency key, such as a hash of order_ID plus billing_date in HTTP request headers. 2. Implement a two-phase commit pattern in reverse ETL pipelines, where destination system receipt is verified before marking records as synced in the warehouse. 3. Add dry run validation steps and rate-limiting safeguards in CI/CD for any pipeline that interacts directly with customer-facing operational APIs. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer implements deterministic HTTP idempotency keys and API connectors, updates synchronization state tracking, and builds operational retry safeguards. 2. Data quality engineer verifies operational sync parity, audits external API delivery logs, and builds automated alerts for duplicate external payload creation. Pro tip: when writing data back to operational systems reverse ETL, pipeline retries do not just corrupt database tables. They charge real credit cards and send real emails. Never call an operational API without passing a deterministic business identifier, for example, order ID or invoice ID.
Scenario 18. A vendor REST API returns identical pages of data when paginating using timestamp offsets, causing your ingestion pipeline to store thousands of duplicate records in the bronze landing layer. How do you resolve and prevent this pagination overlap duplication?
Answer: when an API returns duplicate pages during extraction, the issue stems from vendor-side cursor reset bugs, ambiguous timestamp boundary filtering, or stateless page extraction loops. To isolate the root cause, deduplicate the landing layer, and enforce page payload deduplication, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the bronze landing files to measure record duplicate rates by hashing raw page payloads or comparing unique record IDs across page files. 2. Validate whether page duplication occurs consistently on every extraction run or is restricted to high-volume timestamp boundaries. 3. Check downstream pipeline tables to verify if the duplicate raw API records propagated into silver and gold reporting models. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an API pagination overlap duplication incident. Phase 2. Investigation root cause. 1. Inspect the API request params to determine if greater than or equal to is greater than or equal to timestamp filters caused records on exact second boundaries to be returned on adjacent pages. 2. Audit the pagination cursor state logging to check if the ingestion script resent expired cursor tokens that caused the vendor API to default back to page 1. 3. Review the vendor API documentation to check if record sorting order by was omitted, causing records to shift across page boundaries between HTTP requests. By completing this investigation, you have isolated the root cause and determined whether the page duplication was caused by vendor-side cursor reset bugs, ambiguous timestamp boundaries, or stateless page extraction loops. Phase 3. Targeted resolution. 1. Refactor the extraction query to use strictly greater than timestamp boundaries or enforce explicit record sorting parameters in API requests. 2. Execute a targeted deduplication in the bronze to silver transformation step using unique business record keys and payload hashes. 3. Validate total, unique record counts between the API response metadata and the deduplicated silver table before refreshing downstream views. By completing these recovery steps, the duplicate API page records have been safely deduplicated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement payload-level hashing such as MD5 or SHA-256 on raw API page files to automatically drop duplicate page responses before writing to bronze. 2. Establish strict cursor state validation in ingestion scripts that verifies page tokens change on every request and halts processing if duplicate pages are returned. 3. Add automated record-level deduplication as a standard primitive in all bronze to silver transformation models. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Updates API pagination parameters, implements raw page hashing, and refactors silver layer transformation deduplication. 2. Data quality engineer. Configures page-level payload duplicate monitoring, audits API response record counts, and validates silver table uniqueness. Pro tip: never trust vendor APIs to handle pagination cleanly. Vendor APIs frequently suffer from boundary overlap bugs where updated underscore at is greater than or equal to timestamp returns the last record of page 1 as the first record of page 2. Always implement raw payload hashing or explicit primary key deduplication in your bronze to silver step.
Scenario 19. Following a full historical reload of a dimension table, auto-incrementing surrogate keys were regenerated with completely new integer IDs. This broke foreign key relationships across historical fact tables, multiplying row counts during joins. How do you resolve and prevent this surrogate key drift?
Answer: when historical reloads regenerate auto-incrementing surrogate keys, the issue is caused by non-deterministic key generation logic, stateful identity sequences, or unseeded key generators. To isolate the root cause, repair foreign key integrity, and transition to deterministic surrogate key hashing, I follow a structured production response like Phase 1. Detection and validation. 1. Query historical fact tables to verify foreign key join failures and measure the row count fan out caused by mismatched surrogate identifiers. 2. Check the dimension table metadata to confirm if the primary surrogate key column values changed for historical natural business keys. 3. Validate downstream analytical models to identify which historical reports are displaying corrupted or duplicated dimensional attributes. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a surrogate key regeneration duplication incident. Phase 2. Investigation root cause. 1. Audit the dimension table creation DDL to check if the surrogate key was defined using non-deterministic stateful sequences such as auto-increment or identity. 2. Review the historical reload script to determine why stateful lookup mapping tables were dropped or truncated without preserving key history. 3. Inspect foreign key assignment models in downstream pipelines to see if fact tables rely on volatile integer keys rather than stable natural key lookups. By completing this investigation, you have isolated the root cause and determined whether the key drift was caused by stateful auto-increment sequences, unseeded identity columns, or non-deterministic key generation logic during full reloads. Phase 3. Targeted resolution. 1. Refactor the dimension table to generate deterministic surrogate keys using deterministic hashes such as MD5 or SHA-256 computed from the natural business keys. 2. Reprocess the historical fact tables to update foreign key references using the new deterministic hash identifiers. 3. Validate foreign key integrity tests and confirm row count parity between fact transactions and dimension lookups before releasing downstream tables. By completing these recovery steps, the regenerated surrogate keys have been safely remapped to deterministic hashes, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Eliminate volatile stateful auto-increment sequences in modern data warehouses and mandate deterministic hashing. For example, dbt_utils.generate_surrogate_key for all surrogate keys. 2. Implement automated foreign key integrity checks in CI/CD pipelines that fail builds if dimension reloads alter historical key mappings. 3. Maintain immutable natural key mapping tables whenever non-deterministic surrogate keys are strictly required by legacy data systems. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors dimension DDL to use deterministic hash surrogate keys, updates fact foreign key mapping logic, and executes table backfills. 2. Data quality engineer defines foreign key referential integrity tests, audits surrogate key stability across reloads, and validates model accuracy. Pro tip: never use database auto-increment or identity sequences for surrogate keys in modern data warehouses. They are stateful and non-deterministic. If you ever reload your dimension table, all keys will change and break historical fact relationships. Always generate surrogate keys using deterministic hashes like MD5 with natural underscore key.
Scenario 20. An external payment provider retries sending webhook events due to brief network latency on your receiving endpoint. Because the ingestion handler lacked deduplication caching, duplicate event records were ingested into the warehouse. How do you resolve and prevent this webhook retry duplication?
Answer: when webhook retries create duplicate business events in the warehouse, the issue stems from missing event ID deduplication stores, short cache TTL expiration windows, or unhandled delivery acknowledgments. To isolate the root cause, purge the duplicate event payloads, and implement real-time deduplication caching, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw webhook landing table using the vendor event ID to measure the duplicate event rate generated during the network retry window. 2. Check downstream event-driven tables to identify if duplicate payment events cause double counting of transaction statuses or customer balances. 3. Verify the webhook receiver logs to correlate HTTP 504 timeouts with retry delivery timestamps from the vendor. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a webhook retry deduplication incident. Phase 2. Investigation root cause. 1. Inspect the webhook receiver service code to determine if incoming payloads were acknowledged with an HTTP 200 OK status before or after committing to storage. 2. Audit the deduplication cache such as RIDIs to check if the TTL expiration window was set too short to catch retries arriving minutes or hours later. 3. Review downstream ingestion queries to check if raw webhook landing tables were exposed directly to analytics without primary key deduplication. By completing this investigation, you have isolated the root cause and determined whether the duplicate event creation was caused by missing event ID deduplication stores, short cache TTL expiration windows, or unhandled 200 OK delivery acknowledgments. Phase 3. Targeted resolution. 1. Deduplicate the raw webhook landing layer using qualify row underscore number over partition by event underscore ID order by received underscore and ask to retain only the initial delivery payload. 2. Extend the deduplication cache TTL window in the webhook receiver service to cover extended vendor retry periods. 3. Rematerialize the downstream event models using the cleaned landing dataset and verify event count parity against vendor delivery logs. By completing these recovery steps, the duplicate webhook event payloads have been safely deduplicated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement an in-memory key value cache such as RIDIs at the API gateway layer to instantly reject duplicate event IDs within a window that exceeds the provider's documented retry period. 2. Architect the webhook handler to immediately write raw payloads to an append-only message queue and return an HTTP 200 OK acknowledgement asynchronously. 3. Deploy automated uniqueness assertions on event IDs in downstream silver models to ensure duplicate payloads never reach gold reporting layer. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer configures real-time deduplication caching in the API receiver, decouples endpoint acknowledgement via asynchronous queuing, and cleans landing data. 2. Data quality engineer. Monitors webhook event uniqueness rates, verifies vendor delivery parity, and builds automated alerts for duplicate payload arrivals. Pro tip: webhook endpoints should always be asynchronous. Never process heavy business logic or database. Write synchronously inside a webhook handler. Immediately write the raw payload to a queue. Return an HTTP 200 OK to the vendor, and let a background worker handle deduplication and ingestion.
Category 2 Conclusion: Duplicate data and idempotency.
In Category 2, we established that a pipeline running twice should never produce double the data. We mastered systematic investigation techniques across 10 distinct duplication failure modes, ranging from non-atomic pipeline retries and Kafka offset resets to SQL merge cardinality explosions and operational reverse ETL side effects. By applying our structured incident response framework, we learned how to isolate fan-out logic, execute targeted deduplication without data loss, and implement long-term idempotent safeguards like deterministic hashing and sliding window caches.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition. Category 2 with duplicate data and idempotency to Category 3, data accuracy and business logic.
We are now pivoting from structural data issues to semantic data issues, moving from duplicate data directly into data accuracy and business logic. While missing or duplicate records are usually technical infrastructure failures, accuracy failures are often silent business logic failures. A pipeline can execute perfectly, loading the exact right number of unique rows. But if the exchange rate is applied twice or a floating point calculation truncates currency decimals, the executive dashboard is still completely wrong. Mastering this shift requires bridging the gap between raw code and actual business reality.
Category 3 overview. Designing for accuracy.
Top-tier tech interviewers evaluate whether you actually understand the data you are moving. In Category 3, we will explore 10 high-frequency production scenarios covering dimensional fan-outs, floating point truncation, time zone offset drift, hierarchical reconciliation, and semantic metric drift. Strong candidates must demonstrate how to combine cross-layer reconciliation, explicit schema casting, semantic layer alignment, and robust reference data orchestration to ensure data is not just technically present, but mathematically and financially accurate.
Category 3. Data accuracy and business logic scenarios.
Here are the 10 production accuracy scenarios we are going to solve in this category. Scenario 21. Revenue suddenly increases by 300%. Scenario 22. Negative inventory quantities appear after transformation. Scenario 23. Order totals do not equal item totals. Scenario 24. Exchange rates are applied twice. Scenario 25. Time zone conversion shifts transactions into the wrong business day. Scenario 26. Currency conversion uses stale FX rates. Scenario 27. Decimal precision is lost after ETL transformations. Scenario 28. Tax calculation logic changes without notification. Scenario 29. Derived KPIs differ from finance calculations. Scenario 30. Aggregation logic excludes canceled orders incorrectly. Let's deep dive into Scenario 21.
Scenario 21. The daily executive dashboard shows that revenue suddenly increased by exactly 300% compared to yesterday. Order volumes remain normal, but the financial totals are massively inflated. How do you investigate, resolve, and prevent this dramatic accuracy failure?
Answer: when financial totals multiply symmetrically, while raw transaction volumes remain stable, the issue is almost always caused by a one-to-many join fan-out against unversioned dimension tables. To isolate the root cause, safely consolidate the data, and prevent dimensional explosions, I follow a structured production response like Phase 1. Detection and validation. 1. Query the gold layer aggregated revenue tables to confirm the exact inflation multiplier across different product categories and regions. 2. Validate the bronze layer raw order counts to verify that the upstream source did not actually generate triple the volume of transactions. 3. Check downstream foreign key relationships to identify which dimensional attributes were added or modified in the latest batch run. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a dimensional join accuracy incident. Phase 2. Investigation root cause. 1. Inspect the silver layer SQL transformations to identify where the central fact table joins against upstream reference dimensions like products or customers. 2. Audit the product dimension table to check if a recent update created 3 active versions of the same product without properly terminating the old records. 3. Review the join conditions to see if a point-in-time date filter was omitted, causing each transaction to match all 3 historical versions of the dimension. By completing this investigation, you have isolated the root cause and determined whether the revenue inflation was caused by overlapping dimension effective dates, missing point-in-time join clauses, or duplicate reference data. Phase 3. Targeted resolution. 1. Fix the dimension table by explicitly terminating the older overlapping versions and ensuring strict uniqueness on the active indicator or date boundaries. 2. Refactor the fact table SQL join to strictly enforce effective date boundaries, ensuring a strict 1-to-1 cardinality match for every order. 3. Overwrite the corrupted silver and gold partitions with the corrected query to instantly restore accurate revenue reporting. By completing these recovery steps, the inflated revenue metrics have been safely corrected, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Deploy automated uniqueness assertions on all dimension tables to guarantee that no natural key has more than one active record at any given time. 2. Implement row count parity tests in DBT that fail the pipeline if the output of a dimensional join contains more rows than the incoming fact table. 3. Enforce strict code review policies requiring all dimensional joins to include explicit timestamp boundaries. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the SQL join logic to enforce point-in-time boundaries, cleans up the overlapping dimension records, and recalculates the partitions. 2. Data quality engineer builds row count parity assertions, monitors dimension table uniqueness, and validates the restored financial metrics. Pro tip: a one-to-many join fan-out is the most common cause of sudden, symmetrical data inflation. If revenue goes up by exactly 2 times or 3 times overnight, you did not have a great sales day, you have a corrupted dimension table duplicating your facts. Always test your joins for strict 1-to-1 cardinality.
Scenario 22. A streaming analytics pipeline tracks warehouse inventory. During a flash sale, the dashboard suddenly reports negative available stock for several popular items, which should be physically impossible. How do you investigate, resolve, and prevent this logical inaccuracy?
Answer: when physical metrics like inventory fall into impossible negative balances, the issue is typically caused by out-of-order stream processing, race conditions between independent operational services, or delayed restock events. To isolate the root cause, reconcile the inventory state, and prevent future race conditions, I follow a structured production response like Phase 1. Detection and validation. 1. Query the real-time inventory state table to measure exactly how many product identifiers are exhibiting negative stock balances. 2. Compare the analytical warehouse balance against the source operational database to determine if the negative value originated upstream or during pipeline aggregation. 3. Verify the event logs to trace the chronological sequence of purchase and restock messages for the affected products. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an event ordering accuracy incident. Phase 2. Investigation root cause. 1. Inspect the stream processing framework to determine if purchase deduction events were processed faster than supplier restock events due to differing topic partitions. 2. Audit the watermark and state store configuration to check if out-of-order events were allowed to immediately update the global balance without temporal sorting. 3. Review the upstream microservice architecture to see if a distributed transaction failure caused a purchase to commit while a related inventory check timed out. By completing this investigation, you have isolated the root cause and determined whether the negative balances were caused by out-of-order stream delivery, decoupled source services, or lack of stateful windowing. Phase 3. Targeted resolution. 1. Trigger a state recalculation in the streaming engine, forcing it to sort all historical events for the affected products strictly by event generation time. 2. If the source system itself contains the negative balance, coordinate with back-end engineering to apply a compensating restock transaction to zero out the discrepancy. 3. Refresh the downstream inventory views to reflect the corrected, chronologically sorted balance. By completing these recovery steps, the inventory state has been safely recalculated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement event time windowing and stateful buffering in the streaming pipeline to sort incoming messages chronologically before updating final balances. 2. Add logical boundary constraints in the silver layer that flag and quarantine any record where calculated inventory falls below zero. 3. Transition the pipeline from calculating deltas +1 or -1 to ingesting absolute state snapshots emitted directly by the source database. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the streaming aggregation to buffer and sort by event time and transitions the ingestion to absolute state snapshots. 2. Data quality engineer defines logical boundary assertions for inventory limits and builds real-time alerts for mathematically impossible states. Pro tip: calculating running totals using stream deltas additions and subtractions is highly fragile. If a single restock event is delayed or dropped, the entire downstream balance is permanently corrupted. Whenever possible, design your pipelines to ingest absolute state snapshots rather than attempting to calculate running deltas in flight.
Scenario 23. The finance team discovers a massive reconciliation gap. The total revenue reported in the order header table is $50,000 less than the sum of the order line items table. How do you investigate, resolve, and prevent this hierarchical reconciliation failure?
Answer: when header-level aggregates do not match the sum of their line items, the issue typically points to distributed discount logic, missing tax allocations, or shipping costs stored exclusively at the header level. To isolate the root cause, enforce hierarchical parity, and correct the financial models, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a cross-table reconciliation query, joining the order header and order line tables to isolate exactly which order IDs contain mathematical discrepancies. 2. Measure the exact variance ratio to determine if the $50,000 difference correlates to a specific flat shipping fee, tax rate, or promotional discount code. 3. Validate whether the discrepancy is a historical anomaly or an ongoing issue across all recent data partitions. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a hierarchical parity and mathematical accuracy incident. Phase 2. Investigation root cause. 1. Inspect the source application payload to determine if coupon codes or cart-level discounts are applied to the header total without being proportionately distributed to individual items. 2. Audit the ETL transformation code to verify if shipping fees and regional taxes are accidentally excluded when aggregating line item revenue for downstream reporting. 3. Review the handling of canceled or refunded items to see if partial refunds update the header total but leave the original line items intact. By completing this investigation, you have isolated the root cause and determined whether the variance was caused by undistributed header discounts, excluded shipping fees, or partial refund desynchronization. Phase 3. Targeted resolution. 1. Refactor the bronze to silver transformation logic to proportionately allocate header-level discounts and fees down to the individual line item granularity. 2. Backfill the affected historical line item partitions to reflect the newly calculated distributed net revenue per item. 3. Execute a final reconciliation query to mathematically prove that the sum of the updated line items perfectly matches the order header gross totals. By completing these recovery steps, the hierarchical data has been safely reconciled, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement automated cross-model reconciliation tests in DBT that fail the pipeline if header totals diverge from line item sums by more than 1 cent. 2. Define explicit semantic rules in the metric layer that standardize whether gross revenue, net revenue, or shipping inclusive revenue is used for executive reporting. 3. Establish data contracts with upstream engineering to mandate that all new promotional discounts are explicitly tracked at the line item level. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the allocation logic in the transformation layer, builds the proportional distribution math, and executes the historical backfill. 2. Data quality engineer builds hierarchical cross-model tests, configures variance alerts, and mathematically validates the reconciliation output. Pro tip: never assume that the sum of the parts equals the whole in e-commerce data. Cart-level coupons, flat rate shipping, and partial refunds frequently break hierarchical integrity. Always build your transformations to allocate header-level modifiers down to the line item grain, ensuring perfect mathematical parity across all reporting layers.
Scenario 24. After source system migration, the daily sales dashboard for the UK region plummets. Upon investigation, you realize British pounds were converted to US dollars by the source system, and then the ETL pipeline blindly converted them again. How do you resolve and prevent this double conversion issue?
Answer: when mathematical modifiers like currency exchange rates are applied twice, the issue points to silent upstream logic changes, a lack of metadata indicators, or non-idempotent transformation layers. To isolate the root cause, reverse the mathematical error, and ensure conversion idempotency, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw bronze layer to compare the numeric transaction values and currency string codes from before and after the source system migration. 2. Measure the exact variance ratio to mathematically confirm that the discrepancy perfectly matches the current GBP to USD exchange rate. 3. Check downstream regional reports to identify if this double conversion impacted all international markets or just a single specific region. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a double transformation accuracy incident. Phase 2. Investigation root cause. 1. Inspect the source system, API payloads to confirm if the upstream team silently changed the base currency payload without updating the associated currency symbol field. 2. Audit the ETL transformation script to check if the conversion logic relies on hard-coded regional assumptions rather than explicit row-level currency indicators. 3. Review the release notes and migration documentation from the upstream team to pinpoint exactly when the native currency conversion feature was enabled. By completing this investigation, you have isolated the root cause and determined whether the double application was caused by silent upstream normalization, missing currency metadata, or hard-coded pipeline assumptions. Phase 3. Targeted resolution. 1. Update the ETL transformation logic to only apply exchange rates if the explicitly provided row-level currency code is not already USD. 2. Reverse the double conversion for the affected historical window by dividing the corrupted values by the exact exchange rate used during ingestion. 3. Validate the recalculated financial aggregates against the source system's native reports to confirm perfect dollar parity. By completing these recovery steps, the double conversion has been safely reversed, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4 Long-Term Prevention 1. Enforce strict data contracts requiring upstream systems to explicitly transmit both the original currency code and the converted currency code on every transaction payload. 2. Implement pipeline assertions that mathematically compare day-over-day regional averages, immediately flagging drastic drops caused by currency miscalculations. 3. Shift financial conversion logic exclusively into the warehouse semantic layer, allowing source systems to send raw, unmanipulated local currency. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the pipeline to dynamically read currency metadata, removes hard-coded regional assumptions, and executes the mathematical backfill. 2. Data quality engineer defines data contracts for currency payloads, builds day-over-day variance monitors, and mathematically verifies the corrected metrics. Pro tip: idempotency is not just about preventing duplicate rows, it is about preventing duplicate math. If your pipeline applies an exchange rate or tax calculation, it must first inspect the data to guarantee the operation hasn't already occurred. Always rely on row-level metadata indicators, never on hard-coded regional assumptions.
Scenario 25. The daily sales aggregates generated by the warehouse are consistently lower than the real-time application database at the end of the day. You discover that transactions occurring between 8 p.m. and midnight local time are silently rolling over into the next business day. How do you resolve and prevent this time zone offset failure?
Answer: when transactions silently shift into incorrect business days, the issue is consistently caused by local time to UTC conversion mismatches, missing time zone offsets in source payloads, or presentation layer cast failures. To isolate the root cause, realign the temporal boundaries, and enforce global time zone standards, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw bronze tables to inspect the exact string format of incoming timestamps and determine if ISO time zone offsets are included. 2. Compare hourly transaction volumes between the warehouse and the source database, specifically during the midnight rollover window, to measure the variance. 3. Validate downstream reports to see if this shift impacts all global users or is isolated to a specific server processing region. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a temporal offset accuracy incident. Phase 2. Investigation root cause. 1. Inspect the extraction query to see if local database timestamps were ingested without an explicit at-time zone conversion, causing the warehouse to assume they were UTC. 2. Audit the daily orchestration partitioning logic to check if data is being chunked based on server execution time rather than the actual transaction event time. 3. Review the downstream BI tool configuration to verify if local dashboard time zone casting is accidentally reversing a previously applied offset. By completing this investigation, you have isolated the root cause and determined whether the rollover was caused by missing source offsets, incorrect pipeline UTC assumptions, or presentation layer casting bugs. Phase 3. Targeted resolution. 1. Refactor the ingestion and transformation logic to explicitly cast all incoming timestamps to strict UTC before storing them in the data warehouse. 2. Reprocess the historical partitions by shifting the affected timestamp column by the exact missing hour offset, bringing the data back into the correct business days. 3. Validate the daily aggregate totals against the source system to mathematically prove the 8 p.m. to midnight transactions are correctly assigned. By completing these recovery steps, the temporal boundaries have been safely realigned, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Standardize all data engineering infrastructure, including databases, orchestrators, and file storage, to operate strictly on the UTC time zone. 2. Enforce strict schema validation on incoming data payloads, requiring all timestamp strings to include an explicit ISO time zone offset. 3. Push all local time formatting and daylight saving logic to the absolute edge of the semantic layer, keeping core warehouse tables strictly in UTC. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Standardizes the storage layer to UTC, fixes the ingestion timestamp casting, and executes the historical temporal shift. 2. Data quality engineer. Builds hourly volume variance tests to detect rollover gaps and validates end-user semantic layer configurations. Pro tip: time zones are the silent killers of financial reconciliation. Never store local time in a data warehouse. If a transaction occurs at 9 p.m. in New York, the database must store it as 1 a.m. UTC. Handle the local offset presentation entirely in the BI tool to ensure global aggregation consistency.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 26. The executive revenue dashboard looks accurate overall, but the international conversions are slightly off. You investigate and discover the pipeline successfully completed, but it joined today's sales transactions against yesterday's foreign exchange FX rates. How do you resolve and prevent this reference data timing failure?
Answer: when fact tables join against stale reference data, the root cause is almost always a race condition in pipeline orchestration, missing cross-DAG dependencies, or delayed third-party API updates. To isolate the root cause, synchronize the datasets, and enforce reference data freshness, I follow a structured production response like Phase 1. Detection and validation. 1. Query the daily revenue fact table and inspect the specific FX rate multiplier applied to recent transactions. 2. Cross-reference the applied multiplier against the official FX reference table to confirm the exact date mismatch. 3. Validate whether the stale rate issue affects all foreign currencies or just a specific delayed API feed. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a reference data freshness and join time accuracy incident. Phase 2. Investigation root cause. 1. Audit the orchestrator DAG to verify if the sales fact transformation job executed before the FX reference ingestion job successfully completed. 2. Inspect the FX ingestion logs to determine if the third-party exchange rate API experienced a timeout, causing the table to silently retain yesterday's data. 3. Review the SQL join logic to see if a fallback coalesce function was intentionally designed to use the latest available rate when today's rate is missing. By completing this investigation, you have isolated the root cause and determined whether the stale join was caused by orchestration race conditions, delayed vendor APIs, or intentional fallback logic. Phase 3. Targeted resolution. 1. Manually trigger the FX reference pipeline to successfully fetch and load the correct exchange rates for the current business day. 2. Re-execute the daily sales transformation logic to overwrite the affected partition, applying the correct updated multipliers. 3. Validate the newly calculated international totals against real-time operational reports to confirm mathematical accuracy. By completing these recovery steps, the financial aggregates have been safely recalculated with fresh reference data, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement orchestration sensors or cross-DAG dependencies that strictly block the sales fact transformation until the FX reference table achieves current-day freshness. 2. Deploy freshness SLAs on all critical reference tables that trigger immediate pager alerts if data is not updated by the required morning cutoff time. 3. Add data quality assertions in the semantic layer that warn business users if a dashboard is currently utilizing fallback or stale exchange rates. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. implements orchestrator sensors, enforces cross-pipeline dependencies, and recalculates the affected fact partition. 2. Data quality engineer defines reference data freshness SLAs, builds table update alerts, and implements dashboard warning indicators. Pro tip: never assume your dimension tables will load before your fact tables just because you scheduled them 30 minutes apart. Scheduling by time guarantees race conditions. Always enforce explicit state dependencies, using orchestration sensors to block fact processing until the dimension data is physically verified as fresh.
Scenario 27. The analytics team reports a creeping financial variance. Individual transaction values look fine, but when millions of rows are summed in the gold layer, the totals differ from the source database by hundreds of dollars. You suspect decimal precision is being lost during transformation. How do you resolve and prevent this?
Answer: when massive aggregations exhibit creeping mathematical variance, while individual rows appear correct. The issue almost always stems from floating point arithmetic errors or aggressive schema coercion dropping decimal precision. To isolate the root cause, correct the data types, and ensure absolute mathematical accuracy, I follow a structured production response like: Phase 1. Detection and validation. 1. Execute a sum aggregation on the raw bronze layer and compare it strictly against the sum of the gold layer to calculate the exact fractional variance. 2. Inspect individual transaction records to verify if subcent fractions are present in the source but missing or rounded in the target. 3. Check downstream models to identify if this variance is affecting revenue reporting, tax calculation, or inventory valuation. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a schema casting and mathematical precision incident. Phase 2. Investigation root cause. 1. Audit the table DDL and schema inference logic to determine if the pipeline ingested financial values as approximate float 64 types instead of exact numeric or decimal types. 2. Inspect the transformation code to check if integer division or implicit rounding functions were applied prematurely before the final aggregation step. 3. Review the raw JSON or CSV payloads to see if the source system itself began transmitting scientific notation or truncated strings. By completing this investigation, you have isolated the root cause and determined whether the precision loss was caused by floating point data types, premature rounding, or upstream payload formatting. Phase 3. Targeted resolution. 1. Refactor the pipeline schema definitions and table DDL to explicitly cast all financial and metric columns to fixed precision decimal types. 2. Execute a full historical table overwrite, forcing the pipeline to reread from the raw files using the corrected fixed precision schema. 3. Perform a strict checksum and aggregation reconciliation between the new gold table and the source database to confirm perfect mathematical parity down to the cent. By completing these recovery steps, the creeping mathematical variance has been safely eliminated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Establish strict architectural guidelines banning the use of float or real data types for any column representing currency, taxes, or financial metrics. 2. Disable automatic schema inference on file ingestion paths, requiring explicit schema registries that mandate decimal precision constraints. 3. Implement highly sensitive cross-layer parity tests in CICD that fail builds if aggregate totals diverge by more than a fraction of a cent. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer replaces float variables with fixed precision decimal casts, disables automated schema inference, and orchestrates the historical reload. 2. Data quality engineer defines strict monetary data type standards, builds micro-variance detection tests, and mathematically certifies the aggregation logic. Pro tip: Never use float data types for money. Floating point numbers are mathematical approximations. When you sum 10 million floats, the tiny fractional errors compound into massive financial discrepancies. Always enforce explicit, fixed precision decimal or numeric data types from the moment data lands in your warehouse.
Scenario 28. A daily automated audit flags a sudden variance in net profit margins. You discover the upstream source system implemented a new regional tax calculation, but they didn't notify the data team. Your pipeline's hard-coded business logic is now calculating metrics incorrectly. How do you resolve and prevent this silent drift?
Answer: when downstream reporting breaks due to unannounced upstream business logic changes, the root cause is tightly coupled hard-coded transformations and a lack of organizational data contracts. To isolate the root cause, align the transformation logic, and prevent future silent drift, I follow a structured production response like Phase 1. Detection and validation. 1. Query the impacted financial tables to measure the exact date the variance started and isolate the discrepancy to specific regions or product categories. 2. Compare the calculated warehouse tax totals against the raw tax values provided in the upstream source payload to quantify the drift. 3. Verify downstream dashboards to measure the impact on net revenue and profit margin reporting. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a silent business logic and transformation accuracy incident. Phase 2. Investigation root cause. 1. Inspect the silver layer ETL code to confirm if tax logic was hard-coded as a static percentage rather than being read dynamically from a reference table. 2. Review upstream release notes and software commit logs to identify when the software engineering team deployed the new tax engine update. 3. Audit the ingestion payload schema to see if new explicit tax fields were added that the pipeline simply ignored. By completing this investigation, you have isolated the root cause and determined whether the drift was caused by hard-coded pipeline assumptions, unannounced upstream deployments, or ignored payload fields. Phase 3. Targeted resolution. 1. Refactor the transformation logic to remove hard-coded percentages and instead dynamically apply tax calculations based on the raw payload values. 2. Backfill the data strictly for the time window starting from the upstream deployment date to realign the warehouse totals with the source truth. 3. Reconcile the updated profit margins with the finance team to confirm that all reports are mathematically sound. By completing these recovery steps, the obsolete business logic has been safely replaced, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Migrate all volatile business rules out of pipeline code and into centralized, version-controlled reference data tables managed by business stakeholders. 2. Establish semantic data contracts that require upstream engineering teams to notify and version their APIs before changing core financial logic. 3. Implement statistical drift monitors on derived metrics to instantly flag unexpected shifts in ratios like tax to revenue. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the pipeline to decouple hard-coded logic, integrates dynamic reference tables, and executes the targeted historical backfill. 2. Data quality engineer. Builds statistical drift monitors for financial ratios, enforces data contract policies, and validates metric alignment. Pro tip: hard-coding business logic like tax rates, discount tiers, or shipping fees inside Python or SQL scripts is technical debt. When business rules change, your code silently rots. Always abstract volatile business logic into reference tables so business users can update the parameters without requiring an engineering deployment.
Scenario 29. During a quarterly review, the chief financial officer points out that the data team's active subscription revenue dashboard is consistently 5% higher than the official finance ledger. The pipeline execution is perfect. How do you investigate, resolve, and prevent this semantic metric drift?
Answer: when technically flawless pipelines produce metrics that diverge from official financial ledgers. The issue is entirely semantic, caused by misaligned business definitions, inconsistent filtering, or shadow IT reporting. To isolate the root cause, align the metric definitions, and enforce semantic consistency, I follow a structured production response like Phase 1. Detection and validation. 1. Extract the exact SQL query powering the data team's dashboard and request the exact logic or spreadsheet formula used by the finance team. 2. Run a granular row-by-row comparison between the two datasets for a specific month to isolate the exact subset of user IDs causing the 5% variance. 3. Validate whether the discrepancy is growing over time or remains a constant percentage, indicating a systemic logic difference. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified IT as a semantic definition and business metric accuracy incident. Phase 2. Investigation root cause. 1. Inspect the isolated variance records to identify hidden patterns such as trial users, paused subscriptions, or refunded accounts. 2. Audit the dimensional filters in the BI layer to determine if the data team includes booked revenue, while finance strictly tracks recognized revenue. 3. Review the underlying metric layer definitions to check if the logic for active customer was silently updated without consulting cross-functional stakeholders. By completing this investigation, you have isolated the root cause and determined whether the semantic drift was caused by divergent business definitions, missing status filters, or unrecognized revenue states. Phase 3. Targeted resolution. 1. Facilitate a reconciliation meeting with the finance team to officially document and agree upon the exact enterprise definition of active subscription revenue. 2. Update the semantic layer queries and DBT models to strictly enforce the newly agreed upon filtering and inclusion logic. 3. Backfill and regenerate the entire historical dashboard to ensure long-term trend charts perfectly match the official financial ledger. By completing these recovery steps, the semantic definitions have been safely aligned, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement a centralized headless metric store or semantic layer to ensure a single metric definition is universally queried by all downstream tools. 2. Establish a data governance council where metric definition changes require explicit sign-off from domain owners before merging into production. 3. Deploy automated reconciliation scripts that run daily comparisons between the warehouse semantic layer and the official ERP financial ledger. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer implements the agreed business logic into the centralized metric store, standardizes the transformation models, and recalculates history. 2. Data quality engineer facilitates the stakeholder definition mapping, builds automated ledger reconciliation tests, and audits the semantic layer. Pro tip: the most dangerous data quality issues are not pipeline errors, they are semantic errors. If engineering defines active customer as anyone who logged in, but finance defines it as anyone who paid a bill, your data is fundamentally broken despite perfect execution. Always centralize core business definitions in a version-controlled metric layer.
Scenario 30. A business analyst notices that historical monthly sales totals are slowly decreasing over time. You investigate and realize that when an order is canceled months later, the mutable status field is overwritten in the source database, which causes your pipeline to retroactively erase it from historical aggregates. How do you resolve and prevent this?
Answer: when historical aggregates drift over time due to status field updates, the root cause is a failure to manage state immutability, missing point-in-time snapshots, or direct querying of mutable source tables. To isolate the root cause, restore historical immutability, and manage late-state changes, I follow a structured production response like Phase 1. Detection and Validation. 1. Query historical aggregate tables and compare current state totals against archive static reports from previous months to quantify the decay. 2. Isolate the specific records that disappeared from the historical aggregate and verify if their current source status is marked as canceled or refunded. 3. Check downstream executive trend charts to determine how severely the historical drift is skewing year-over-year growth calculations. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an aggregate drift and mutable state incident. Phase 2. Investigation root cause. 1. Inspect the extraction layer to confirm if the pipeline uses destructive upsert logic that completely overwrites the original transaction record. 2. Audit the silver layer aggregation query to check if it applies a strict where status is not equal to canceled filter on mutable records instead of using point-in-time state. 3. Review the underlying data model to verify if a slowly changing dimension SCD Type 2 or immutable ledger architecture is completely missing. By completing this investigation, you have isolated the root cause and determined whether the historical decay was caused by destructive upserts, mutable status filtering, or a lack of historical snapshots. Phase 3. Targeted resolution. 1. Redesign the aggregate model to calculate historical gross sales based exclusively on the initial order creation event, completely ignoring late-state cancellations. 2. Build a secondary reporting view specifically designed to track late-state refunds and cancellations assigned to the actual date the refund occurred. 3. Reconstruct the affected historical aggregates using raw immutable event logs to restore the original point-in-time revenue figures. By completing these recovery steps, the historical aggregates have been safely restored, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Transition the core data architecture to an immutable event ledger where changes like cancellations are inserted as new events rather than overriding old rows. 2. Implement slowly changing dimensions SCD Type 2 for all mutable entities to track exactly what a record looked like at any specific point in time. 3. Deploy automated regression tests that compare daily aggregate snapshots against historical baselines, triggering alerts if past months drift unexpectedly. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Transitions the architecture to an immutable event ledger, implements SCD Type 2 tracking, and recalculates historical baselines. 2. Data quality engineer. Builds historical snapshot regression tests, verifies point-in-time accuracy, and audits downstream metric stability. Pro tip: never filter historical aggregates using mutable current state columns. If an order was placed in January and canceled in March, January's gross sales report should not magically change in March. Always model financial transactions as an immutable ledger of events, tracking sales and refunds on the days they actually occurred.
Category 3 Conclusion. Data accuracy and business logic.
In Category 3, we established that mathematically incorrect data is far more dangerous than missing data. We mastered systematic investigation techniques across 10 accuracy failure modes, ranging from dimension, join fan-outs, and floating point truncation to time zone rollovers and stale reference data. Key takeaway: data accuracy is more than correct row counts. In production systems, accuracy depends on 9 core dimensions: dimensional integrity, event ordering, hierarchical reconciliation, transformation logic, temporal correctness, reference data freshness, numerical precision, business rule consistency, and historical immutability. Mastering these dimensions enables you to troubleshoot not just failing pipelines, but misleading business outcomes.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition. Category 3 with data accuracy and business logic to Category 4 semantic quality and business rules.
We are now pivoting from mathematical accuracy to semantic meaning, moving directly into semantic quality and business rules. A pipeline can execute perfectly, and the math can add up flawlessly. But if the engineering team defines an active customer differently than the marketing team, the business still fails. Mastering this shift requires stepping outside the codebase and entering the business domain, transforming abstract company policies into strictly versioned, governable code.
Category 4 Overview: Defending the Semantic Layer.
Top-tier tech interviewers evaluate your ability to resolve cross-functional disputes and govern business logic at scale. In Category 4, we will explore 10 high-frequency scenarios covering interdepartmental metric conflicts, semantic layer misconfigurations, silent rule drift, and shadow IT reporting. Strong candidates must demonstrate how to use headless metric stores, definition versioning, and stakeholder mapping to ensure that the entire enterprise speaks the exact same language.
Category 4 Semantic Quality and Business Rules Scenarios.
Here are the 10 production semantic scenarios we are going to solve in this category. Scenario 31. Active customer is defined differently across sales and marketing. Scenario 32. Revenue differs between finance and BI dashboards. Scenario 33. Customer churn calculation changes after business policy updates. Scenario 34. Inventory availability differs between warehouse and ERP. Scenario 35. Gross margin KPI differs across reports. Scenario 36. Executive dashboard does not match operational reports. Scenario 37. Business users report wrong numbers despite technically successful pipelines. Scenario 38. Semantic layer produces inconsistent KPIs. Scenario 39. Product hierarchy changes invalidate historical reporting. Scenario 40. Business rule drift silently changes long-term trend analysis. Let's deep dive into Scenario 31.
Scenario 31. The CEO complains that the sales dashboard shows 50,000 active customers, but the marketing dashboard shows 120,000. Both dashboards query the exact same data warehouse, but the teams are fighting over who is correct. How do you resolve and prevent this semantic conflict?
Answer: when different departments report drastically different totals from the same warehouse, the issue is almost always a semantic divergence in BI layer filtering or calculated fields. To isolate the root cause, align the definitions, and enforce semantic consistency, I follow a structured production response like Phase 1. Detection and validation. 1. Extract the raw SQL queries generated by both the sales and marketing BI dashboards to inspect their respective filtering logic. 2. Execute a side-by-side comparison of the two resulting datasets to isolate the exact 70,000 users present in the marketing data but excluded by sales. 3. Interview both domain leaders to document their verbal business definitions of what constitutes an active customer. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a semantic definition and cross-functional alignment incident. Phase 2. Investigation root cause. 1. Inspect the BI layer SQL to determine if marketing defines active as anyone who opened an email in 30 days, while sales defines IT as anyone with a paid invoice. 2. Audit the data catalog to see if a single unified active flag exists in the gold layer, or if both teams were forced to derive their own logic. 3. Review the underlying data models to check for missing semantic layer centralization that allowed shadow logic to proliferate. By completing this investigation, you have isolated the root cause and determined whether the conflict was caused by missing centralized metrics, shadow IT reporting, or divergent departmental goals. Phase 3. Targeted resolution. 1. Establish explicit, namespace-separated metrics in the semantic layer, defining them clearly as marketing engaged user versus financially active customer. 2. Deprecate the ambiguous active customer calculated fields in the BI tools, replacing them with the centralized, governed metrics. 3. Refresh both dashboards using the explicitly named metrics to clarify exactly what each chart represents to the executive team. By completing these recovery steps, the semantic conflict has been safely resolved, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Deploy a headless metric store such as DBT metrics or metric flow to centrally define business logic in code, explicitly blocking BI tools from creating custom logic. 2. Establish a data governance council that requires cross-functional sign-off before any Tier 1 business metric is published or altered. 3. Implement a data catalog that explicitly surfaces the mathematical formula and business owner for every semantic metric. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Deploys the centralized metric store infrastructure, translates business rules into code, and restricts BI tool direct table access. 2. Data quality engineer. Facilitates definition alignment across departments, audits the semantic layer code, and verifies that dashboards consume governed metrics. Pro tip: never allow business users to define core business logic in the presentation layer. BI tools are for visualizing data, not defining it. If you let users write custom calculated fields in Tableau or Power BI, you will inevitably end up with 5 different definitions for revenue. Centralize all logic in a headless metric store.
Scenario 32. The data team's real-time BI dashboard shows $2 million in daily revenue, but the finance team's official ERP system reports $1.8 million. The data team claims their pipeline is perfectly capturing all transactions. How do you resolve this financial reconciliation gap?
Answer: when real-time BI dashboards diverge from official ERP ledgers, the issue is almost always related to cash versus accrual accounting differences, omitted tax and shipping deductions, or time zone boundaries. To isolate the root cause, reconcile the ledgers, and enforce financial parity, I follow a structured production response like: Phase 1. Detection and validation. 1. Execute a ledger reconciliation query, joining the warehouse sales table with an export of the finance ERP data to isolate the exact missing $200,000. 2. Verify whether the variance is spread evenly across all transactions or isolated to specific transaction types like refunds, chargebacks, or international sales. 3. Check the timestamp boundaries to ensure both systems are defining the start and end of the business day using identical time zone rules. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a cross-system financial reconciliation incident. Phase 2. Investigation root cause. 1. Inspect the metric definition in the BI tool to check if the data team is aggregating gross revenue, while finance is reporting net revenue minus refunds and taxes. 2. Audit the data pipeline to determine if delayed operational events like credit card chargebacks or deferred revenue recognition are bypassing the real-time stream. 3. Review the ERP integration logic to see if finance applies manual end-of-month journal entries that are completely invisible to the data warehouse. By completing this investigation, you have isolated the root cause and determined whether the financial gap was caused by gross versus net calculation differences, missing operational events, or manual ledger adjustments. Phase 3. Targeted resolution. 1. Align the semantic model to explicitly separate and label gross bookings from net recognized revenue, matching the finance team's exact accounting logic. 2. Integrate the missing event streams such as refund webhooks or manual journal entries into the data warehouse to achieve full ledger parity. 3. Backfill and regenerate the BI dashboards using the updated net revenue logic to perfectly mirror the ERP system. By completing these recovery steps, the financial metrics have been safely reconciled, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Establish automated daily reconciliation tests that compare the data warehouse semantic layer directly against the ERP system, alerting on any variance over 1%. 2. Transition financial dashboards from real-time streaming to a verified batch schedule, ensuring data is only published after all daily accounting rules are applied. 3. Mandate that the finance team owns the ultimate sign-off on any SQL model in the data warehouse that calculates enterprise revenue. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer integrates missing operational data streams, refactors the warehouse models to match accounting logic, and automates ERP comparisons. 2. Data quality engineer investigates the row-level variance, defines the acceptable reconciliation thresholds, and orchestrates the financial sign-off. Pro tip: the data team does not own the definition of revenue. Finance does. If the data warehouse says 2 million and finance says 1.8 million, finance is correct by default because they face legal audits. Never build a revenue dashboard without explicitly mapping your SQL logic to the company's official accounting principles.
Scenario 33. The business operations team quietly changes the company policy, declaring that a customer is only considered churned after 60 days of non-payment instead of 30 days. The data pipeline continues using the hard-coded 30-day rule, resulting in massively over-reported churn. How do you resolve and prevent this policy drift?
Answer: when metrics degrade due to unannounced business policy changes, the root cause is tightly coupled business logic combined with poor cross-functional communication. To isolate the root cause, retroactively apply the new policy and implement logic versioning. I follow a structured production response like: Phase 1. Detection and validation. 1. Compare the warehouse churn metric outputs against the newly updated operational system statuses to identify the exact volume of misclassified users. 2. Validate whether the new 60-day policy applies retroactively to all historical data or only to new subscriptions moving forward. 3. Query downstream executive dashboards to measure how severely the outdated logic is inflating current quarter churn rates. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a business logic drift and semantic alignment incident. Phase 2. Investigation root cause. 1. Inspect the gold layer transformation scripts to verify where the 30-day threshold is hard-coded into the SQL case statements. 2. Audit the organizational communication channels like Jira or release notes to determine why the data team was excluded from the policy change notification. 3. Review the semantic models to see if churn is derived dynamically from an operational configuration table or statically hard-coded in the repository. By completing this investigation, you have isolated the root cause and determined whether the metric drift was caused by hard-coded thresholds, siloed communication, or missing configuration tables. Phase 3. Targeted resolution. 1. Create a versioned metric update, for example, churn_V2 in the semantic layer that incorporates the new 60-day threshold, preserving churn_V1 for historical auditing if required. 2. Backfill the warehouse data according to the finance team's decision on whether the rule should be applied retroactively or point in time. 3. Deploy the updated metric to the BI layer and validate the newly calculated retention numbers against operational realities. By completing these recovery steps, the outdated business logic has been safely upgraded, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Abstract volatile business rules like threshold days out of SQL code and into operational configuration tables managed directly by business stakeholders. 2. Implement shadow deployments for major metric updates, running the old and new logic side by side to quantify impact before fully cutting over. 3. Enforce organizational data contracts requiring business operations to submit a formal pull request when altering enterprise definitions. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the SQL logic to read from dynamic configuration tables, manages the metric versioning, and executes the historical backfill. 2. Data quality engineer validates the impact of the new logic during the shadow deployment phase and ensures dashboards migrate successfully to the new version. Pro tip: business logic changes are inevitable. If you hardcode days greater than 30 in your SQL, you guarantee future technical debt. Always treat thresholds and policy variables as configuration data. Store them in a reference table so the operations team can update the policy themselves without requiring a data engineering code deployment.
Scenario 34. The supply chain dashboard in the data warehouse shows 5,000 units of a product available, but the operational ERP system shows 0 units available. Both systems refreshed 5 minutes ago. How do you resolve and prevent this semantic mismatch in inventory state?
Answer: when identically refreshed systems report drastically different inventory balances, the issue is rarely a pipeline failure. It is usually a semantic mapping error regarding allocated versus physical stock. To isolate the root cause, map the correct operational states, and enforce semantic alignment, I follow a structured production response like: Phase 1, detection and validation. 1. Query the raw ERP replica tables in the bronze layer to verify if the source system transmitted the number 5,000 or the number 0. 2. Execute a granular status check on the 5,000 units in question to see if they are flagged as reserved, in transit, or damaged. 3. Validate whether this discrepancy applies to all product categories or is isolated to items currently undergoing fulfillment. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a semantic state mapping incident. Phase 2. Investigation root cause. 1. Inspect the warehouse transformation logic to determine if the pipeline defines available as physical on-hand inventory, completely ignoring pending digital orders. 2. Audit the ERP business logic to verify that it defines available as physical inventory minus allocated cart reservations. 3. Review the ingestion payload to check if the ERP's internal reservation state column was intentionally dropped or ignored during extraction. By completing this investigation, you have isolated the root cause and determined whether the mismatch was caused by ignored allocation states, dropped payload columns, or divergent definitions of availability. Phase 3. Targeted resolution. 1. Refactor the data warehouse semantic layer to explicitly define and calculate physical inventory versus available to sell inventory. 2. Update the ETL transformation to ingest and deduct the reservation state column, ensuring parity with the ERP's net availability logic. 3. Regenerate the supply chain dashboards using the corrected metric and validate the 0 unit balance against the operational system. By completing these recovery steps, the inventory states have been safely mapped, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement data dictionary standards that ban ambiguous terms like available in favor of explicit terms like available to promise and total physical stock. 2. Establish automated semantic reconciliation checks that run end-of-day comparisons between the warehouse net stock and the ERP net stock. 3. Enforce cross-functional mapping sessions with supply chain domain experts before modeling any new operational state tables. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer updates the extraction logic to include reservation states, refactors the semantic models, and recalculates the historical balances. 2. Data quality engineer validates the semantic mapping with domain experts, builds the reconciliation checks, and updates the data catalog definitions. Pro tip: words like available, active, and complete are the most dangerous words in data engineering. They mean completely different things to a warehouse worker versus a web developer. Always force stakeholders to explicitly define operational states. Replace ambiguous terms with mathematically exact labels in your semantic layer.
Scenario 35. During a board meeting, the CEO opens 3 different automated reports: Tableau, a custom web portal, and an emailed PDF, and sees 3 different numbers for the company's gross margin. How do you investigate, resolve, and prevent this semantic fragmentation?
Answer: when multiple presentation layers display different values for the same fundamental metric, the root cause is shadow IT logic, disconnected calculation engines, or isolated BI caching. To isolate the root cause, unify the calculation engine, and restore executive trust, I follow a structured production response like: Phase 1. Detection and validation. 1. Extract the underlying query or calculated field formula from all 3 reporting applications to document their exact mathematical logic. 2. Query the central data warehouse to verify if a single gross margin metric actually exists, or if users are forced to calculate IT themselves on the fly. 3. Trace the data lineage of each report to see if they query the same gold layer table, or if they are sourcing data from different fragmented data marts. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified IT as a semantic fragmentation and shadow logic incident. Phase 2. Investigation root cause. 1. Inspect the Tableau workbook to see if gross margin is defined using a local calculated field that excludes international shipping costs. 2. Audit the custom web portal's backend code to check if IT applies a hard-coded static tax deduction that the other systems ignore. 3. Review the underlying warehouse semantic models to confirm that no centralized, governed API exists to serve this metric universally. By completing this investigation, you have isolated the root cause and determined whether the fragmentation was caused by localized BI calculations, fragmented data marts, or unversioned shadow IT logic. Phase 3. Targeted resolution. 1. Define a single, universally agreed upon formula for gross margin inside the central data warehouse transformation layer, for example, using dbt. 2. Strip the localized calculated fields out of Tableau, the web portal, and the PDF generator, replacing them with a direct select from the new governed metric. 3. Perform a validation run across all 3 platforms simultaneously to mathematically prove that they now output the exact same figure. By completing these recovery steps, the fragmented logic has been safely unified, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Deploy a headless semantic layer that serves metrics via API, forcing all BI tools and custom portals to query the exact same calculation engine. 2. Lock down presentation layer permission to prevent business users from creating unapproved calculated fields on governed enterprise datasets. 3. Implement a data certification program where only dashboards carrying a governed watermark are allowed to be presented in executive meetings. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer deploys the headless semantic layer API, unifies the transformation logic in the warehouse, and removes shadow reporting tables. 2. Data quality engineer audits the presentation layers for shadow calculations, coordinates metric definitions, and manages the dashboard certification process. Pro tip: if you allow your business users to define their own metrics inside their visualization tools, you have already lost control of data accuracy. Presentation tools should only be allowed to read pre-calculated metrics. The moment someone clicks Create Calculated Field in a BI tool for an enterprise metric, they are creating shadow IT.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 36. The granular operational report lists exactly 10,000 user signups for the month. However, the high-level executive summary dashboard rolls up to only 9,500 signups. The discrepancy is causing executives to distrust the data team. How do you resolve and prevent this aggregation grain failure?
Answer: when detailed operational reports do not match high-level executive aggregations, the issue typically points to silent inner join exclusions, dimension mapping failures, or mismatched filtering at the roll-up phase. To isolate the root cause, realign the aggregation grains, and enforce hierarchical parity, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a minus or accept query between the operational user list and the underlying data powering the executive dashboard to isolate the exact 500 missing users. 2. Inspect the metadata of the 500 isolated users to find commonalities such as missing geographic regions, deleted accounts, or specific sign-up channels. 3. Validate whether the 500 users are actually legitimate business accounts, or if they are internal test accounts correctly excluded from executive metrics. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an aggregation grain and filtering consistency incident. Phase 2. Investigation root cause. 1. Audit the ETL aggregation script to see if a strict inner join on a dimension table like a region mapping table dropped users who had null region values. 2. Review the executive dashboard SQL to determine if a hard-coded where clause silently filtered out accounts marked as freemium or trial. 3. Inspect the operational report to check if it includes duplicate signups or test accounts that the executive roll-up correctly identified and removed. By completing this investigation, you have isolated the root cause and determined whether the mismatch was caused by silent inner joins, undocumented dashboard filters, or uncleaned operational data. Phase 3. Targeted resolution. 1. Change the overly strict inner join to a left join in the aggregation pipeline, ensuring users with missing dimension mappings are preserved under an unknown category. 2. Unify the filtering logic so that both the operational report and the executive dashboard utilize the exact same is_valid_user flag. 3. Reprocess the executive aggregation tables and validate that the top-level rollup perfectly matches the sum of the operational rows. By completing these recovery steps, the aggregation grain has been safely reconciled, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement hierarchical reconciliation tests in the deployment pipeline that guarantee the SUM of granular operational facts exactly equals the top-level executive aggregates. 2. Standardize default dimension handling by ensuring all reference tables contain an unknown or unassigned row to prevent inner join data loss. 3. Expose explicit data lineage in the BI catalog so executives can clearly see the exact filtering rules applied to their dashboards. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors inner joins to left joins, adds unknown dimension records, and unifies the underlying aggregation SQL logic. 2. Data quality engineer. Builds hierarchical cross-check alerts, identifies the missing user patterns, and validates the dashboard filtering alignment. Pro tip: the silent inner join is the most common cause of missing data in executive dashboards. If a user signs up but forgets to select a region, an inner join to the region table will permanently delete that user from the total count. Always use left joins for analytical rollups and map null to an explicit unknown category.
Scenario 37. A business user opens a support ticket stating the numbers look wrong. You check Airflow, DBT, and Snowflake. Every single technical indicator is green. The row counts are normal, and no tests failed. How do you investigate a semantic failure when all technical systems report perfect health?
Answer: when business users report inaccurate numbers despite perfect technical pipeline execution, the issue is almost always upstream schema value drift, reference mapping changes, or undocumented operational shifts. To isolate the root cause, trace the business reality, and close the observability gap, I follow a structured production response like Phase 1. Detection and Validation. 1. Schedule a rapid triage call with the reporting business user to identify exactly which metric, dimension, or specific row looks wrong to their trained eye. 2. Query the specific subset of data identified by the user to measure the exact deviation from historical baseline trends. 3. Validate whether the operational source system's front-end application shows the same wrong numbers, indicating an upstream bug rather than a pipeline error. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a silent source drift and business logic incident. Phase 2. Investigation root cause. 1. Inspect the raw ingested data to check for value-level drift, such as an upstream engineer changing a status string from closed to closed_1 without breaking the schema type. 2. Audit the reference mapping tables to verify if a business user accidentally uploaded a bad CSV that recategorized profitable products into a loss-making category. 3. Review the transformation logic to see if strict string matching rules silently ignored the newly modified upstream values. By completing this investigation, you have isolated the root cause and determined whether the drift was caused by unannounced upstream string changes, corrupted reference data, or rigid transformation rules. Phase 3. Targeted Resolution. 1. Update the warehouse transformation logic to correctly map the new upstream values or rectify the corrupted reference data table. 2. Execute a targeted backfill for the time frame where the silent drift occurred, ensuring the warehouse accurately reflects the corrected categorizations. 3. Reconcile the updated dashboard metrics with the business user to confirm the numbers now align with their operational expectations. By completing these recovery steps, the silent value drift has been safely mapped, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement strict accepted value tests in DBT that automatically fail the pipeline if an upstream column introduces an undocumented categorical string. 2. Establish organizational data contracts that mandate upstream teams must communicate value-level semantic changes, not just structural schema changes. 3. Deploy statistical anomaly detection tools that monitor categorical distributions, alerting engineers if a specific status code suddenly drops to 0. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors transformation logic to handle the new values, implements the backfill, and enforces programmatic data contracts. 2. Data quality engineer. Triages the semantic complaint with the business user, configures accepted value tests, and builds distribution anomaly alerts. Pro tip: technical data observability is not enough. Your pipeline can have perfect row counts and 0 nulls, but if the upstream team changes a string from active to active_user, your downstream case statements will silently evaluate to false. Always implement categorical accepted values testing to catch silent semantic drift.
Scenario 38. Your team recently deployed a headless semantic layer to centralize business logic. However, when business users slice the total revenue metric by the customer acquisition channel dimension, the revenue numbers explode drastically. How do you resolve and prevent this semantic compilation failure?
Answer: when dynamic semantic layers produce massive metric fan-outs during specific dimensional slices, the root cause is typically a compiled many-to-many join, missing primary key definitions in the metric graph, or cross-grain aggregation failures. To isolate the root cause, fix the metric graph, and ensure dynamic query safety, I follow a structured production response like Phase 1. Detection and Validation. 1. Extract the dynamically generated SQL query compiled by the semantic engine when the user requested the specific metric and dimension combination. 2. Query the compiled SQL directly against the warehouse to mathematically reproduce the massive revenue fan out. 3. Validate which other dimensional slices such as time, region, or product cause similar Cartesian explosions when joined against the core metric. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a semantic layer compilation and cross-grain join incident. Phase 2. Investigation root cause. 1. Inspect the semantic layer configuration files to verify if the join path between the revenue fact table and the acquisition channel dimension lacks a direct primary key relationship. 2. Audit the defined granularities to determine if the engine attempted to join a daily fact table against a loosely related event table, creating a Cartesian product. 3. Review the underlying data models to see if a bridge table or chasm trap resolution strategy is missing from the metric graph definition. By completing this investigation, you have isolated the root cause and determined whether the fan-out was caused by missing join keys, incorrect granularity mappings, or unhandled chasm traps in the semantic graph. Phase 3. Targeted resolution. 1. Update the semantic graph configuration to explicitly define the primary and foreign key relationships, enforcing strict one-to-one or many-to-one cardinality. 2. If a direct relationship does not exist, explicitly disable that specific metric to dimension combination in the semantic layer to prevent invalid queries. 3. Recompile the semantic models and validate the generated SQL against the warehouse to prove the revenue totals remain mathematically consistent. By completing these recovery steps, the semantic graph compilation errors have been safely corrected, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement automated compilation testing in CI/CD that programmatically slices every core metric by every available dimension, failing the build if row counts explode. 2. Enforce strict primary key and foreign key constraints on the physical data warehouse tables to guide the semantic engine's join optimizer. 3. Design unified one big table OBT structures for highly critical BI domains to entirely bypass complex on-the-fly semantic join generation. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the underlying warehouse models to support clean dimensional joins and optimizes the semantic graph definitions. 2. Data quality engineer builds automated semantic compilation tests, maps valid dimensional paths, and ensures metric outputs remain consistent. Pro tip: headless semantic layers are powerful, but they dynamically generate SQL on the fly. If you do not explicitly define the primary keys and granularities in your configuration files, the engine will inevitably generate a Cartesian join, a chasm trap. Always test your metrics against every single available dimensional slice before deploying.
Scenario 39. The merchandising team restructures the product catalog, moving several laptops into a new workstations category. The pipeline updates the dimension table via a standard overwrite. Suddenly, last year's historical revenue reports dynamically change, retroactively shifting millions of dollars into the new category. How do you fix this?
Answer: when upstream hierarchy updates retroactively rewrite historical reporting. The root cause is destructive dimension overwrites and a failure to maintain slowly changing dimensions. To isolate the root cause, restore historical immutability, and manage hierarchy drift safely, I follow a structured production response like Phase 1. Detection and validation. 1. Query the historical aggregate tables and compare the current category revenue totals against archived financial snapshots from the previous year. 2. Identify exactly which product IDs were moved into the new workstations category and calculate the exact dollar amount that retroactively shifted. 3. Validate downstream executive dashboards to determine if this retroactive shift broke year-over-year growth comparisons. By completing these validation steps, You have verified the anomaly, measured its business impact, and classified it as a dimensional drift and historical mutation incident. Phase 2. Investigation root cause. 1. Inspect the dimension ingestion pipeline to confirm that it utilizes destructive type 1 updates overriding the category string rather than preserving history. 2. Audit the fact table joins to verify if they rely entirely on the product natural key rather than a time-bound surrogate key. 3. Review the source system payload to check if the merchandising team provided an effective date for the hierarchy change or simply updated the active state. By completing this investigation, you have isolated the root cause and determined whether the historical mutation was caused by type 1 dimension overwrites, missing surrogate keys, or undocumented operational changes. Phase 3. Targeted resolution. 1. Restore the product dimension table from a pre-update backup or time travel snapshot to immediately revert the corrupted historical relationships. 2. Redesign the dimension table to support SCD Type 2 tracking, inserting the new workstations category mapping as a new row with a current effective start date. 3. Reprocess the recent fact table partitions using the new surrogate key, ensuring historical transactions remain permanently tied to the old laptop's category. By completing these recovery steps, the historical revenue aggregates have been safely restored, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Mandate slowly changing dimension SCD Type 2 architectures for all hierarchical reference tables, completely banning destructive Type 1 overwrites. 2. Implement bridge tables for complex, highly volatile ragged hierarchies like sales territories or complex product catalogs to decouple relationships from core dimensions. 3. Deploy automated regression tests that compare monthly historical snapshots against live queries, instantly failing if past data mutates. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the dimension pipeline to support SCD Type 2 logic, implements time-bound surrogate key joins, and restores the historical tables. 2. Data quality engineer. Builds historical snapshot regression tests, audits dimension effective dates, and validates year-over-year metric stability. Pro tip: if you use destructive Type 1 updates on your dimension tables, you are constantly rewriting history. If a product was considered a laptop when it was sold in 2024, the 2024 financial reports must always reflect that, even if it is reclassified in 2026. Always use SCD Type 2 to preserve the exact point in time reality of your business.
Scenario 40. A data scientist analyzing a 3-year historical trend notices a structural break in the data right around 6 months ago. The pipeline hasn't failed once, but the SQL definition for a core filtering metric was silently altered via a GitHub pull request, shifting the entire long-term trend line. How do you resolve this?
Answer: when long-term statistical trends exhibit structural breaks due to silent code alterations, the root cause is unversioned semantic logic, missing change management controls, or retroactive backfill failures. To isolate the root cause, restate the historical baseline, and enforce rigorous logic versioning, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a statistical time series analysis on the affected metric to mathematically pinpoint the exact date the structural break occurred. 2. Compare the metric output from 6 months ago against archived raw data to confirm the variance is programmatic and not a real-world market shift. 3. Validate downstream machine learning models to determine if the shifted trend line corrupted recent training data. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a silent logic drift and structural break incident. Phase 2. Investigation root cause. 1. Inspect the Git version control history for the specific SQL model to identify exactly which pull request altered the where clause or aggregate function 6 months ago. 2. Audit the deployment logs to determine why the new logic was applied only to new incremental partitions, rather than triggering a full historical restatement. 3. Review the code review approval chain to understand why a fundamental definition change bypassed data governance oversight. By completing this investigation, you have isolated the root cause and determined whether the structural break was caused by unrestated historical data, unauthorized logic changes, or incremental processing flaws. Phase 3. Targeted resolution. 1. Force a complete historical backfill of the entire 3-year dataset using the newly defined SQL logic to ensure the trend line is uniform and continuous. 2. If the old logic was actually the correct business definition, revert the git commit and backfill the last 6 months to restore the original baseline. 3. Notify the data science team so they can retrain their machine learning models on the newly unified, continuous dataset. By completing these recovery steps, the continuous historical trend has been safely restored, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement mandatory full refresh triggers in CI/CD pipelines whenever the core logic of a highly critical historical model is modified. 2. Establish strict GitHub code ownership rules code owners requiring explicit approval from a data governance lead before modifying core semantic models. 3. Deploy continuous statistical anomaly detection tools like Monte Carlo or Anomalo to instantly alert teams when a time series trend breaks unexpectedly. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer traces the git commit history, enforces CI/CD full refresh triggers, and orchestrates the massive historical restatement. 2. Data quality engineer deploys statistical anomaly detection, audits the code review process, and communicates the restatement to the data science team. Pro tip: if you change the mathematical definition of a core business metric, you cannot just apply it incrementally moving forward. Changing a formula halfway through the year creates a structural break that destroys machine learning models and year-over-year reporting. You must always backfill the new logic across all historical data.
Category 4 Conclusion. Semantic quality and business rules.
In Category 4, we established that a technically flawless pipeline can still produce completely unusable business data if semantic definitions drift. We mastered systematic investigation techniques across 10 distinct semantic failure modes, ranging from cross-departmental metric disputes and shadow IT reporting to hard-coded business rules and silent operational shifts. Key takeaway: semantic quality is not about moving data correctly. IT is about ensuring the business interprets data consistently. In production systems, semantic failures generally fall into 10 domains: business definition alignment, financial reconciliation, policy versioning, operational state mapping, metric governance aggregation consistency, business expectation validation, semantic graph modeling, hierarchy versioning, and historical metric evolution. Mastering these domains enables engineers to build trusted data platforms where every dashboard, report, and model speaks the same business language.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition. Category 4 with semantic quality and business rules to Category 5 consistency and end-to-end reconciliation.
We are now pivoting from semantic definitions to system-wide harmony, moving directly into consistency and end-to-end reconciliation. A metric might be perfectly defined in the data warehouse, but if the downstream machine learning feature store, the executive BI extract, and the upstream CRM all display different values for the exact same record, business users will instantly lose trust. Mastering this shift requires moving beyond isolated pipeline checks and adopting a macro-level perspective, ensuring data state remains perfectly synchronized across highly distributed architectures.
Category 5 Overview. Designing for end-to-end consistency.
Top-tier tech interviewers evaluate your ability to trace data discrepancies across massively distributed multi-hop architectures. In Category 5, we will explore 10 high-frequency production scenarios covering master data management survivorship, caching mismatches, medallion layer row drops, replication lag, and training serving skew in ML models. Strong candidates must demonstrate how to combine hash-based reconciliation, event-driven state mapping, and strict referential integrity to guarantee that data remains identical no matter which system a user queries.
Category 5. Consistency and end-to-end reconciliation scenarios.
Here are the 10 production consistency scenarios we are going to solve in this category. Scenario 41. Customer names differ between CRM and ERP. Scenario 42. Order status differs across systems. Scenario 43. Bronze, silver, and gold layers contain different row counts. Scenario 44. Dashboard totals do not match gold tables. Scenario 45. ML feature store differs from analytical warehouse. Scenario 46. Foreign key relationships break after migration. Scenario 47. Golden customer records conflict across master systems. Scenario 48. Reference data refreshes weekly while facts refresh hourly. Scenario 49. Cross-region replication creates inconsistent reporting. Scenario 50. End-to-end reconciliation fails somewhere between source and dashboard. Let's deep dive into Scenario 41.
Scenario 41. The customer success team reports that a VIP client's name is spelled differently in the CRM than it is in the financial ERP system. The data warehouse ingests both, but the executive dashboards are displaying the incorrect legacy spelling. How do you resolve and prevent this master data management failure?
Answer. When the same entity displays conflicting attributes across different source systems, the issue is caused by a lack of master data management MDM integration and undefined survivorship rules in the warehouse. To isolate the root cause, establish a golden record, and enforce system consistency, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw bronze layer for both the CRM and ERP datasets to physically verify the differing name string values for the specific VIP customer ID. 2. Measure the total volume of customer profiles exhibiting naming discrepancies between the two systems to determine if this is an isolated typo or a systemic drift. 3. Check downstream gold tables to identify which upstream system the current warehouse pipeline is blindly prioritizing. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a cross-system consistency and master data management incident. Phase 2. Investigation root cause. 1. Inspect the silver layer dimensional modeling code to see if a simple coalesce function is arbitrarily choosing the CRM name over the ERP name based on column order. 2. Audit the operational systems to determine which application owns the actual legal billing entity versus the informal sales contact entity. 3. Review the timestamp metadata on both systems to see if an update in the ERP failed to propagate via reverse synchronization back to the CRM. By completing this investigation, you have isolated the root cause and determined whether the discrepancy was caused by naive coalesce logic, by directional sync failures, or undefined system of record rules. Phase 3. Targeted resolution. 1. Implement explicit survivorship rules in the warehouse transformation layer, explicitly designating the financial ERP as the trusted system of record for legal company names. 2. Reprocess the customer dimension table using the newly defined survivorship logic, overriding the incorrect legacy spelling with the verified ERP string. 3. Issue a data quality alert back to the CRM administration team, providing them a list of misaligned accounts to manually sync with the ERP. By completing these recovery steps, a single governed golden record has been reestablished, ensuring every downstream application references the same trusted customer identity. Phase 4. Long-term prevention. 1. Deploy a master data management engine that automatically evaluates conflicting source attributes and applies timestamp or confidence-based survivorship scoring. 2. Establish bi-directional synchronization pipelines that automatically push golden record corrections from the data warehouse back into the operational source systems. 3. Enforce cross-system parity tests that flag records where critical attributes like name or tax ID diverge across domains for more than 24 hours. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the transformation pipeline to implement explicit survivorship rules and builds the reverse synchronization feeds. 2. Data quality engineer defines the system of record logic with business stakeholders, builds the divergence alerts, and audits golden record accuracy. Pro tip: never use co-a-less with CRM_name, ERP_name to build a customer dimension. A simple co-a-less blindly trusts whichever system appears first in the function, completely ignoring the business reality of which system is the legal source of truth. Always define explicit, documented survivorship rules for every critical attribute.
Scenario 42. The logistics application marks an order as shipped, but the data warehouse and customer-facing portal still show the order as processing. The data pipeline is running continuously. How do you investigate, resolve, and prevent this state synchronization failure?
Answer: when operational state changes fail to propagate across distributed systems, the issue is typically caused by eventual consistency lag, asynchronous webhook failures, or out-of-order event delivery. To isolate the root cause, synchronize the distributed states, and enforce consistency, I follow a structured production response like Phase 1. Detection and validation. 1. Query the bronze layer ingestion tables to determine if the shipped webhook event physically arrived in the data platform, but was dropped during transformation. 2. Measure the exact replication lag timestamp delta between the logistics database commit time and the warehouse processing time. 3. Validate whether this state lag is affecting a specific geographic logistics center or impacting the entire global fulfillment network. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an eventual consistency and state synchronization incident. Phase 2. Investigation root cause. 1. Inspect the message broker dead letter queue to see if the shipped event was rejected by the ingestion layer due to a malformed schema payload. 2. Audit the streaming state store to check if out-of-order delivery caused a delayed processing event to overwrite the newer shipped event. 3. Review the logistics systems, API outbound logs to confirm if the webhook failed to fire entirely due to a transient network timeout. By completing this investigation, you have isolated the root cause and determined whether the state mismatch was caused by silent webhook drops, out-of-order event processing, or schema rejection. Phase 3. Targeted resolution. 1. If events were dropped due to network timeouts, trigger an operational replay of the missing webhook events from the logistics outbox table. 2. Reprocess the recovered events through the warehouse, utilizing strict event time ordering to guarantee the final state resolves correctly to shipped. 3. Verify state parity by running a direct API check against the logistics database for a random sample of the affected orders before notifying stakeholders. By completing these recovery steps, the distributed system states have been safely synchronized, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement the transactional outbox pattern on all operational databases to guarantee state changes are durably published to the message broker. 2. Enforce state machine logic in the silver layer that strictly rejects illegal state transitions, such as rejecting a processing event if the current state is already shipped. 3. Deploy active reconciliation scripts that periodically compare warehouse states directly against the logistics database, alerting on any discrepancies older than 15 minutes. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the state machine logic in the streaming pipeline, processes the webhook replay, and configures dead letter queues. 2. Data quality engineer. Defines illegal state transition rules, builds periodic cross-system reconciliation queries, and monitors replication lag SLAs. Pro tip: in highly distributed architectures, eventual consistency is a guarantee, not a bug. However, out-of-order events can permanently corrupt that consistency. You must build state machines in your transformation layer that no shipped always supersedes processing, ignoring the physical arrival time of the messages.
Scenario 43. A daily audit alert fires indicating that the bronze raw layer received 500,000 records, the silver cleansed layer output 495,000 records, and the gold aggregate layer used only 490,000 records. No explicit filters were intended. How do you trace and fix this multi-hop leakage?
Answer: when data silently drops between the hops of a medallion architecture, the issue is heavily tied to implicit inner joins, strict schema casting rejections, or aggressive deduplication rules. To isolate the root cause, identify the exact dropped rows, and plug the multi-layer leakage, I follow a structured production response like: Phase 1. Detection and validation. 1. Execute a left anti-join between the bronze and silver tables to perfectly isolate the 5,000 raw records that failed to promote. 2. Execute a second left anti-join between silver and gold to isolate the remaining 5,000 records that were dropped during final aggregation. 3. Profile the dropped records to identify shared characteristics, such as containing null foreign keys or malformed date strings. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a multi-hop pipeline leakage and consistency incident. Phase 2. Investigation root cause. 1. Inspect the bronze to silver transformation code to check if strict schema casting, for example, forcing a corrupted string into an int caused silent row drops. 2. Audit the silver to gold aggregation logic to determine if an implicit inner join on a dimension table excluded records with missing reference mappings. 3. Review the staging deduplication logic to verify if valid identical transactions were improperly flagged and dropped as duplicates. By completing this investigation, you have isolated the root cause and determined whether the leakage was caused by strict cast failures, unmapped inner joins, or over-aggressive deduplication. Phase 3. Targeted resolution. 1. Replace the strict schema casting with safe try_cast functions that replace invalid types with null rather than dropping the entire row. 2. Refactor the gold layer inner joins to left join, mapping unassigned dimension records to a default unknown category. 3. Reprocess the pipeline from bronze forward, ensuring the 10,000 previously dropped records successfully propagate to the gold layer. By completing these recovery steps, the missing records have been safely restored across all layers. Business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement the dead letter queue pattern between all medallion layers, automatically routing any rejected record to a quarantine table for investigation. 2. Embed cross-layer reconciliation assertions in DBT that mathematically guarantee bronze row counts equal gold row counts minus an explicitly logged quarantine list. 3. Standardize data engineering practices to completely ban implicit inner joins in analytical reporting models without explicit business approval. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the joins and casting logic, builds the quarantine routing framework, and orchestrates the multi-layer backfill. 2. Data quality engineer. Defines the cross-layer reconciliation rules, analyzes the quarantine records, and validates medallion parity. Pro tip: The left anti-join is the single most powerful tool in a data engineer's troubleshooting arsenal. When layer row counts diverge, do not guess. Immediately run select star from bronze left anti-join silver on the primary key to physically look at the exact rows that the pipeline dropped.
Scenario 44. The data engineering team validates that the gold table contains exactly $50 million in gross revenue. However, the Tableau dashboard viewed by the CEO displays $48 million. The warehouse is perfect, but the presentation layer is out of sync. How do you resolve this presentation consistency failure?
Answer: when the data warehouse is perfectly accurate but the BI dashboard displays divergent totals, the issue points to presentation layer extract caching, hidden dashboard level filters, or semantic layer compilation bugs. To isolate the root cause, synchronize the presentation layer, and enforce visual consistency, I follow a structured production response like Phase 1. Detection and validation. 1. Export the raw data directly from the BI tool's internal cache or workbook to compare it row by row against the live gold table in the warehouse. 2. Inspect the dashboard's visual filter panes and calculated field menus to check for hidden exclusions applied directly by the dashboard author. 3. Determine exactly when the dashboard was last physically refreshed versus when the gold table finished its last pipeline load. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a presentation layer caching and filtering incident. Phase 2. Investigation root cause. 1. Audit the BI tool's extract refresh schedule to verify if the server failed to pull the latest partition from the warehouse due to a connection timeout. 2. Review the custom SQL or semantic queries embedded in the dashboard connection to see if it utilizes an outdated table name or deprecated view. 3. Inspect user-level, row-level security RLS policies that might be silently filtering out regional data based on the service account executing the dashboard. By completing this investigation, you have isolated the root cause and determined whether the visual discrepancy was caused by stale BI extracts, hidden presentation filters, or row-level security mismatches. Phase 3. Targeted resolution. 1. Manually force a full extract refresh on the BI server, ensuring it completely synchronizes with the latest state of the gold table. 2. Remove any hidden dashboard-level filters, shifting the exclusion logic deep into the governed warehouse semantic layer. 3. Update the dashboard footer to dynamically display the last refreshed timestamp of both the BI extract and the underlying gold table. By completing these recovery steps, the presentation layer has been safely synchronized with the warehouse, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Transition critical executive dashboards from scheduled BI extracts to direct query or live connection modes against highly optimized warehouse views. 2. Implement pipeline orchestrator triggers that automatically ping the BI server API to refresh the extract the exact second the gold table finishes loading. 3. Establish automated visual UI testing like specific dashboard assertions that compare top-level BI metrics against warehouse APIs before sending morning reports. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role perspective and boundaries. 1. Data engineer configures the API triggers from the orchestrator to the BI tool, optimizes the live connection views, and manages RLS roles. 2. Data quality engineer audits the dashboard for hidden local filters, builds the visual UI reconciliation tests, and enforces semantic layer usage. Pro tip: the data pipeline does not end at the data warehouse, it ends at the CEO's eyeballs. If the warehouse is right but the dashboard extract is stale, you still failed. Always trigger your BI extract refreshes via API from your orchestration tool like Airflow, so the presentation layer updates the exact second the data is ready.
Scenario 45. A data scientist complains that a machine learning model's performance has degraded. You discover that the total historical spend feature calculated in the online feature store differs significantly from the same metric calculated in the analytical warehouse. How do you resolve this training serving skew?
Answer: when online feature stores diverge from offline analytical warehouses, the issue is called training serving skew, typically caused by differing calculation logic, delayed online streaming aggregations, or inconsistent point-in-time lookups. To isolate the root cause, synchronize the feature logic, and eliminate the skew, I follow a structured production response like Phase 1, Detection and Validation. 1. Query the offline historical analytical warehouse and the online fast key value feature store for a specific user ID to capture the exact numerical delta. 2. Validate whether the discrepancy exists on all historical records or is strictly isolated to events occurring within the last 24 hours. 3. Work with the ML team to quantify how much the feature skew is actively degrading the model's prediction accuracy in production. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a training serving feature skew incident. Phase 2. Investigation root cause. 1. Inspect the calculation code for the online streaming feature and compare it against the DBT SQL logic generating the offline batch feature. 2. Audit the online feature store's stream processing latency to verify if the metric is missing recent transactions that are already available in the batch warehouse. 3. Review how null values and default states are handled in both environments, checking if the online store defaults to 0 while the warehouse drops the row. By completing this investigation, you have isolated the root cause and determined whether the skew was caused by dual written logic, streaming lag, or inconsistent default value handling. Phase 3. Targeted resolution. 1. Refactor the logic so that both the streaming feature calculation and the batch calculation utilize the exact same underlying mathematical formula and null handling rules. 2. Execute a historical backfill from the verified offline analytical warehouse directly into the online feature store to completely overwrite and synchronize the corrupted features. 3. Trigger an offline model evaluation using the corrected feature set to confirm the model prediction accuracy returns to expected baselines. By completing these recovery steps, the online feature store and offline warehouse are mathematically aligned, restoring model prediction reliability. Phase 4. Long-term prevention. 1. Adopt a unified feature store architecture where a single declarative framework, for example, Feast or Databricks feature store, compiles both the batch and streaming calculation code. 2. Implement automated feature parity testing that continuously compares a random sample of online features against their offline equivalents, alerting on drift. 3. Enforce strict point-in-time correctness time travel in all offline training data generation to perfectly simulate the online serving state. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Unifies the stream and batch calculation logic, manages the unified feature store infrastructure, and executes the online synchronization backfill. 2. Data quality engineer. Builds the online-offline parity monitoring tests, validates point-in-time correctness, and audits model input distributions. Pro tip: training serving skew is the most silent and destructive data engineering failure in machine learning. If you maintain two separate codebases, one in Python for streaming and one in SQL for batch, they will inevitably drift and destroy your model. Always define your ML features in a single, unified framework that deploys to both environments.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 46. Following a major cloud migration, data models that rely on joining the orders table to the customer's table begin failing. You investigate and discover millions of orphan records in the orders table with customer IDs that no longer exist in the customer dimension. How do you resolve this referential integrity failure?
Answer. When massive volumes of orphan records appear immediately after a database migration, the issue is caused by incorrect data load sequencing, missing constraints on the target system, or corrupted incremental extraction logic. To isolate the root cause, restore referential integrity, and enforce migration load order, I follow a structured production response like Phase 1. Detection and validation. 1. Execute an explicit left anti-join on the migrated orders table against the customer's table to physically count the exact number of orphaned foreign keys. 2. Compare the orphaned ID list against the legacy on-premise database to confirm that the customer records do actually exist in the source system. 3. Validate whether the missing records are scattered randomly across history or isolated to a specific creation date window. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a referential integrity and migration consistency incident. Phase 2. Investigation root cause. 1. Inspect the migration orchestrator to verify if the orders fact table was loaded simultaneously or prior to the customer's dimension table. Breaking load sequencing. 2. Audit the cloud data warehouse schema to determine if foreign key constraints were intentionally disabled for performance but never re-enabled post-migration. 3. Review the extraction logs to check if the customer table extraction timed out or hit memory limits, resulting in a partial transfer. By completing this investigation, you have isolated the root cause and determined whether the orphan records were caused by out-of-order migration sequencing, disabled constraints, or partial extraction failures. Phase 3. Targeted resolution. 1. Re-extract and load the completely missing or partially failed customer dimension records from the legacy source system to the new cloud warehouse. 2. Execute a reconciliation query to mathematically confirm that the left anti-join now returns 0 orphan records. 3. Rerun the downstream analytical models that failed during the migration to ensure full reporting continuity is restored. By completing these recovery steps, referential integrity has been safely restored, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement strict DAG dependencies in the orchestrator that completely block fact table loads until all dependent dimension tables have successfully completed. 2. Enforce logical referential integrity tests, such as DBT relationships tests, that automatically fail the pipeline if orphaned foreign keys are detected. 3. Use automated table checksums between the legacy and cloud databases to guarantee one-to-one parity before officially cutting over production traffic. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer fixes the orchestrator load sequencing, re-extracts the missing dimension tables, and manages the migration parity checks. 2. Data quality engineer defines the referential integrity test suite, audits the migration logs, and verifies that 0 orphan records exist. Pro tip: modern cloud data warehouses like Snowflake or BigQuery often treat foreign key constraints as informational rather than enforcing them physically. This means the database will happily let you load orphan records. You must enforce referential integrity manually using CI/CD testing frameworks like DBT before you publish migrated data.
Scenario 47. Your company acquires a competitor and begins merging customer data. The identity resolution pipeline creates massive conflicts, linking two entirely different customers as the same golden record because they share the same common name and ZIP code. How do you resolve and prevent this probabilistic matching failure?
Answer: when identity resolution algorithms aggressively merge unique individuals into incorrect golden records, the issue is caused by overly loose probabilistic matching thresholds, missing deterministic identifiers, or cyclical graph logic. To isolate the root cause, split the corrupted records, and enforce strict identity matching, I follow a structured production response like Phase 1. Detection and validation. 1. Query the golden record cross-reference table to identify merged accounts exhibiting conflicting secondary attributes, for example, different phone numbers or birth dates. 2. Measure the total volume of merged identities created during the acquisition data load to determine the blast radius of the false positive matches. 3. Validate the downstream impacts to check if marketing communications or billing invoices were sent to the wrong physical individuals. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an identity resolution and golden record consistency incident. Phase 2. Investigation root cause. 1. Inspect the identity resolution matching rules to see if the algorithm relied solely on weak identifiers, first name plus last name plus ZIP, without requiring an exact email or phone match. 2. Audit the probabilistic matching engine like fuzzy string matching to determine if the confidence score threshold was lowered too far during the migration. 3. Review the source data from the acquired company to check for default or placeholder data, for example, all emails set to null at null.com that triggered massive false linkages. By completing this investigation, you have isolated the root cause and determined whether the false linkages were caused by weak matching logic, loose confidence thresholds, or placeholder source data. Phase 3. Targeted resolution. 1. Execute an unmerge operation in the golden record master table, reverting the improperly linked source identities back to their original distinct customer IDs. 2. Refactor the matching logic to mandate at least one deterministic hard identifier such as email, SSN, or phone number before authorizing a merge. 3. Reprocess the acquisition dataset through the corrected identity resolution engine and validate that the individuals remain distinctly separated. By completing these recovery steps, the incorrectly merged identities have been safely separated, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement a human-in-the-loop workflow for probabilistic matches that fall between 80% and 95% confidence, requiring manual data steward approval. 2. Deploy graph-based cycle detection to prevent multi-hop transitive matching. For example, A matches B, B matches C, therefore A is incorrectly merged with C. 3. Establish automated data quality profiling on acquired datasets to instantly flag placeholder data before it enters the identity resolution pipeline. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the identity resolution matching engine, builds the unmerged logic, and integrates graph cycle detection. 2. Data quality engineer. Profiles the acquired data for placeholders, tunes the probabilistic confidence thresholds, and manages the human-in-the-loop steward queue. Pro tip: first name, last name, and ZIP code do not uniquely identify a human being. There are hundreds of John Smiths in the same ZIP code. Never build an automated identity resolution system that relies solely on fuzzy string matching of names. You must demand deterministic anchors like phone numbers, emails, or device IDs.
Scenario 48. Your streaming pipeline ingests sales transactions hourly. However, the critical product mapping table from a third-party vendor only refreshes once a week. This temporal skew causes thousands of weekend transactions to silently drop because their new product IDs do not exist in the reference table yet. How do you resolve this?
Answer: when high-frequency fact pipelines join against low-frequency reference tables, the issue is caused by temporal refresh skew and a lack of late-arriving dimension handling. To isolate the root cause, rescue the dropped transactions, and gracefully handle orchestration boundaries, I follow a structured production response like Phase 1. Detection and validation. 1. Query the rejected records table or dead letter queue to isolate all hourly transactions that failed the product mapping join. 2. Cross-reference the missing product IDs against the operational source system to confirm they are indeed net new products created after the weekly refresh. 3. Measure the total revenue impact of the dropped weekend transactions to determine the severity of the reporting gap. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a temporal orchestration and reference alignment incident. Phase 2. Investigation root cause. 1. Inspect the silver layer join logic to confirm that an implicit inner join permanently drops facts with missing reference mappings rather than passing them through. 2. Audit the orchestration schedule to verify the exact temporal gap between the hourly fact streaming job and the weekly batch dimension job. 3. Review the vendor's API documentation to determine if an incremental, high-frequency endpoint exists for the reference data that was overlooked. By completing this investigation, you have isolated the root cause and determined whether the drops were caused by destructive inner joins, unoptimized vendor SLAs, or rigid batch orchestration. Phase 3. Targeted resolution. 1. Convert the strict inner join to a left join, allowing the new weekend transactions to flow into the gold layer assigned to a default pending mapping category. 2. Trigger an out-of-band manual refresh of the third-party reference table via API to immediately fetch the new product definitions. 3. Reprocess the pending mapping facts to correctly assign them to their newly loaded product hierarchies, restoring revenue attribution. By completing these recovery steps, the missing transactions have been safely mapped, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement late-arriving dimension logic that automatically inserts placeholder rows skeleton records into the dimension table whenever an unknown ID is encountered in the fact stream. 2. Negotiate a faster data transfer agreement with a third-party vendor to transition from weekly batch drops to daily incremental updates. 3. Build automated alerts that trigger if the percentage of pending mapping transactions exceeds 1% of overall hourly volume. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the pipeline to use left joins and skeleton records, automates the out-of-band refreshes, and negotiates vendor API patterns. 2. Data quality engineer monitors the volume of pending mapping records, validates the eventual consistency of the mappings, and tracks vendor delivery SLAs. Pro tip: fact tables and dimension tables almost never update at the exact same speed. If you use an inner join, you are guaranteeing that fast-moving facts will be deleted whenever they beat the dimension data to the warehouse. Always implement late-arriving dimension logic using left joins and skeleton records.
Scenario 49. Your global company uses an active-active database architecture. A user updates their profile in the Europe region, but a BI dashboard querying the US region shows the old profile data for several hours. The synchronization pipeline is failing silently. How do you resolve this cross-region replication failure?
Answer: when an active-active architecture surfaces different data depending on the query region, the issue is caused by replication lag, split brain scenarios, or misconfigured vector clocks. To isolate the root cause, resolve the replication conflict, and enforce global consistency, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the exact same user ID simultaneously against both the European and US read replicas to mathematically measure the state delta. 2. Inspect the record's transaction timestamps and vector clock metadata to identify exactly which region holds the absolute latest state. 3. Validate network telemetry to determine if the issue is a systemic replication queue backup or an isolated failure on a single data partition. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a cross-region replication and eventual consistency incident. Phase 2. Investigation root cause. 1. Inspect the replication agent logs to verify if a network partition severed the cross-continental link, causing changes to queue up in local memory. 2. Audit the conflict resolution rules, for example. Last write wins to see if concurrent updates in both regions cause the database to silently drop the European update. 3. Review the underlying cloud infrastructure like AWS Global Tables or Cosmos DB to check for service degradation or degraded cross-region bandwidth. By completing this investigation, you have isolated the root cause and determined whether the inconsistency was caused by network partitions, split-brain conflict resolution, or cloud infrastructure degradation. Phase 3. Targeted resolution. 1. If the network link is degraded, force a manual flush of the replication queue to push the queued European state changes into the US region. 2. If a conflict occurred, manually apply the correct business survivorship rule to update the US record with the latest European state. 3. Requery both regional databases to guarantee complete state parity. Before informing the analytics teams, they can safely refresh their dashboards. By completing these recovery steps, cross-region replicas have converged to a consistent state, eliminating stale reads across global analytics workloads. Phase 4. Long-term prevention. 1. Implement automated continuous replication monitoring that explicitly queries a heartbeat table in all regions, triggering SEV1 alerts if lag exceeds 5 minutes. 2. Route mission-critical analytical queries that require strict global consistency to a designated primary region, accepting higher latency to avoid dirty reads. 3. Enforce strict vector clock conflict resolution logic that deterministically merges simultaneous multi-region updates without silent data loss. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer investigates the replication agent logs, forces queue flushes, and tunes the conflict resolution algorithms. 2. Data quality engineer builds the multi-region heartbeat monitors, audits the consistency lag SLAs, and dictates analytical routing rules. Pro tip: the CAP theorem states you cannot have consistency, availability, and partition tolerance simultaneously. In a global active-active database, you are choosing availability over consistency. If your analytics require perfect real-time consistency, you must route those specific reads to a single master region, accepting the network latency.
Scenario 50. A highly sensitive financial pipeline moves data from the source DB to Kafka, to Databricks, to Snowflake, and finally to Tableau. The source has exactly $1 million, but Tableau shows $999,950. How do you find a $50 discrepancy hidden somewhere inside a massive 5-hop architecture?
Answer: when micro-variances appear across massive multi-hop architectures, the issue is impossible to find manually. The root cause is typically silent serialization drops, intermediate caching failures, or micro-batch edge cases. To isolate the root cause, trace the discrepancy, and enforce cryptographic multi-hop parity, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a macro-level reconciliation by checking the aggregate dollar sum at every single boundary. Source: Kafka topic, Databricks Delta table, Snowflake, and Tableau. 2. Identify the exact architectural hop where the $50 disappears. For example, source to Kafka is perfect, but Kafka to Databricks drops $50. 3. Validate whether the missing $50 represents a single large drop transaction or fractions of a cent lost across thousands of rows. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a multi-hop consistency, an end-to-end lineage incident. Phase 2. Investigation root cause. 1. If the gap is in Kafka to Databricks, inspect the stream consumer checkpointing to see if an off-by-one offset commit skipped a micro-batch. 2. If the gap is in Databricks to Snowflake, audit the copy into execution logs to verify if a badly formatted JSON file was shunted to a rejection table. 3. If the gap is in Snowflake to Tableau, review the extract refresh query to check if a specific time boundary excluded late arriving transactions. By completing this investigation, You have isolated the root cause and determined whether the microvariance was caused by offset skipping, serialization rejection, or boundary clipping. Phase 3. Targeted resolution. 1. Generate a cryptographic hash of all transaction IDs at the upstream layer and the downstream layer, using a minus query to find the exact missing record IDs. 2. Reprocess only the missing or rejected microbatch, ensuring the specific lost records successfully traverse the broken architectural hop. 3. Recalculate the macro-level sums across all 5 hops to mathematically prove the $1 million total is fully synchronized end-to-end. By completing these recovery steps, the microvariance has been safely resolved, business continuity has resumed, and downstream systems can reliably consume the corrected data. Phase 4. Long-term prevention. 1. Implement an automated control framework where every architectural hop emits a manifest file row count and sum that is continuously reconciled against the previous hop. 2. Embed data lineage tags using open lineage directly into the payloads to track the lifecycle of every transaction across distributed systems. 3. Deploy strict dead letter queues at every transition boundary, so no record can ever be dropped silently by any technology in the stack. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer implements cryptographic hash tracing, builds the multi-hop manifest framework, and repairs the specific failing connector. 2. Data quality engineer defines the end-to-end parity rules, builds the macro-level boundary alerts, and analyzes the dead letter queue drops. Pro tip: finding a needle in a haystack requires splitting the haystack in half. Never attempt to debug an end-to-end pipeline all at once. Always calculate the macro sum at every single boundary layer to instantly isolate which specific connection is dropping the data. Then use cryptographic hashing to find the exact missing rows.
Category 5. Conclusion and key takeaway. Consistency and end-to-end reconciliation.
In Category 5, we established that a perfectly accurate metric in the warehouse is useless if downstream and upstream systems disagree with it. We mastered tracing discrepancies across highly distributed environments, from resolving master data conflicts and streaming state lag to finding microvariances hidden deep within 5-hop architectures. Key takeaway: consistency is the ability to preserve one trusted version of data across every system that stores, transforms, or presents it. In production platforms, consistency depends on 7 core disciplines: master data governance, distributed state synchronization, cross-layer reconciliation, presentation parity, feature parity, referential integrity, and end-to-end lineage validation. Mastering these disciplines enables engineers to build data platforms where every application, dashboard, model, and service reports the same business truth.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition. Category 5, Consistency and End-to-End Reconciliation to Category 6, Data Freshness and SLA.
We are now pivoting from system agreement to system velocity, moving directly into data freshness and SLAs. It does not matter if your data is perfectly complete, deduplicated, mathematically accurate, and globally consistent if it arrives 3 hours too late for the business to make a decision. Mastering this shift requires moving beyond static data quality and entering the realm of operational execution, where time is the ultimate metric of success.
Category 6 Overview. Designing for Freshness.
Top-tier tech interviewers evaluate your ability to identify and eliminate temporal bottlenecks. In Category 6, we will explore 10 high-frequency production scenarios covering pipeline stalling, Kafka consumer lag, time zone scheduling drifts, streaming watermark drops, and macro-level SLA breaches. Strong candidates must demonstrate how to optimize critical paths, decouple heavy dependencies, and build resilient pipelines that guarantee data arrives exactly when the business expects it.
Category 6. Data Freshness and SLA Scenarios.
Here are the 10 production freshness scenarios we are going to solve in this category. Scenario 51. Dashboard still shows yesterday's numbers during business hours. Scenario 52. Hourly pipeline hasn't run for 6 hours. Scenario 53. Kafka consumer lag causes stale analytics. Scenario 54. Event timestamp differs significantly from processing timestamp. Scenario 55. Scheduler time zone mismatch delays production pipelines. Scenario 56. Downstream pipeline never starts after upstream completion. Scenario 57. Watermark configuration permanently drops late events. Scenario 58. Streaming dashboard remains 40 minutes behind. Scenario 59. Cloud function timeout interrupts ingestion. Scenario 60. Data SLA exceeds agreed business thresholds. Let's deep dive into Scenario 51.
Scenario 51. It is 10 a.m., and business users complain that their daily performance dashboard is still showing yesterday's numbers. You check the data warehouse, and the table's updated successfully at 6 a.m. The data is fresh, but the presentation is stale. How do you resolve this?
Answer: when the data warehouse is perfectly fresh but the presentation layer remains stale, the issue typically points to isolated BI extract caching, broken webhook triggers, or scheduled refresh timeouts. To isolate the root cause, synchronize the presentation layer, and eliminate silent caching failures, I follow a structured production response like Phase 1. Detection and validation. 1. Query the gold layer warehouse table directly to physically verify the exact timestamp of the most recent data load. 2. Open the BI dashboard in the browser and inspect the internal last refreshed metadata indicator to calculate the exact lag window. 3. Check the BI server's background task logs to determine if an automated extract refresh was attempted and failed this morning. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a BI layer freshness and extract caching incident. Phase 2. Investigation root cause. 1. Inspect the orchestrator to BI tool API integration to verify if the trigger pushing the refresh command failed silently without alerting the data team. 2. Audit the BI server capacity metrics to determine if the morning queue was overloaded, causing the refresh job to time out or sit in a pending state. 3. Review the underlying dashboard connection string to ensure someone didn't accidentally switch it from a live connection back to a scheduled extract. By completing this investigation, you have isolated the root cause and determined whether the stale presentation was caused by failed API triggers, BI server queue exhaustion, or connection type misconfigurations. Phase 3. Targeted resolution. 1. Manually force a high-priority extract refresh on the BI server to immediately pull the fresh 6 a.m. data into the dashboard. 2. If the BI server queue is deadlocked, restart the background task process to flush pending jobs and prioritize the executive dashboard extract. 3. Verify the newly updated dashboard visuals directly with the business users to confirm the figures now reflect current day reality. By completing these recovery steps, the executive dashboard has been safely refreshed with current day data, restoring executive visibility into today's business performance. Phase 4. Long-term prevention. 1. Decouple the BI extract schedule from static time-based cron jobs and strictly use event-driven API triggers initiated by the pipeline orchestrator. 2. Transition highly critical executive dashboards from cached extracts to direct query or live connection architectures to eliminate caching lag entirely. 3. Implement an observability check that queries the BI server API every morning at 8 a.m., firing a pager alert if the extract timestamp is older than 4 hours. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the orchestrator to trigger BI refreshes via API, manages the live connection views, and optimizes the warehouse query speed. 2. Data quality engineer builds the BI server API freshness monitors, validates the UI timestamps, and manages SLA expectations with business users. Pro tip: the pipeline is not done until the user can actually see the data. A frequent mistake data engineers make is declaring victory when the Snowflake table is loaded, ignoring the Tableau or Power BI refresh schedule. Always integrate your BI tool directly into your DAG so the dashboard refreshes the millisecond the warehouse finishes.
Scenario 52. A critical hourly pipeline that ingests operational data hasn't processed a new batch in over 6 hours. The orchestrator shows no failed tasks. The pipeline simply stopped scheduling new runs. How do you investigate and resolve this silent orchestration stall?
Answer: when an orchestrator silently stops scheduling an active pipeline without throwing explicit task failures, the root cause is usually a deadlock in concurrency limits, hung zombie processes, or frozen scheduler daemons. To isolate the root cause, unblock the queue, and safely process the 6-hour backlog, I follow a structured production response like Phase 1. Detection and Validation. 1. Review the orchestrator dashboard to confirm the exact timestamp of the last successful pipeline execution. 2. Inspect the task queue to check if the subsequent hourly runs are stuck in a queued, scheduled, or running state. 3. Validate downstream applications to measure the business impact of the 6-hour data void on operational decision-making. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an orchestration scheduling and pipeline execution freshness incident. Phase 2. Investigation root cause. 1. Inspect the orchestrator's concurrency limits such as maximum active DAG runs to see if a previous run hung indefinitely, blocking all future runs from starting. 2. Audit the underlying compute cluster or worker nodes to determine if resources were exhausted, leaving tasks perpetually waiting in the queue. 3. Review the scheduler daemon logs to verify if the orchestrator process itself crashed silently, halting the generation of new time-based triggers. By completing this investigation, you have isolated the root cause and determined whether the stall was caused by hung zombie tasks, worker node resource exhaustion, or a crash scheduler daemon. Phase 3. Targeted resolution. 1. Manually terminate the hung zombie tasks or deadlocked pipeline runs that were hoarding the concurrency slots. 2. Restart the orchestrator scheduler daemon if it was completely frozen, forcing it to re-evaluate the DAG directory and trigger missing runs. 3. Allow the orchestrator to sequentially process the 6-hour backlog catch-up, ensuring historical runs execute chronologically before resuming real-time processing. By completing these recovery steps, the stalled pipeline executions have safely caught up to real time, clearing the 6-hour backlog without overwhelming the compute cluster. Phase 4. Long-term prevention. 1. Implement strict task execution timeouts, for example, execution_timeout in Airflow to guarantee that hung network requests are automatically killed before they block the pipeline. 2. Configure DAG-level concurrency limits that allow a small backlog to process concurrently without exhausting the global worker pool. 3. Deploy meta orchestration alerts that query the metadata database, firing a critical page if the time since the last successful run exceeds 2 hours. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer configures task timeouts, tunes the orchestrator concurrency limits, and manually unblocks the stuck worker nodes. 2. Data quality engineer builds meta alerts to monitor pipeline execution frequency and validates data integrity after the heavy backlog is processed. Pro tip: orchestrators like Airflow will silently stop scheduling new jobs if the max_active_runs limit is reached. If a task hangs forever on a network request, it consumes that slot indefinitely. You must always enforce strict execution timeouts on every single task, ensuring hung jobs fail loudly rather than silently deadlocking your entire schedule.
Scenario 53. A real-time fraud detection dashboard is currently displaying events that occurred 45 minutes ago. The streaming pipeline is running, but the Kafka consumer is processing messages significantly slower than the producer is generating them. How do you resolve this consumer lag?
Answer: when a streaming consumer falls behind real-time event generation, the issue is caused by processing bottlenecks, insufficient consumer concurrency, or Sudden upstream volume spikes. To isolate the root cause, scale the streaming throughput, and eliminate the consumer lag, I follow a structured production response like Phase 1. Detection and validation. 1. Query the Kafka broker metrics to measure the exact consumer lag, the mathematical difference between the latest offset and the consumer's committed offset. 2. Compare the current incoming message volume against historical baselines to determine if the lag is caused by a massive producer spike or a slowed consumer. 3. Validate downstream applications to measure how this 45-minute latency degrades fraud prevention and business operational SLAs. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a stream ingestion and consumer lag freshness incident. Phase 2. Investigation root cause. 1. Inspect the stream processing logic to determine if a newly introduced heavy transformation, such as an external API lookup or complex regex, is bottlenecking the thread. 2. Audit the consumer group configuration to see if the number of active consumer instances is less than the total number of topic partitions. 3. Review the target sync database logs to verify if write throttling or connection pooling limits are causing backpressure on the Kafka consumer. By completing this investigation, you have isolated the root cause and determined whether the lag was caused by heavy thread transformations, insufficient partition concurrency, or downstream database backpressure. Phase 3. Targeted resolution. 1. Scale out the consumer group by adding more worker instances up to the maximum number of Kafka topic partitions to instantly increase parallel throughput. 2. If the target database is bottlenecking, increase the micro-batch size in the consumer to optimize network writes and reduce connection overhead. 3. Temporarily pause heavy non-critical transformations like external API lookups if necessary, allowing the consumer to drain the 45-minute backlog rapidly. By completing these recovery steps, consumer lag has been eliminated, real-time processing has been restored, and downstream analytics are once again operating within the defined freshness SLA. Phase 4. Long-term prevention. 1. Repartition the Kafka topic to a higher number of partitions, permanently increasing the maximum allowable concurrency for future consumer scaling. 2. Implement auto-scaling policies on the streaming infrastructure that automatically provision new worker nodes when consumer lag exceeds a 5-minute threshold. 3. Decouple heavy API lookups from the real-time ingestion stream, shifting enrichment to an asynchronous offline process whenever possible. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Increases consumer group concurrency, optimizes batch sync writes, and repartitions the topic for higher throughput. 2. Data quality engineer. Configures real-time offset lag monitoring, defines latency thresholds for the fraud team, and tracks stream velocity. Pro tip: in Kafka, your maximum concurrency is strictly bound by your partition count. If your topic has 4 partitions, you can only have 4 active consumers in a group. Adding a 5th consumer does absolutely nothing to reduce lag. Always over-partition your high-volume topics during initial design to give your consumers room to scale during traffic spikes.
Scenario 54. The marketing team analyzes an hourly ad click dashboard. They notice a massive spike in clicks logged at 3 p.m. However, you discover that the actual clicks occurred between 9 a.m. and 2 p.m. The pipeline just happened to ingest them all at 3 p.m. How do you resolve this temporal distortion?
Answer: when dashboards spike artificially due to delayed ingestion, the root cause is a fundamental pipeline design flaw where downstream models aggregate by processing time rather than the actual event generation time. To isolate the root cause, realign the temporal boundaries, and restore chronological accuracy, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw bronze layer payload to extract the actual timestamp embedded in the add click event by the source client device. 2. Compare the client event timestamp against the database insertion timestamp to mathematically measure the delayed ingestion window. 3. Check downstream models to identify if this temporal distortion affects hourly aggregations, daily boundary cutoffs, or real-time alerting logic. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an event time versus processing time latency incident. Phase 2. Investigation root cause. 1. Inspect the silver layer SQL aggregation logic to verify if the group by clause incorrectly utilizes the metadata ingestion timestamp column. 2. Audit the upstream data collection API to determine why mobile devices or web clients batched 5 hours of data before transmitting it at 3 p.m. 3. Review the windowing functions in the streaming architecture to ensure they are configured to handle delayed records safely. By completing this investigation, you have isolated the root cause and determined whether the distortion was caused by processing time aggregations, client-side batching, or improper windowing logic. Phase 3. Targeted resolution. 1. Refactor the downstream aggregation queries to strictly use the client-side event timestamp rather than the warehouse processing timestamp. 2. Backfill and regenerate the affected historical partitions to retroactively distribute the massive 3 p.m. spike back to the correct hours of 9 a.m. to 2 p.m. 3. Validate the newly distributed hourly aggregates against the marketing team's campaign logs to ensure temporal accuracy is restored. By completing these recovery steps, the temporal offset has been safely reconciled, ensuring downstream models reflect the true generation time of the events rather than their delayed arrival. Phase 4. Long-term prevention. 1. Enforce strict data modeling standards requiring all fact tables to explicitly split timestamps into 2 separate columns, event_time and processed_time. 2. Deploy semantic layer linting tools that flag and reject any analytical rollup or BI chart that attempts to group business logic by processed_time. 3. Implement watermark logic that gracefully accepts late arriving data, updating historical event time partitions without throwing out of order exceptions. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Refactors the SQL aggregations to use event time, implements late arriving watermark logic, and executes the hourly backfill. 2. Data quality engineer. Audits the semantic layer for illegal processing time usage and builds drift alerts to track massive ingestion delays. Pro tip: event time is when the action physically happened in the real world. Processing time is when your server finally noticed it. If a mobile user loses cell service and their phone uploads 50 clicks 3 hours later, aggregating by processing time makes it look like a massive usage spike. Always group business analytics by event time.
Scenario 55. Daylight saving time just began. Suddenly, all of your critical daily data pipelines run exactly 1 hour late, breaching SLAs and leaving morning dashboards empty for the European business teams. How do you resolve and prevent this time zone offset failure?
Answer: when pipeline schedules drift abruptly by 1 hour, the issue is exclusively caused by orchestrators or database schedulers running on local time zones that observe daylight saving shifts, rather than strict UTC. To isolate the root cause, realign the schedules, and eliminate future daylight saving bugs, I follow a structured production response like Phase 1. Detection and validation. 1. Review the orchestrator run history to confirm the exact execution. Start time drifted by exactly 60 minutes compared to the previous day. 2. Validate which specific regional dashboards and downstream dependencies missed their business SLA cutoffs due to the 1 hour delay. 3. Check the server system clocks for the orchestration nodes to physically verify their current time zone configuration. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a temporal orchestration and time zone offset freshness incident. Phase 2. Investigation root cause. 1. Inspect the cron expressions inside the DAG definitions to verify if they were hard-coded to a local time zone, for example, America or New_York rather than UTC. 2. Audit the orchestrator server configuration file to check if the default global time zone was incorrectly configured to observe local daylight saving shifts. 3. Review the underlying server operating system settings to see if the Linux Crony or NTP service applied an unexpected time boundary shift. By completing this investigation, you have isolated the root cause and determined whether the drift was caused by local DAG cron expressions, incorrect orchestrator defaults, or OS-level time zone misconfigurations. Phase 3. Targeted resolution. 1. Immediately manually trigger the delayed DAGs to process the data and populate the empty morning dashboards for the European teams. 2. Refactor the orchestrator cron expressions and configuration files to execute strictly on the UTC time zone schedule. 3. If explicit local execution times are required by business contracts, utilize time zone-aware cron logic natively supported by modern orchestrators to handle the shift gracefully. By completing these recovery steps, pipeline schedules are fully synchronized with the intended execution windows, ensuring future daylight-saving transitions no longer impact business reporting. Phase 4. Long-term prevention. 1. Standardize all infrastructure, databases, compute clusters, orchestrators, and file servers strictly on UTC, banning local time zone usage on backend systems. 2. Implement CI/CD linting rules that explicitly block any orchestration code containing hard-coded local time zone definitions. 3. Execute boundary testing in staging environments, specifically simulating daylight-saving time roll forwards and rollbacks to prove pipeline stability. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role perspective and boundaries. 1. Data engineer. Standardizes the orchestrator cluster to UTC, refactors the DAG cron expressions, and manually triggers the delayed runs. 2. Data quality engineer. Defines the CI/CD time zone linting rules, audits the regional SLA impacts, and designs the daylight-saving boundary tests. Pro tip: if your orchestration server is set to a local time zone like EST, your pipelines will break twice a year during daylight-saving transitions. You will either run the pipeline twice in one night or miss an hour entirely. Set absolutely every backend server to UTC. If a business user wants a report at 9 a.m. local time, calculate that offset specifically for that single job.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 56. The raw data ingestion pipeline DAG-A successfully completes at 2 a.m. However, the transformation pipeline DAG-B that builds the gold tables never triggers. It sits indefinitely in a waiting state, causing severe freshness delays. How do you resolve this cross-pipeline dependency failure?
Answer: when downstream pipelines fail to trigger after upstream success, the root cause is almost always broken external task sensors, misconfigured event-driven triggers, or decoupled state boundaries. To isolate the root cause, manually unblock the data flow, and ensure reliable execution handoffs, I follow a structured production response like Phase 1. Detection and validation. 1. Review the orchestrator dashboard to physically verify that DAG-A reached a final, committed success state without skipped tasks. 2. Inspect the execution state of DAG-B to check if its sensor task is perpetually running, timed out, or never queued in the first place. 3. Validate downstream applications to calculate the exact SLA breach duration caused by the stalled transformation pipeline. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a cross-DAG dependency and sensor synchronization incident. Phase 2. Investigation root cause. 1. Inspect the external task sensor in DAG-B to check if it is polling for an exact execution timestamp from DAG-A that misaligned by a few seconds. 2. Audit the event-driven webhook configuration to determine if DAG-A successfully fired the API call required to trigger DAG-B, or if a network partition dropped the request. 3. Review the underlying dataset-driven scheduling logic to see if DAG-A updated a specific partition, but DAG-B was configured to watch a different file path. By completing this investigation, you have isolated the root cause and determined whether the stall was caused by strict execution date mismatches, dropped API triggers, or incorrect dataset polling. Phase 3. Targeted resolution. 1. Manually trigger DAG-B to immediately begin processing the available raw data and clear the freshness backlog. 2. Refactor the sensor in DAG-B to tolerate execution date variances, or switch the dependency mechanism to an explicit dataset update trigger. 3. Verify the final gold table outputs to ensure the delayed transformation did not miss any late-arriving bronze data during the manual trigger window. By completing these recovery steps, the decoupled pipeline dependencies have been safely repaired, ensuring downstream transformations immediately trigger the moment upstream extractions complete. Phase 4. Long-term prevention. 1. Migrate away from fragile time-based external task sensors and adopt native dataset-driven scheduling, where pipelines trigger automatically when specific tables are updated. 2. Implement cross-pipeline SLA monitors that alert the data team if a downstream DAG fails to start within 15 minutes of its upstream dependency completing. 3. Enforce strict sensor timeouts that force a loud failure and pager alert rather than allowing a task to poll silently for 24 hours. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Transitions the orchestrator from time sensors to dataset-driven scheduling, manually triggers the stalled pipeline and configures task timeouts. 2. Data quality engineer. Builds the cross-DAG freshness monitors, validates SLA compliance, and audits the transformation output after the delayed run. Pro tip: using time-based external task sensors to link two pipelines together is extremely fragile. If DAG-A takes 5 seconds longer to run today than it did yesterday, DAG-B sensor might miss the exact timestamp match and wait forever. Always decouple pipelines using event-driven or dataset-driven triggers based on physical table updates.
Scenario 57. Your streaming pipeline calculates active user counts every 5 minutes. The pipeline is running perfectly on time, but millions of mobile app events from offline users are permanently dropped by the pipeline when their phones reconnect an hour later. How do you resolve this watermark exclusion?
Answer: when a streaming pipeline permanently drops late-arriving data, the issue is caused by overly aggressive state watermarks that discard records outside a rigid temporal window. To isolate the root cause, rescue the dropped events, and optimize the watermark boundaries, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the streaming pipeline's dropped records metric or dead letter queue to quantify the exact volume of events rejected due to late arrival. 2. Compare the event timestamp against the stream processing timestamp to calculate the maximum temporal delay exhibited by the mobile clients. 3. Validate downstream active user dashboards to mathematically measure the severity of the undercounting caused by the dropped events. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a streaming state window and watermark exclusion incident. Phase 2. Investigation root cause. 1. Inspect the stream processing engine configuration such as Spark structured streaming to identify the exact allowed lateness threshold defined in the watermark. 2. Audit the mobile app telemetry to determine why client devices are buffering events for over an hour before transmitting them to the server. 3. Review the downstream database sync to verify if it is capable of handling historical upserts, or if the pipeline drops late events simply because the sync only supports append operations. By completing this investigation, you have isolated the root cause and determined whether the exclusion was caused by aggressive watermark thresholds, long client-side buffering, or rigid target syncs. Phase 3. Targeted resolution. 1. Recover the dropped events from the raw landing zone or dead letter queue and execute a batch backfill to merge them into the historical active user aggregates. 2. Relax the watermark delay threshold in the streaming application, for example, from 5 minutes to 2 hours to accommodate the reality of mobile network latency. 3. Update the streaming sync logic to output records in update or append mode dynamically, ensuring late records can successfully recalculate past time windows. By completing these recovery steps, the dropped late events have been safely recovered into the warehouse, ensuring historical accuracy while maintaining real-time stream performance. Phase 4. Long-term prevention. 1. Implement a lambda or kappa architecture, where a nightly batch job automatically sweeps the raw storage layer to recalculate and correct any aggregates missed by the real-time stream. 2. Configure specific observability alerts that trigger if the percentage of late dropped records exceeds 1% of overall streaming volume. 3. Decouple real-time operational alerting, which needs strict short watermarks from historical analytical reporting, which requires long, lenient watermarks into separate pipelines. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer expands the watermark threshold, refactors the sync to support updates, and builds the nightly batch reconciliation sweep. 2. Data quality engineer monitors the volume of dropped late records, measures the maximum event latency, and validates the backfilled aggregates. Pro tip: a watermark is a compromise between state memory and data completeness. If your watermark is 5 minutes, you keep memory costs low, but you permanently lose any data delayed by a subway tunnel or bad cell service. Always tune your watermark to the real-world latency of your devices and use a nightly batch sweep to catch the extreme outliers.
Scenario 58. A critical operational dashboard is designed to provide sub-minute latency for supply chain monitoring. However, throughout the day, the dashboard gradually falls further behind, eventually stabilizing at a permanent 40-minute delay. How do you troubleshoot and resolve this creeping stream latency?
Answer: when a streaming pipeline gradually loses velocity and falls behind real time, the issue is typically caused by micro-batch processing times exceeding their designated intervals, downstream sync throttling, or complex stateful joins bottlenecking the cluster. To isolate the root cause, unblock the stream, and restore sub-minute latency, I follow a structured production response like Phase 1. Detection and validation. 1. Monitor the streaming engine metrics to compare the actual micro-batch processing duration against the configured trigger interval. 2. Query the target database to verify the timestamp of the latest committed transaction compared to the current system clock. 3. Validate whether the creeping latency is correlated with a sudden spike in incoming payload volume from the upstream producers. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a micro-batch processing and stream throughput freshness incident. Phase 2. Investigation root cause. 1. Inspect the stream transformation logic to determine if a stateful operation like a sliding window aggregate or stream-to-stream join is hoarding cluster memory. 2. Audit the target sync, for example, Snowflake or Postgres, to see if write API rate limits or connection pooling exhaustion are forcing the stream to wait during commits. 3. Review the garbage collection logs of the streaming worker nodes to verify if memory pressure is causing the JVM to freeze constantly. By completing this investigation, you have isolated the root cause and determined whether the creeping lag was caused by stateful memory exhaustion, downstream sync throttling, or insufficient compute scaling. Phase 3. Targeted resolution. 1. Optimize the downstream sync by increasing batch commit sizes or provisioning higher connection limits to eliminate database backpressure. 2. Horizontally scale the streaming cluster by adding more worker nodes and increasing the topic partitions to distribute the heavy stateful processing load. 3. If the 40-minute lag is critical, temporarily restart the streaming application with a massively increased compute allocation to rapidly drain the queued backlog. By completing these recovery steps, stream processing throughput now exceeds the incoming event rate, allowing the streaming application to maintain sustained near real-time performance. Phase 4 Long-Term Prevention 1. Implement auto-scaling policies on the streaming infrastructure that dynamically add compute nodes the moment micro-batch duration exceeds 80% of the trigger interval. 2. Enforce strict state cleanup rules by applying short TTL's time to live on windowed aggregates to prevent the state store from growing infinitely. 3. Set up critical paging alerts based explicitly on processing time versus event time drift, ensuring engineers are notified before the lag reaches 5 minutes. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer optimizes the micro-batch sync writes, provisions higher compute resources, and tunes the state store TTL rules. 2. Data quality engineer defines the sub-minute SLA thresholds, monitors the event time drift, and validates dashboard freshness. Pro tip: if your streaming micro-batch interval is set to 10 seconds, but your transformation takes 12 seconds to run, your pipeline will fall behind by 2 seconds every single batch. This is the cause of creeping latency. Always monitor your micro-batch processing duration. It must strictly remain below your trigger interval to achieve true real-time freshness.
Scenario 59. A serverless cloud function like AWS Lambda extracts data from a vendor API every hour. Over the holidays, transaction volume doubled. Now, the pipeline constantly fails because the cloud function hits its hard 15-minute execution timeout before finishing the extraction. How do you resolve this?
Answer: when a serverless ingestion pipeline abruptly fails due to hard execution timeouts, the issue points to unpaginated monolithic extractions, lack of parallel processing, or sudden payload volume spikes breaching compute limits. To isolate the root cause, redesign the extraction flow, and bypass the timeout limits, I follow a structured production response like Phase 1. Detection and validation. 1. Review the serverless execution logs to physically confirm the task timed out after 900 seconds error message. 2. Query the bronze landing zone to determine if the function successfully wrote partial data before crashing, or if the entire batch was lost. 3. Compare the API payload volume from this week against historical averages to mathematically confirm the exact magnitude of the traffic spike. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a serverless compute boundary and ingestion timeout incident. Phase 2. Investigation root cause. 1. Inspect the Python extraction code to check if it attempts to download, transform, and upload the entire payload in a single monolithic thread. 2. Audit the vendor API latency to determine if the timeout was actually caused by the third-party server taking too long to respond, rather than raw data volume. 3. Review the orchestrator setup to verify if the timeout boundary was set artificially low within the DAG itself, or if it hit the absolute cloud provider ceiling. By completing this investigation, you have isolated the root cause and determined whether the timeout was caused by monolithic single-threaded processing, vendor API latency, or absolute cloud limits. Phase 3. Targeted resolution. 1. Temporarily transition the extraction task from a serverless function to a dedicated compute instance like a container without hard time limits to immediately clear the backlog. 2. If partial data was written before the crash, purge the incomplete files from the bronze layer to ensure the re-extraction does not duplicate records. 3. Manually slice the time window into smaller chunks, for example, pulling data in 15-minute intervals instead of hourly, and execute them sequentially. By completing these recovery steps, the serverless extraction has been safely paginated, allowing the ingestion framework to reliably process heavy payloads without breaching timeout limits. Phase 4. Long-term prevention. 1. Refactor the monolithic cloud function using a scatter-gather pattern. One function fetches pagination tokens and distributes those tokens to dozens of parallel worker functions. 2. Decouple the extraction and transformation steps. The cloud function should solely dump raw JSON files to storage, leaving heavy parsing to the data warehouse. 3. Monitor API extraction durations directly within the orchestrator, triggering warnings when task runtimes approach 80% of the maximum cloud timeout limit. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the monolithic script into a distributed scatter-gather pattern, manages the temporary container migration, and decouples transformation. 2. Data quality engineer validates the completeness of the chunked extractions and sets duration alerts for the new parallel workers. Pro tip: serverless functions like AWS Lambda are amazing for event-driven triggers, but they are terrible for monolithic ETL extractions because of their strict time limits. If you must use serverless for heavy ingestion, you have to write your code to retrieve pagination tokens first, and fan out the actual data downloading to multiple concurrent functions.
Scenario 60. The business agreed on a strict 7 a.m. SLA for the daily executive reporting suite. However, over the last 3 months, the pipeline completion time has crept from 6:30 a.m. to 7:45 a.m. Nothing is failing, but the pipeline is simply taking too long to run. How do you resolve this macro-level SLA breach?
Answer: when pipelines suffer from creeping macro-level latency without explicit task failures, the root cause is usually exponential data volume growth, serial dependency bottlenecks, or unoptimized full table scans. To isolate the root cause, optimize the critical path, and restore SLA compliance, I follow a structured production response like Phase 1. Detection and validation. 1. Extract the historical orchestrator runtimes over the last 90 days to mathematically graph the creeping latency curve. 2. Generate a Gantt chart of the pipeline DAG execution to identify exactly which specific transformation models or extraction jobs are on the critical path. 3. Measure the daily data volume ingested from the source systems to confirm if the processing slowdown directly correlates with organic business data growth. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an enterprise SLA breach and critical path degradation incident. Phase 2. Investigation root cause. 1. Inspect the longest-running SQL transformations to check if they use full table overrides scanning 5 years of history daily instead of efficient incremental builds. 2. Audit the orchestrator dependencies to determine if independent tasks are running serially when they could safely run in parallel. 3. Review warehouse compute sizing to verify if the cluster is experiencing severe query queuing or disk spilling due to insufficient memory allocation. By completing this investigation, you have isolated the root cause and determined whether the SLA breach was caused by full table scans, serial orchestrator bottlenecks, or under-provisioned compute clusters. Phase 3. Targeted resolution. 1. Immediately scale up the warehouse compute cluster, for example, moving from a medium to a large warehouse in Snowflake to forcefully buy back execution time. 2. Refactor the bottleneck transformation models from full table overwrites into incremental materializations, processing only the last 24 hours of data. 3. Reconfigure the DAG dependencies to parallelize all non-dependent extraction and transformation tasks, shortening the absolute length of the critical path. By completing these recovery steps, the critical execution path has been optimized, restoring pipeline completion times within the agreed enterprise SLA while preserving scalability for future data growth. Phase 4. Long-term prevention. 1. Implement pipeline profiling tools that automatically alert engineering when a specific DBT model or Airflow task increases its runtime by more than 10% week over week. 2. Establish strict architectural guidelines, mandating that any dataset over 10 million rows must utilize incremental loading strategies. 3. Decouple non-critical operational datasets from the morning executive reporting pipeline, ensuring the 7 a.m. SLA is reserved only for top-tier business metrics. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the SQL transformations to incremental logic, parallelizes the DAG dependencies, and tunes warehouse compute sizing. 2. Data quality engineer defines the business SLA boundaries, monitors macro-level pipeline duration trends, and profiles slow-running queries. Pro tip: the critical path is the longest sequence of dependent tasks in your pipeline. If a job is not on the critical path, optimizing it by 10 minutes will not speed up your pipeline by a single second. Always generate a Gantt chart of your DAG to find the exact bottleneck before you start rewriting SQL or paying for larger compute clusters.
Category 6 Conclusion and Key Takeaway: Data Freshness and SLA.
In Category 6, we established that perfectly accurate data is entirely useless if it arrives after the business decision has already been made. We mastered systematic investigation techniques across 10 freshness failure modes, ranging from hidden BI extract caching and time zone drift to streaming consumer lag and critical path bottlenecks. Key takeaway: freshness is the discipline of delivering trustworthy data within the time required for business decisions. In production platforms, freshness depends on 8 core disciplines: presentation refresh, orchestration reliability, streaming throughput, event time correctness, time synchronization, dependency orchestration, late event handling, and critical path optimization. Mastering these disciplines ensures that accurate data is not only correct, but also available exactly when the business needs it.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition. Category 6 Data Freshness and SLA to Category 7 Schema Evolution and Data Contracts.
We are now pivoting from temporal delivery to structural integrity, moving directly into schema evolution and data contracts. A pipeline can execute flawlessly on time, but if the upstream software engineering team renames a column or changes an integer to a string, the downstream analytics will crash instantly. Mastering this shift requires moving beyond reactive data engineering and adopting a software engineering mindset, treating data pipelines like strict APIs governed by explicit contracts.
Category 7 Overview. Designing for Schema Evolution.
Top-tier tech interviewers evaluate your ability to protect the warehouse from upstream chaos. In Category 7, we will explore 10 high-frequency production scenarios covering silent column renames, data type coercion, unannounced JSON expansions, Avro registry incompatibilities, and the implementation of strict data contracts. Strong candidates must demonstrate how to decouple producers from consumers, implement shift-left CI/CD testing, and utilize dead letter queues to route bad data safely without crashing the critical path.
Category 7. Schema Evolution and Data Contract Scenarios.
Here are the 10 production schema scenarios we are going to solve in this category. Scenario 61. Source team renames a column without notice. Scenario 62. Column data type changes from int to string. Scenario 63. Nested JSON adds unexpected fields. Scenario 64. CSV files suddenly contain additional columns. Scenario 65. Avro schema compatibility breaks downstream consumers. Scenario 66. Delta Lake schema enforcement blocks ingestion. Scenario 67. Producer releases a breaking data contract version. Scenario 68. Contract testing catches schema violations during CI/CD. Scenario 69. Consumer application crashes after unexpected producer changes. Scenario 70. Invalid contract changes trigger quarantine versus fail fast decisions. Let's deep dive into Scenario 61.
Scenario 61. The nightly ingestion job crashes because the upstream software engineering team renamed the user_account_status column to account_state in the source database without telling anyone. Downstream models are broken. How do you resolve and prevent this silent schema drift?
Answer: when an unannounced column rename breaks a downstream pipeline, the issue is caused by brittle extraction queries. tight coupling between systems, and a lack of organizational change management. To isolate the root cause, restore the pipeline, and decouple the schema dependencies, I follow a structured production response like Phase 1. Detection and Validation. 1. Review the orchestrator execution logs to physically identify the specific column not found exception and isolate the exact missing column name. 2. Query the upstream source database schema directly using information_schema to visually confirm the new column structure and verify the rename. 3. Check downstream BI tools and analytical models to determine exactly which critical executive dashboards are currently offline due to this extraction failure. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a schema column drift incident. Phase 2. Investigation root cause. 1. Inspect the extraction SQL to verify if the pipeline was explicitly selecting column names or dangerously relying on a generic select star statement. 2. Audit the upstream application repository commits to trace exactly when the software engineering team deployed the database migration. 3. Review the bronze to silver transformation logic to determine how deeply the old column name is embedded across downstream DBT models. By completing this investigation, you have isolated the root cause and determined whether the failure was caused by select star queries, unannounced upstream deployments, or rigid transformation models. Phase 3. Targeted resolution. 1. Update the extraction script to alias the new source column back to the legacy column name. For example, select account_state as user_account_status to instantly restore downstream compatibility. 2. Clear the failed task state in the orchestrator and manually re-trigger the ingestion job to process the backlog data. 3. Execute a targeted validation query in the gold layer to mathematically confirm the status field is populating correctly before notifying the business. By completing these recovery steps, the renamed column has been successfully mapped, downstream references have been updated, and analytical continuity is fully restored. Phase 4. Long-term prevention. 1. Establish strict data contracts that programmatically bind the producer to a specific schema, requiring them to support both V1 and V2 columns simultaneously during a deprecation period. 2. Implement schema drift detection in the extraction layer that dynamically alerts the team of column additions or renames before attempting to load data. 3. Ban the use of select star in production extraction pipelines, enforcing explicit column definitions in all ingestion queries. By implementing these preventive controls, future column renames will be detected before deployment, allowing downstream systems to remain backward compatible during schema transitions. Role, perspective, and boundaries. 1. Data engineer refactors the SQL query to implement the column alias, clears the orchestrator backlog, and builds the schema drift detection logic. 2. Data quality engineer defines the data contract with the upstream software team and validates that downstream models continue to interpret the statuses correctly. Pro tip: never use select star in an ingestion pipeline. If the upstream team adds, removes, or renames a column, your pipeline will either crash or silently load garbage data. Always explicitly declare the columns you are extracting. If a column name changes upstream, use SQL aliasing in the extraction layer to shield your downstream models from the chaos.
Scenario 62. An upstream application suddenly starts sending zip codes as alphanumeric strings, for example, 1000 apt instead of standard integers. The ingestion pipeline crashes with a data type mismatch error, halting all geographic analytics. How do you resolve and prevent this type coercion failure?
Answer: when numeric fields silently mutate into strings, the root cause is usually a lack of API schema validation, uncoordinated upstream feature releases, or rigid downstream table definitions. To isolate the root cause, safely coerce the data types, and prevent future type mismatches, I follow a structured production response like Phase 1. Detection and validation. 1. Review the data warehouse load logs to isolate the exact batch of records that threw the invalid type or numeric value out of range exception. 2. Query the raw extraction payload to visually inspect the new alphanumeric strings and determine the scale of the formatting change. 3. Validate which downstream geographic models and marketing dashboards are currently blocked by this extraction failure. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a data type coercion and schema mutation incident. Phase 2. Investigation root cause. 1. Inspect the target database table DDL to confirm if the zip code column was rigidly defined as an integer rather than a more flexible varchar. 2. Audit the upstream producer's release notes to determine if they intentionally launched a global feature supporting international postal codes. 3. Review the bronze to silver casting logic to see if it relies on implicit casting rather than safe, explicit error handling. By completing this investigation, you have isolated the root cause and determined whether the mismatch was caused by rigid target DDL, global feature expansions, or unsafe casting logic. Phase 3. Targeted resolution. 1. Execute an alter table command on the target warehouse table to safely widen the column data type from integer to varchar to accept the new alphanumeric format. 2. Refactor the ingestion SQL to safely cast incoming values to strings, ensuring legacy integer records are seamlessly converted to text. 3. Reprocess the failed ingestion batch and verify that the new international postal codes populate correctly in downstream geographic models. By completing these recovery steps, the corrupted string values have been safely accepted, historical aggregates remain logically consistent, and the pipeline continues processing without data loss. Phase 4. Long-term prevention. 1. Implement safe casting functions such as cast that route unparsable data types to a dead letter queue rather than crashing the entire pipeline. 2. Standardize schema design principles that mandate storing categorical identifiers like zip codes, phone numbers, and SSNs exclusively as strings. 3. Deploy schema registry validation on the API gateway that explicitly rejects producer payloads if they violate the agreed-upon data type contracts. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer executes the alter table command, updates the casting logic in the transformation layer, and implements the cast routing. 2. Data quality engineer redefines the zip code validation rules, audits the dead letter queue for dropped records, and updates the data catalog. Pro tip: never store categorical identifiers as numbers. Zip codes, phone numbers, employee IDs, and bank account numbers should always be stored as strings. You do not perform math on a zip code. Storing them as integers guarantees leading zeros will be silently deleted, and international formats will crash your pipeline.
Scenario 63. Your pipeline extracts a massive nested JSON payload from a NoSQL database. Suddenly, the upstream team injects an entirely new nested array into the payload. The pipeline does not crash, but the new data is completely ignored by downstream models. How do you resolve this?
Answer: when pipelines silently ignore newly added JSON fields, the issue stems from rigid schema on read parsing, hard-coded struct definitions, or missing schema evolution configurations. To isolate the root cause, capture the new arrays, and enable dynamic schema expansion, I follow a structured production response like Phase 1. Detection and validation. 1. Query the raw bronze layer variant column to physically inspect the raw JSON payload and confirm the presence of the new nested array. 2. Compare the raw payload against the parse silver layer table to prove mathematically that the new fields are being silently dropped during unnesting. 3. Consult with business stakeholders to determine if the new nested array contains critical metrics required for immediate executive reporting. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a semi-structured payload and schema expansion incident. Phase 2. Investigation root cause. 1. Inspect the JSON parsing SQL like JSON_extract or lateral flattening to verify if the extraction logic strictly names legacy paths and ignores wildcard dynamic paths. 2. Audit the target table configuration to determine if features like Delta Lake's merge schema are disabled, preventing the table from dynamically adding new columns. 3. Review the data catalog to see if a schema registry was bypassed, allowing the producer to mutate the document structure without alerting the warehouse. By completing this investigation, you have isolated the root cause and determined whether the silent drop was caused by rigid parsing paths, disabled schema evolution, or unmanaged schema on read logic. Phase 3. Targeted resolution. 1. Refactor the extraction SQL to explicitly unnest the newly discovered array and map it to a structured column in the silver layer. 2. If using a modern lakehouse format, enable automated schema evolution. For example, merge schema equals true for the specific table to safely accept the new columns. 3. Backfill the silver layer by reprocessing the raw bronze payloads, ensuring historical records are populated with the newly unnested data. By completing these recovery steps, the pipeline now dynamically parses the nested payload, preserving the new fields without dropping existing structural data. Phase 4. Long-term prevention. 1. Always store the complete, unparsed JSON payload in a raw variant column in the bronze layer, ensuring you can retrospectively extract fields you didn't know existed. 2. Implement automated schema drift alerts that parse incoming JSON keys and trigger a Slack notification if a net new key appears in the payload. 3. Adopt schema registries for document databases that enforce explicit structural definitions before writing to the operational system. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Stores the raw variant payloads, enables delta merge schema logic, and updates the lateral flatten functions. 2. Data quality engineer. Builds JSON key drift alerts, validates the unnested data types, and ensures downstream models dynamically accept the new fields. Pro tip: the greatest advantage of JSON is flexibility, but that is also its greatest danger. Never try to parse a complex JSON payload directly during extraction. Always land the raw, unmanipulated JSON string into a variant column in your bronze layer first. If you miss a field today, you can simply write a new SQL query tomorrow to extract it from the raw history.
Scenario 64. An external vendor drops a daily CSV file into your S3 bucket. Today, they inserted a new column exactly in the middle of the file. Your pipeline relies on index position parsing, causing every subsequent column to shift one place over. Marketing data is now bleeding into finance columns. How do you resolve this?
Answer: when flat files mutate and cause data bleeding across columns, the root cause is index-based positional parsing rather than header-based semantic parsing. To isolate the root cause, untangle the corrupted data, and enforce resilient flat file ingestion, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the silver layer table to physically identify records where string values like customer names are populating numeric fields like revenue totals. 2. Download the raw CSV from the S3 landing bucket and manually inspect the header row to visually confirm the unannounced column insertion. 3. Validate downstream BI dashboards to immediately pause executive reporting before the shifted, corrupted metrics propagate to business leaders. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a positional flat file and delimiter schema incident. Phase 2. Investigation root cause. 1. Inspect the Python or copy into ingestion script to verify if it reads columns by integer index, for example, column 4 instead of strictly mapping by header name. 2. Audit the vendor AP. I contract to see if they provided advance notification of the new column that was missed by the data engineering team. 3. Review the file delimiter configuration to ensure a stray comma inside a text field didn't accidentally trigger a false column shift. By completing this investigation, you have isolated the root cause and determined whether the column shift was caused by index-based parsing, unannounced vendor changes, or stray delimiter characters. Phase 3. Targeted resolution. 1. Purge the corrupted daily partition from the target warehouse to immediately remove the bleeding data. 2. Refactor the ingestion script to map columns strictly by header name, explicitly ignoring any unrecognized columns introduced by the vendor. 3. Reprocess the corrected CSV file from the S3 bucket into the warehouse and mathematically validate that the revenue column contains only numeric values. By completing these recovery steps, the flat file ingestion logic correctly aligns the shifted columns, preventing data from bleeding into incorrect analytical fields. Phase 4. Long-term prevention. 1. Enforce strict column count validation tests that instantly fail the ingestion pipeline if the number of columns in the CSV does not match the expected baseline. 2. Transition external vendor integrations away from brittle CSV files toward strongly typed formats like Parquet or Direct REST APIs. 3. Implement automated data type assertions on the landing table that fail the load if a string attempts to write into a numeric column. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Rewrites the ingestion script to use header-based parsing, purges the corrupted data, and transitions the pipeline to strict typing. 2. Data quality engineer. Builds column count assertions, audits vendor file delivery SLAs, and configures data type anomaly alerts. Pro tip: never read a CSV file using index positions. If you tell your script to read column 5, the moment a vendor inserts a new column at position 3, your data shifts and corrupts everything downstream. Always configure your ingestion tools like Snowflake Copy, Into, or Python Pandas to map columns strictly by header name.
Scenario 65. Your streaming pipeline uses Apache Kafka and a schema registry. The upstream producer deploys an update, and suddenly, downstream consumer applications crash with deserialization errors. The Avro schema compatibility broke. How do you resolve this binary serialization failure?
Answer: when downstream consumers crash due to Avro deserialization errors, the issue stems from broken forward or backward compatibility rules in the schema registry, or consumers failing to fetch the latest schema ID. To isolate the root cause, unblock the stream, and enforce strict serialization rules, I follow a structured production response like: Phase 1. Detection and validation. 1. Check the consumer application logs to identify the exact serialization exception and isolate the specific schema ID that triggered the crash. 2. Review the Kafka broker metrics to quantify how rapidly the consumer lag is increasing due to the halted processing thread. 3. Validate which specific business domains are impacted by the stalled real-time data feed to prioritize the recovery effort. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a binary serialization and schema registry compatibility incident. Phase 2. Investigation root cause. 1. Inspect the schema registry, for example, Confluent, to compare the current schema version against the previous version, looking for deleted mandatory fields or incompatible type changes. 2. Audit the registry compatibility level configuration, for example, backward, forward, full, to determine why the registry permitted a breaking change to be registered. 3. Review the consumer application code to verify if it is tightly coupled to a static schema version, rather than dynamically resolving schema IDs from the registry. By completing this investigation, you have isolated the root cause and determined whether the crash was caused by deleted mandatory fields, misconfigured registry compatibility, or hard-coded consumer schemas. Phase 3. Targeted resolution. 1. Coordinate with the upstream producer to immediately revert their deployment and restore the previous compatible Avro schema version. 2. If the breaking change must remain, deploy an emergency update to the downstream consumer application code so it can successfully recognize and deserialize the new schema structure. 3. Restart the consumer application and monitor the offset logs to confirm the massive Kafka backlog is successfully draining without further exceptions. By completing these recovery steps, the consumer applications can successfully deserialize the stream, preventing serialization exceptions and restoring real-time consumption. Phase 4. Long-term prevention. 1. Lock the schema registry configuration globally to strictly enforce backward compatibility, programmatically rejecting any producer schema registration that breaks existing consumers. 2. Implement schema validation testing in the producer's CI/CD pipeline, ensuring a pull request fails if it attempts to delete a mandatory field. 3. Embed robust exception handling in consumer applications to route unparsable binary messages to a dead letter queue instead of crashing the main thread. By implementing these preventive controls, incompatible schemas are rejected before entering production, ensuring existing consumers continue processing messages without interruption. Role, perspective, and boundaries. 1. Data engineer investigates the schema registry versions, updates the consumer application to handle the new binary format, and drains the Kafka queue. 2. Data quality engineer defines the global backward compatibility rules, builds the CI/CD schema tests, and monitors the dead letter queue. Pro tip: if your schema registry allows a producer to delete a mandatory column, it defeats the entire purpose of having a registry. You must configure your schema registry to strictly enforce backward compatibility. This guarantees that any new schema version can successfully be read by older consumer applications without crashing.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 66. Your data lakehouse utilizes Delta Lake. An upstream vendor adds a new loyalty_tier column to their payload. Instead of accepting the data, the Delta table throws a schema mismatch error and fails the entire pipeline. The business wants the new column. How do you resolve this?
Answer: when modern lakehouse formats block data ingestion due to unapproved schema additions, it is actually a feature, not a bug, designed to prevent data swamp corruption. To isolate the root cause, safely incorporate the new column, and configure intentional schema evolution, I follow a structured production response like: Phase 1. Detection and validation. 1. Review the Databricks or Spark execution logs to isolate the exact analysis exception. A schema mismatch detected error message. 2. Query the raw bronze staging files to physically inspect the incoming payload and confirm the specific data type of the new loyalty_tier column. 3. Consult with business stakeholders to explicitly approve the inclusion of the new column into downstream silver and gold analytical models. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a lakehouse schema enforcement and right validation incident. Phase 2. Investigation root cause. 1. Inspect the Delta Lake write configuration in the pipeline code to verify that the merge schema option was intentionally set to false or omitted. 2. Audit the target table properties to ensure no strict table constraints or check constraints conflict with the incoming data type of the new column. 3. Review the downstream dependency graph to confirm that dynamically adding this column will not inadvertently break explicit select star views in the presentation layer. By completing this investigation, you have isolated the root cause and determined whether the rejection was caused by strict schema enforcement, missing merge schema flags, or conflicting table constraints. Phase 3. Targeted resolution. 1. Temporarily update the pipeline write logic to include the dot option with merge schema true flag for a single run, forcing the Delta table to safely absorb the new column. 2. Reprocess the failed ingestion batch, ensuring the loyalty_tier column is physically added to the transaction log and par-k metadata. 3. Remove the merge schema flag from the codebase immediately after the successful run to re-enable strict schema protection for future batches. By completing these recovery steps, the unapproved schema changes are successfully integrated into the table geometry, protecting the gold layer while allowing valid records to ingest cleanly. Phase 4 Long-Term Prevention 1. Implement an automated schema evolution review process where new columns are safely routed to a quarantine table until a data engineer explicitly approves a schema merge. 2. Enforce strict column aliasing and explicit schema mapping in the bronze to silver layer so that unannounced upstream columns do not bleed across boundaries. 3. Deploy metadata monitoring tools that automatically ping a Slack channel whenever a schema mismatch error is thrown, providing the exact column diff. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer modifies the Spark-write logic to enable schema merging, executes the backfill, and builds the quarantine routing logic. 2. Data quality engineer approves the semantic validity of the new column, audits the schema mismatch alerts, and ensures downstream views remain stable. Pro tip: Delta Lake schema enforcement is your best defense against data swamps. Never leave merge schema equals true permanently enabled in a production pipeline. If an upstream system goes crazy and adds 50 garbage columns, your Delta table will permanently absorb all of them. Enable it manually for one run to accept an approved column, then turn it right back off.
Scenario 67. Your organization recently implemented strict data contracts. A producer team releases a breaking change, dropping a mandatory field directly into production without bumping the contract version to V2. The pipeline crashes instantly. How do you resolve this contract violation?
Answer: when an upstream producer violates an established data contract by introducing a breaking change without versioning, the issue stems from a failure in CI/CD validation gates or weak organizational governance. To isolate the root cause, force compliance, and protect downstream consumers, I follow a structured production response like Phase 1. Detection and validation. 1. Review the central data contract registry logs to isolate the exact field deletion that triggered the contract violation exception. 2. Check the incoming payload against the registered V1 schema to mathematically verify that the mandatory field is physically missing. 3. Validate which critical downstream machine learning models and operational reports are completely halted due to the contract enforcement block. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a producer contract violation and dependency breaking incident. Phase 2. Investigation root cause. 1. Inspect the producer team's CI/CD deployment logs to determine why the automated contract validation checks were bypassed or overridden during their release. 2. Audit the data catalog to confirm if the downstream data engineering team was ever notified of the impending change via a formal deprecation warning. 3. Review the API gateway or message broker configuration to verify if strict payload validation is actively enforced at the ingestion boundary. By completing this investigation, you have isolated the root cause and determined whether the violation was caused by bypassed CI/CD tests, rogue deployments, or weak gateway enforcement. Phase 3. Targeted resolution. 1. Immediately reject the corrupted payload at the ingestion layer, routing the malformed records to a dead letter queue to prevent downstream pollution. 2. Escalate to the upstream software engineering team, requiring an immediate deployment rollback to the previous compliant payload structure. 3. If a rollback is impossible, deploy an emergency patch to the ingestion pipeline to inject a safe default value for the missing mandatory field, unblocking the data flow. By completing these recovery steps, the upstream producer has rolled back their breaking change, allowing consumers to process data safely while migrating to the new version contract. Phase 4. Long-term prevention. 1. Enforce hard gateway blocking in the production environment that instantly returns an HTTP 4.0.0 error to the producer if their payload violates the contract. 2. Mandate an explicit versioning strategy where producers must maintain V1 and release a new V2 endpoint concurrently, giving consumers 90 days to migrate safely. 3. Tie engineering KPIs to contract compliance, ensuring software teams face organizational friction if they repeatedly break downstream data platforms. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer implements hard gateway blocking, manages the dead letter queue routing, and applies emergency pipeline patches. 2. Data quality engineer defines the data contract rules, audits the producer CI/CD bypass, and enforces the 90-day version deprecation policy. Pro tip: a data contract is meaningless if it cannot physically stop a deployment. If a software team can deploy a breaking change to production without the build failing, your contract is just a wiki page. You must integrate contract validation directly into the producer's CI/CD pipeline, failing their deployment if they violate the schema.
Scenario 68. An upstream backend developer tries to merge a pull request that changes a critical user ID field from an integer to a UUID. Fortunately, your shift-left contract tests catch the violation in their CI/CD pipeline, failing the build. How do you resolve this pre-deployment conflict?
Answer: when pre-deployment CI/CD tests successfully block a breaking schema change, the system has operated exactly as designed. The challenge is no longer a data engineering incident, but an organizational negotiation on how to safely evolve the schema without halting backend product development. I follow a structured production response like: Phase 1. Detection and validation. 1. Review the failed CI/CD GitHub actions log to identify the exact line of code and specific data type change int to UUID that triggered the contract violation. 2. Cross-reference the specific user ID field against the data catalog to identify every downstream BI dashboard and ML model that currently depends on the integer format. 3. Calculate the estimated engineering effort required for the downstream teams to refactor their systems to support UUIDs. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a pre-deployment schema validation and shift-left testing incident. Phase 2. Investigation root cause. 1. Discuss the architectural motivation with the backend developer to understand why the transition to UUIDs is necessary for their application scaling. 2. Audit the semantic versioning rules defined in the data contract to verify if data type changes are explicitly classified as major breaking changes. 3. Review the local development environment tools to determine why the backend developer did not catch the violation on their local machine before opening the pull request. By completing this investigation, you have isolated the root cause and determined whether the conflict requires a contract version bump, a backward-compatible workaround, or improved local linting. Phase 3. Targeted resolution. 1. Guide the backend developer to implement an additive change rather than a destructive change, instructing them to add a new user_UUID column while temporarily preserving the legacy integer column. 2. Bump the data contract to version 2.0, officially documenting the new UUID field and setting a 60-day deprecation timeline for the legacy integer field. 3. Approve the modified, non-breaking pull request, allowing the backend deployment to proceed without crashing the data warehouse. By completing these recovery steps, the bad code is blocked from merging, entirely preventing a production pipeline failure before the deployment could execute. Phase 4. Long-term prevention. 1. Provide localized CLI tools or pre-commit hooks so backend developers can validate their schema changes against the data contract locally before ever pushing code. 2. Establish a formal data contract evolution playbook that explicitly documents the expand and contract pattern for making safe schema changes. 3. Decouple downstream consumers from raw source tables by utilizing intermediate abstract views, shielding analytical models from underlying structural shifts. By implementing these preventive controls, breaking schema changes are blocked during code review, preventing production incidents before deployment even begins. Role, perspective, and boundaries. 1. Data engineer builds the CI/CD blocking mechanisms, creates the intermediate views, and manages the migration from integer to UUID downstream. 2. Data quality engineer negotiates the contract evolution with the backend team, enforces the deprecation timeline, and manages local linting tools. Pro tip: shift-left testing is the holy grail of data engineering. The cheapest time to fix a broken data pipeline is before the code is ever deployed. If you block a breaking schema change in a GitHub pull request, you turn a stressful midnight SEV1 production outage into a calm, 5-minute conversation during regular business hours.
Scenario 69. A third-party producer changes the case of a JSON key from product ID to product_ID. Your ingestion pipeline crashes immediately because the consumer application expects exact case matching. How do you resolve and prevent this brittle parsing failure?
Answer: when downstream consumer applications crash due to trivial formatting shifts like casing or whitespace, the root cause is overly rigid parsing logic, lack of defensive consumer coding, and missing payload normalization. To isolate the root cause, restore data flow, and build resilient consumers, I follow a structured production response like: Phase 1. Detection and validation. 1. Review the consumer application exception, logs to isolate the exact key error or field not found error causing the thread to panic. 2. Compare the raw JSON payload in the message broker against the expected schema definition to visually confirm the casing shift. 3. Validate downstream applications to measure the severity of the stream interruption and estimate the growing consumer lag. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a downstream schema consumption and resilient parsing incident. Phase 2. Investigation root cause. 1. Inspect the consumer parsing logic to determine if it uses strict, case-sensitive string matching rather than generalized extraction functions. 2. Audit the upstream producer's API documentation to see if the casing shift was an intentional standardization effort or an accidental typo in their latest release. 3. Review the message broker configuration to verify if payload normalization layers like Kafka Connect single message transforms were bypassed. By completing this investigation, you have isolated the root cause and determined whether the crash was caused by strict case sensitivity, unannounced upstream standardization, or missing payload normalization. Phase 3. Targeted resolution. 1. Refactor the consumer application's parsing logic to safely convert all incoming JSON keys to lowercase before attempting explicit key lookups. 2. Restart the consumer application and monitor the logs to ensure the updated logic successfully processes the shifted product_ID payload without throwing exceptions. 3. Ensure the backlogged messages in the queue drain successfully, fully restoring the real-time analytics feed. By completing these recovery steps, the consumer application correctly parses the mutated payload using fallback defaults, preventing a system crash and ensuring uninterrupted service. Phase 4. Long-term prevention. 1. Implement defensive coding practices in all consumer applications, utilizing safe extraction methods, for example, get with key with default values instead of direct indexing. 2. Enforce payload normalization at the gateway level, standardizing all JSON keys to snake_case before the message ever reaches the downstream consumer. 3. Establish comprehensive unit tests for consumer applications that explicitly mock malformed, missing, and incorrectly cased payloads to guarantee resilient execution. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer rewrites the consumer parsing logic to be case insensitive, configures gateway payload normalization, and drains the message backlog. 2. Data quality engineer builds unit tests for malformed payloads, audits the upstream API documentation, and defines robust normalization rules. Pro tip: never trust an upstream system to maintain perfect capitalization or formatting. If your pipeline crashes because ID became ID, your pipeline is too brittle. Always apply a normalization step at the very edge of your architecture, converting all keys to lowercase snake underscore case immediately, so your downstream logic can rely on a perfectly standardized format.
Scenario 70. A massive batch file contains 1 million records. The schema validation gate detects that 50 records contain invalid data types. Do you fail the entire pipeline fail fast to protect downstream integrity, or do you quarantine the 50 records and load the remaining 999,950? How do you make this architectural decision?
Answer: when deciding how to handle partial schema mutations in flight, the root cause of indecision is a lack of defined architectural routing patterns and business criticality alignment. To isolate the payload variants, apply the correct fault tolerance strategy, and implement safe routing, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a payload profiling script to identify exactly which 50 rows violated the schema and specifically which columns contain the invalid data types. 2. Measure the error ratio. 50 out of 1 million is 0.005% to mathematically determine if the failure is an isolated edge case or a systemic file corruption. 3. Consult the data product SLA to validate whether the downstream business users prioritize absolute completeness or on-time partial delivery. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a schema routing and dead letter queue triage incident. Phase 2. Investigation root cause. 1. Inspect the 50 corrupted rows to determine if they contain highly critical data like end-of-quarter financial adjustments that cannot legally be excluded from reporting. 2. Audit the pipeline configuration to see if it utilizes an all-or-nothing transaction block that physically prevents partial loading. 3. Review the downstream systems to verify if they are capable of handling late-arriving corrections if the 50 rows are reprocessed and inserted tomorrow. By completing this investigation, you have isolated the root cause and determined whether the schema variance allows for safe partial ingestion or mandates a strict fail-fast halt. Phase 3. Targeted resolution. 1. Because the error rate is microscopically low 0.005% and business requires timely data, implement the quarantine routing strategy. 2. Dynamically route the 999,950 valid records into the target warehouse table, allowing the morning executive dashboards to refresh on time. 3. Shunt the 50 malformed records directly into a dead letter queue table and trigger a localized alert for a data engineer to manually inspect and correct them. By completing these recovery steps, invalid records are safely routed to a quarantine queue, ensuring the main pipeline continues processing compliant data without silent drops. Phase 4. Long-term prevention. 1. Embed dynamic threshold logic in the pipeline orchestrator. For example, if errors less than 1%, quarantine and proceed. If errors greater than 1%, fail fast and halt the pipeline. 2. Build an automated replay mechanism that allows data engineers to easily push corrected records from the dead letter queue back into the main pipeline. 3. Establish clear organizational guidelines, documenting which highly regulated financial pipelines must strictly use fail-fast versus which analytical pipelines can tolerate quarantine. By implementing these preventive controls, schema violations are automatically routed according to business criticality, balancing data integrity with operational continuity. Role, perspective, and boundaries. 1. Data engineer implements the dead letter queue routing logic, builds the dynamic threshold circuit breakers, and manages the replay scripts. 2. Data quality engineer defines the acceptable error threshold percentages, audits the quarantine records, and aligns routing strategies with business SLAs. Pro tip: fail fast is safe, but it causes alert fatigue. If you fail a 1 million row pipeline at 3 a.m. because a single user typed a letter into a phone number field, your engineers will burn out. Use the quarantine pattern dead letter queues for edge cases to keep the business running, and only fail fast when the corruption is systemic.
Category 7, Conclusion and Key Takeaway. Schema Evolution and Data Contracts.
In Category 7, we established that hard-coded pipelines are extremely fragile in the face of upstream software deployments. We mastered systematic investigation techniques across 10 distinct structural failure modes, ranging from unannounced column renames and silent data type mutations to nested JSON array injections and broken AV row registries. Key takeaway: schema evolution is not about accepting every change. It is about enabling controlled change without breaking downstream consumers. In production platforms, this is achieved through 10 core capabilities: schema drift detection, safe type evolution, schema on read handling, resilient file parsing, compatibility enforcement, controlled schema evolution, contract governance, shift left validation, defensive consumer design, and intelligent quarantine routing.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip: whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition. Category 7 Schema Evolution and Data Contracts to Category 8 Validation and Data Integrity.
We are now pivoting from structural integrity to logical reality, moving directly into validation and data integrity. A pipeline can have the perfect schema, strict data contracts, and execute on time. But if the data inside the columns represents impossible real-world states like negative product prices or humans born in the future, the data is entirely invalid. Mastering this shift requires moving beyond checking data types and instead writing deterministic assertions that enforce the physical laws of your business.
Category 8 Overview. Enforcing Reality.
Top-tier tech interviewers evaluate your ability to detect and quarantine logically corrupted data before it poisons downstream analytics. In Category 8, we will explore 10 high-frequency production scenarios covering temporal paradoxes, regex formatting failures, mathematical bound violations, and referential sequence breaks. Strong candidates must demonstrate how to combine statistical profiling, domain-specific regex validation, temporal bounding rules, and quarantine routing to guarantee that every row of data is physically possible and business compliant.
Category 8 Validation and Data Integrity Scenarios.
Here are the 10 production validation scenarios we are going to solve in this category. Scenario 71. Birth dates occur in the future. Scenario 72. Age exceeds valid business limits. Scenario 73. Mandatory fields suddenly contain null values. Scenario 74. Email addresses fail validation. Scenario 75. Phone numbers violate country standards. Scenario 76. Zip codes contain invalid characters. Scenario 77. Product prices become negative. Scenario 78. Order dates precede customer registration. Scenario 79. Primary keys become null. Scenario 80. Foreign key integrity violations appear after migration. Let's deep dive into Scenario 71.
Scenario 71. A daily profiling alert triggers, indicating that 5,000 new users generated today have birth dates listed in the year 2050 or later. The pipeline processed the dates without throwing any schema errors because they are valid date strings. How do you resolve this temporal validation failure?
Answer: when valid data types contain logically impossible future timestamps, the root cause is typically epoch math calculation bugs, client-side time zone bugs, or intentional placeholder values set by upstream systems. To isolate the root cause, correct the timestamps, and enforce temporal bounds, I follow a structured production response like Phase 1. Detection and validation. 1. Query the target user dimension table to isolate the exact 5,000 records, analyzing if they share the exact same future date, for example, 31st December 2099, or a randomized spread of future dates. 2. Check the raw bronze layer payloads to verify if the future dates originated directly from the client application or were generated during pipeline extraction. 3. Validate downstream marketing segmentation models to ensure upcoming campaigns are not actively targeting these corrupted profiles. By completing these validation steps, you have verified the anomaly. measured its business impact, and classified it as a chronological boundary and logical validation incident. Phase 2. Investigation root cause. 1. Inspect the transformation code to check for epoch calculation errors, such as multiplying a millisecond Unix timestamp by 1000 instead of dividing it. 2. Audit the upstream source database to see if 2099 or 9999 is intentionally used as a default placeholder for users who decline to provide a birth date. 3. Review the mobile application or front-end form logic to see if a UI calendar bug allowed users to scroll into future years without client-side validation. By completing this investigation, you have isolated the root cause and determined whether the future dates were caused by epoch math errors, default placeholders, or missing UI constraints. Phase 3. Targeted resolution. 1. If caused by a math error, refactor the epoch conversion logic and recalculate the 5,000 dates to their true historical values in the silver layer. 2. If caused by intentional placeholders, implement a transformation step that converts sentinel future dates into explicit null values, making them analytically safe. 3. Reprocess the affected partitions and mathematically verify that 0 active records possess a birth date greater than current date. By completing these recovery steps, the logically impossible timestamps have been corrected or nullified, restoring the accuracy of demographic segmentation and downstream reporting. Phase 4. Long-term prevention. 1. Enforce logical boundary testing in DBT using DBT expectations to instantly fail the pipeline if a birth date column contains any value greater than the current system timestamp. 2. Establish a data contract with the front-end engineering team to enforce strict calendar input limits directly on the client-side UI. 3. Standardize missing data representation by banning sentinel dates like 9999 in analytical models, strictly utilizing native database null. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer fixes the epoch conversion math, routes sentinel dates to null, and executes the historical backfill. 2. Data quality engineer builds the current underscore date boundary assertions, monitors chronological edge cases, and audits demographic model health. Pro tip: the database does not care if a human is born in the year 2500. A date column only cares if the string format is valid. You cannot rely on schema types to catch logical impossibilities. You must explicitly write logical boundary assertions. For example, birth underscore date is less than or equal to today to protect your analytical tables from physical impossibilities.
Scenario 72. You run a quality check on the customer dimension table and discover thousands of users listed as being exactly 54 years old or having a birth year of 1970. This massive concentration skews the average customer age dramatically. How do you resolve this demographic anomaly?
Answer: when demographic distributions show a massive, unnatural spike at a specific historical age like 1970 or 1900, the root cause is almost always default Unix epoch parsing failures or legacy system defaults masking missing data. To isolate the root cause, normalize the demographic distribution, and enforce realistic bounds, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a frequency distribution query group by birth underscore year on the customer table to mathematically quantify the exact volume of users clustered in the 1970 bucket. 2. Correlate these specific 1970 records with other profile completeness metrics to see if they consistently lack other optional attributes like phone numbers or addresses. 3. Check downstream machine learning features to assess how severely this artificial demographic spike is skewing predictive modeling distributions. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a business logic constraint and out-of-bounds validation incident. Phase 2. Investigation root cause. 1. Inspect the raw JSON payloads to check if the upstream application is sending a 0 or blank string when a user skips the birth date field during signup. 2. Audit the ingestion pipeline's date parsing logic to verify if it automatically defaults a 0 integer into the Unix epoch start date January 1st, 1970. 3. Review legacy database migration scripts to see if an old system used 1st January 1900 as a mandatory not null placeholder for unknown dates. By completing this investigation, you have isolated the root cause and determined whether the age skew was caused by Unix epoch default parsing, legacy not null placeholders, or raw payload 0 values. Phase 3. Targeted resolution. 1. Refactor the data parsing logic to explicitly intercept 0 or blank values in the birth date field and cleanly cast them to null before timestamp conversion. 2. Run an update script on the affected silver and gold customer dimensions to nullify the artificial 1st January 1970 entries, removing them from average age calculations. 3. Verify the newly calculated average customer age and confirm the distribution curve resembles a natural demographic spread. By completing these recovery steps, the artificial demographic clustering has been eliminated, restoring accurate statistical distributions for downstream machine learning and analytics. Phase 4. Long-term prevention. 1. Deploy statistical distribution monitors that track the standard deviation and variance of numerical columns, alerting on massive unnatural clustering. 2. Implement logical guardrails in the transformation layer that automatically quarantine or nullify any birth date that results in an age greater than 110 years or exactly matching epoch boundaries. 3. Collaborate with front-end teams to ensure optional date fields transmit true null payloads rather than injecting 0 integers. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Updates the parsing logic to handle 0 values safely, removes the Unix epoch fallbacks, and recalculates the dimension table. 2. Data quality engineer. Builds frequency distribution profiling tests, defines valid age range guardrails, and validates the normalized demographic curve. Pro tip. The Unix epoch January 1, 1970 is the most common hidden ghost in demographic data. If an upstream system sends a 0 because a field was left blank, most date parsing functions will blindly convert that 0 into 1970, instantly making the user 50+ years old. Always explicitly cast 0 integers to null before parsing dates.
Scenario 73. The gold layer fact table usually boasts a 100% completeness rate for the transaction_currency field. Today, data quality alerts fire because 15% of the new rows contain null in this explicitly mandatory field. How do you trace and resolve this constraint violation?
Answer. When a historically perfectly populated mandatory field suddenly spikes with null values, the root cause is either an upstream producer omitting the field entirely, or a downstream safe casting function like try_cast swallowing malformed strings and converting them to null. To isolate the root cause, repair the mandatory constraint, and route malformed data safely, I follow a structured production response like Phase 1. Detection and validation. 1. Query the silver layer table to measure the exact volume and percentage of null currency values injected during the most recent pipeline execution. 2. Isolate the corrupted rows and check if they share a specific product category, geographic origin, or payment gateway source. 3. Cross-reference the raw bronze landing files to visually determine if the currency field is physically missing from the JSON payload or if it contains data. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a constraint enforcement and mandatory attribute validation incident. Phase 2. Investigation root cause. 1. If the field is physically present in the bronze layer, inspect the text value to see if a new, unrecognized currency code, for example, crypto was introduced. 2. Audit the bronze to silver SQL transformation to check if a strict try_cast or case statement evaluated the unrecognized string to null to avoid crashing the pipeline. 3. If the field is completely missing from bronze, review the upstream application commit history to see if an API payload minimization effort accidentally dropped the attribute. By completing this investigation, you have isolated the root cause and determined whether the null spike was caused by dropped upstream payload fields, unmapped reference codes, or silent safe casting failures. Phase 3. Targeted resolution. 1. If caused by a new unmapped value, update the reference mapping or cast logic to officially recognize and process the new currency string. 2. If the field was truly missing from the source, work with the producer to re-extract the affected 15% of transactions with the full payload intact. 3. Execute a targeted backfill on the affected partitions to populate the restored currency values, bringing the column back to 100% completeness. By completing these recovery steps, the mandatory attributes have been successfully repopulated, ensuring downstream financial aggregations do not silently drop unclassified revenue. Phase 4. Long-term prevention. 1. Enforce strict not-null physical constraints on the target database table to completely block the insertion of corrupted mandatory fields. 2. Implement the right audit publish pattern so that if the not-null threshold drops below 100% during the staging audit, the data is never published to gold. 3. Route records that fail the try_cast conversion directly to a dead letter queue rather than silently converting the failed column to null. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer refactors the try_cast logic to route failures to a dead letter queue, implements not null constraints, and executes the partition backfill. 2. Data quality engineer configures the right audit publish completeness gates and audits the raw payloads for upstream API omissions. Pro tip: safe casting functions like try_cast or safe_cast are dangerous double-edged swords. They prevent your pipeline from crashing when it hits a bad string, but they do so by silently turning the bad data into a null. If you use safe casting on a mandatory column, you must pair it with a not null threshold alert to catch the silent data loss.
Scenario 74. The marketing team's email automation tool rejects 10,000 new leads provided by the data warehouse. You check the data and see that the emails look visually normal, but the downstream tool is failing them for formatting violations. How do you resolve this string integrity failure?
Answer: when visually normal strings fail downstream formatting validation, the root cause is almost always hidden whitespaces, invisible control characters, or overly rigid regex patterns failing on new top-level domains. To isolate the root cause, sanitize the strings, and enforce format integrity, I follow a structured production response like Phase 1. Detection and validation. 1. Export a sample of the 10,000 rejected email strings from the warehouse and run a local regex validation script to explicitly reproduce the downstream failure. 2. Inspect the raw string byte encoding to check for invisible characters like carriage returns, trailing spaces, or non-breaking spaces. 3. Check the domain suffixes of the rejected emails to verify if they use newer, valid top-level domains like .io or .tech that legacy systems might reject. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a string pattern matching and format integrity incident. Phase 2. Investigation root cause. 1. Audit the upstream data collection forms to see if a recent UI change allowed users to copy-paste emails, carrying over hidden formatting characters. 2. Review the warehouse transformation code to determine if basic string sanitation functions like trim or lower were omitted from the silver layer. 3. Inspect the downstream marketing tool's API documentation to confirm its exact regex requirements and character limits for valid email formats. By completing this investigation, you have isolated the root cause and determined whether the validation failure was caused by hidden trailing whitespaces, missing string sanitation, or legacy downstream regex rules. Phase 3. Targeted resolution. 1. Refactor the data pipeline to apply explicit string cleaning, applying lower, trim, and regex underscore replace to strip invisible control characters. 2. Execute a targeted update statement on the affected customer records in the gold layer to overwrite the corrupted strings with the sanitized versions. 3. Resync the cleaned 10,000 leads to the marketing automation tool, API, verifying that the payloads are accepted with HTTP 200 success codes. By completing these recovery steps, the string formatting has been successfully sanitized, allowing the marketing tools to ingest the leads and resume outbound campaigns. Phase 4. Long-term prevention. 1. Implement an enterprise standard formatting macro in DBT that automatically applies trim, lowercase, and whitespace stripping to every email field across all models. 2. Deploy regex validation tests on the staging layer that quarantine any email lacking an @ symbol or a valid domain suffix into a manual review table. 3. Enforce front-end validation at the point of entry so the operational database natively rejects malformed strings before they reach the warehouse. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Implements the string sanitization macros in the transformation code, executes the historical cleanup, and manages the API resync. 2. Data quality engineer. Defines the regex validation rules, audits the quarantine records, and coordinates input validation standards with front-end teams. Pro tip: never trust free text user input. If a human can type into a box, they will accidentally paste trailing spaces, invisible tabs, and carriage returns. You must treat all raw string inputs as inherently dirty. Always pass critical text fields like emails through a standard cleansing macro that applies trim and lower before saving it to a master dimension.
Scenario 75. Your company expands internationally, but the operational SMS notification system starts failing for thousands of new European customers. You investigate the warehouse and discover the international phone numbers are missing country codes and leading zeros. How do you resolve this formatting failure?
Answer: when international phone numbers lose leading zeros or country codes, the root cause is almost universally an integer casting error during ingestion or a lack of strict E.164 string formatting standards. To isolate the root cause, reconstruct the phone numbers, and enforce global standards, I follow a structured production response like: Phase 1. Detection and validation. 1. Query the customer contact table to isolate phone records that lack the plus prefix or fall below the standard digit length for international formatting. 2. Group the malformed records by region or country code to verify if the truncation specifically impacts regions that utilize leading zeros like the UK. 3. Validate the SMS delivery logs to quantify the exact number of dropped customer notification messages resulting from the malformed numbers. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an internationalization formatting and reference standard integrity incident. Phase 2. Investigation root cause. 1. Inspect the bronze layer ingestion schema to determine if the pipeline used schema inference, which aggressively casts the numeric phone string into a big int. 2. Audit the upstream user registration form to check if international users are allowed to input free text numbers without selecting a standardized country code dropdown. 3. Review the database column DDL to confirm the target field is defined as a varchar and not a numeric data type. By completing this investigation, you have isolated the root cause and determined whether the formatting loss was caused by aggressive integer casting, missing country code prefixes, or free text input forms. Phase 3. Targeted resolution. 1. Update the pipeline ingestion schema to strictly define the phone number field as a string, preventing the engine from stripping leading zeros. 2. Reconstruct the corrupted numbers using a SQL case statement that prepends the correct regional country code based on the customer's linked geographic region. 3. Reprocess the corrected string values into the target dimension table and execute a test AP. I call to the SMS provider to confirm successful parsing. By completing these recovery steps, the international phone strings have been successfully reconstructed, allowing the downstream notification systems to resume global delivery. Phase 4. Long-term prevention. 1. Establish the global E.164 format, for example, +14155552671 as the absolute enterprise standard for all phone numbers stored in the data platform. 2. Deploy automated regex validation checks in the pipeline that quarantine any phone number string that lacks a plus prefix or contains alphabetic characters. 3. Force upstream software teams to implement strict phone number parsing libraries like Google libphone number on the client side before saving to the database. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Disables schema inference for phone columns, applies the E.164 reconstruction logic, and ensures target tables use varchar. 2. Data quality engineer. Defines the E.164 regex compliance tests, audits the quarantined phone numbers, and coordinates validation with front-end teams. Pro tip: never store a phone number as an integer. Integers do not retain leading zeros, and they cannot store the plus symbol required for international dialing. If you ingest a UK phone number starting with 07 as an integer, the 0 is deleted forever. Always store phone numbers as strings adhering strictly to the E.164 international format.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 76. An established pipeline has processed US zip codes flawlessly for years. The company launches in Canada and the UK, and suddenly the pipeline halts, rejecting thousands of records because the new postal codes contain alphabetic characters. How do you resolve this validation constraint failure?
Answer: when geographic data pipelines crash during international expansion, the root cause is almost exclusively rigid, US-centric integer casting or hyper-specific regex rules that fail on alphanumeric strings. To isolate the root cause, widen the geographical schema, and handle global formats natively, I follow a structured production response like: Phase 1. Detection and validation. 1. Review the orchestration logs to isolate the exact step where the pipeline failed, capturing the specific type conversion or regex mismatch exception. 2. Query the raw bronze layer payloads to visually inspect the rejected postal codes, for example, SW1A1AA for the UK, to confirm they are valid international formats. 3. Assess downstream analytical impacts to determine if geographic revenue reporting is currently blocked due to the halted ingestion. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an alphanumeric schema validation and geographic data integrity incident. Phase 2. Investigation root cause. 1. Inspect the target database DDL to see if the postal code column was historically defined as an int or a rigid var char with 5 constraint that clips international codes. 2. Audit the staging layer data quality tests like DBT expectations to see if a strict regex pattern 0 to $95 was explicitly blocking non-numeric characters. 3. Review the transformation logic to check if trailing spaces or hyphens from international systems were breaking downstream geographic joins. By completing this investigation, you have isolated the root cause and determined whether the failure was caused by rigid numeric data types, strict US-centric regex filters, or insufficient column length constraints. Phase 3. Targeted resolution. 1. Execute an alter table statement to safely widen the column to a flexible var char with 20 to accommodate spacing and alphabetic characters. 2. Update the DBT data quality rules to apply dynamic regex validation based explicitly on the linked country code column rather than a global rule. 3. Reprocess the halted pipeline batch, ensuring the Canadian and UK postal codes are successfully loaded into the target geographic dimension. By completing these recovery steps, the rigid geographical constraints have been widened, allowing international alphanumeric formats to successfully load without pipeline failure. Phase 4. Long-term prevention. 1. Transition all geographic validation rules from static regex patterns to dynamic API lookups using established geographic standard libraries. 2. Establish schema design policies that mandate strings for all geographic identifiers, explicitly banning integers for zip codes, phone numbers, and IP addresses. 3. Create a dedicated geo_unmapped bucket for unrecognized postal formats, allowing the pipeline to proceed while flagging edge cases for manual review. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer. Alters the table DDL to varchar, removes the integer casting, and builds the routing logic for unrecognized formats. 2. Data quality engineer. Refactors the DBT validation rules to be country-specific, monitors geographic data completion, and audits the unmapped bucket. Pro tip: the 5-digit integer zip code is a classic trap in data modeling. Only the US uses numeric-only, 5-digit postal codes. The moment your company sells a product in Canada or the UK, an integer column will instantly crash your database. Always model postal codes as strings varchar from day one to future-proof your global architecture.
Scenario 77. The monthly revenue roll-up job succeeds, but a downstream data quality alert fires on the gold sales table. 200 orders have a final underscore price less than $0. The business logic generated a physically impossible negative price. How do you resolve this mathematical constraint failure?
Answer: when calculated financial metrics drop below zero into logically impossible negative territory, the root cause is typically aggressive discount stacking, unhandled refund allocations, or integer underflow errors. To isolate the root cause, cap the financial models, and enforce absolute value boundaries, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a bounding query. For example, select star where final underscore price less than 0 to instantly isolate the 200 corrupted transaction rows in the gold layer. 2. Cross-reference the specific negative transactions against upstream promotional campaigns to see if they all utilize the same heavy discount code. 3. Check the source operational database to determine if the negative value actually exists in the transactional system or was solely generated during pipeline aggregation. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a mathematical boundary and absolute value integrity incident. Phase 2. Investigation root cause. 1. Inspect the silver layer transformation logic to verify if flat discount amounts, for example, -$50, were applied to items costing less than the discount itself. 2. Audit the order cancellation logic to see if a full refund was applied to an order that had already been partially refunded previously, resulting in double deduction. 3. Review the numerical data types in the pipeline to check if a signed integer underflowed, causing a massive negative loop. By completing this investigation, you have isolated the root cause and determined whether the negative bounds were breached by unconstrained flat discounts, double refunds, or mathematical underflow. Phase 3. Targeted resolution. 1. Refactor the pricing transformation logic to use a greatest with 0 calculated underscore price function, establishing an absolute mathematical floor of $0. 2. Reverse the incorrect double refund or discount stacking on the affected 200 rows by reprocessing them through the updated bounding logic. 3. Reconcile the corrected totals with the finance team to ensure the previously negative amounts are correctly zeroed out in the general ledger. By completing these recovery steps, the logically impossible negative prices have been corrected to an absolute zero floor, ensuring financial aggregates remain accurate and positive. Phase 4. Long-term prevention. 1. Implement strict mathematical boundary expectations in DBT, for example. Expect column values to be between 0 and max that instantly halt publishing if a final price drops below 0. 2. Establish data contracts with the promotional systems team requiring business logic that prevents discount codes from exceeding the base cart value. 3. Utilize database check constraints at the physical table level to strictly prohibit the insertion of negative values into gross revenue columns. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer implements the greatest bounding function, adds physical check constraints to the DDL, and recalculates the corrupted partitions. 2. Data quality engineer configures the DBT boundary tests, isolates the discount code patterns, and verifies the general ledger reconciliation. Pro tip: never assume your source system will do the math correctly. If marketing issues a $50 off coupon and a user buys a $10 item, your pipeline will calculate a $40 sale unless you explicitly tell it not to. Always wrap your final price transformations in a greatest with zero price boundary to enforce a hard physical floor on your financial metrics.
Scenario 78. A data analyst discovers a temporal paradox in the data warehouse. Hundreds of customers have valid order transactions dated days or weeks times before their official account registration date. How do you resolve this chronological integrity failure?
Answer: when dependent events happen chronologically before their prerequisite parent events, the root cause is almost always a synchronous guest checkout merging, late arriving historical migrations, or disconnected microservice clocks. To isolate the root cause, reconcile the chronological timeline, and map logical sequences, I follow a structured production response like Phase 1. Detection and validation. 1. Execute a chronological validation query joining the orders and customers tables, isolating records where order_date less than customer_registration_date. 2. Review the payment gateways to physically verify that the order was placed on the older timestamp and that it is not an artifact of a delayed ingestion job. 3. Analyze the 500 affected user profiles to identify shared behavioral patterns, such as utilizing guest checkout or migrating from a legacy platform. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a temporal sequence and relational chronology incident. Phase 2. Investigation root cause. 1. Inspect the e-commerce platform's business logic to verify if users are allowed to make purchases as guests and subsequently create an account weeks later. 2. Audit the identity resolution pipeline to check if guest orders are being retroactively merged into the newly created account without adjusting the original order timestamps. 3. Review the application microservices to see if time zone drifts between the account service and the order service generated artificial chronological inversions. By completing this investigation, you have isolated the root cause and determined whether the temporal paradox was caused by guest checkout merges, retroactive identity linking, or microservice clock drift. Phase 3. Targeted resolution. 1. Update the semantic layer models to explicitly handle the guest-to-registered conversion pathway, accepting order dates preceding registration dates as logically valid for this specific scenario. 2. If the cause was time zone drift, align the timestamp cast logic across both domains to UTC to physically correct the inverted time sequence. 3. Add an explicit is_guest_purchase Boolean flag to the fact table to provide analytical context for why the chronological inversion exists. By completing these recovery steps, the temporal sequence has been contextually resolved, preventing data quality tools from flagging valid guest conversions as corrupted data. Phase 4, long-term prevention. 1. Implement dynamic chronological assertions in DBT that only flag order_date less than registration_date if the transaction is explicitly marked as a registered user purchase. 2. Enforce end-to-end identity tracking, for example, persistent device IDs or cookies that smoothly link guest activity to the eventual account creation timestamp. 3. Centralize time handling by ensuring all upstream microservices sync to the same NTP network time protocol server to eliminate clock drift. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer fixes the UTC time zone alignment, adds the guest purchase indicator flags, and maps the identity resolution timeline. 2. Data quality engineer refactors the chronological DBT tests to tolerate guest merges while strictly failing actual microservice time drifts. Pro tip: data quality rules must reflect business reality, not just mathematical purity. A transaction occurring before an account registration looks like a data corruption bug, but in e-commerce, it is a highly common guest checkout feature. Do not delete the data, enrich it. Add a Boolean flag explaining the state so analysts understand the timeline.
Scenario 79. A highly critical dimensional table fails its morning data quality checks because 5% of the newly inserted rows have a completely null primary key. The pipeline loaded the data without crashing, but downstream joins are now failing massively. How do you resolve this?
Answer: when primary keys silently evaluate to null during ingestion, the root cause is almost always exploded JSON arrays lacking parent IDs, upstream CDC drops, or unseeded surrogate hash functions. To isolate the root cause, restore entity identification, and enforce primary key integrity, I follow a structured production response like Phase 1. Detection and validation. 1. Query the target dimension table to explicitly count the number of rows where the primary key column evaluates to is null. 2. Inspect the remaining secondary attributes of the corrupted rows to determine if they contain valid business data or if the entire row is completely empty. 3. Validate downstream analytical joins to measure how many dependent fact records are currently orphaned due to the missing dimension anchors. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as an entity identification and primary key integrity incident. Phase 2. Investigation root cause. 1. Inspect the JSON unnesting transformation logic, for example. Lateral flatten to see if expanding nested child arrays cause the query to lose the parent ID mapping. 2. Audit the surrogate key generation macro like dbt_utils .generate_surrogate_key to determine if it concatenated multiple null source fields, yielding a null hash. 3. Review the upstream extraction API to check if a specific edge case in the operational system is allowing records to be generated without unique identifiers. By completing this investigation, you have isolated the root cause and determined whether the null keys were caused by unnested array explosion, unseeded surrogate hashes, or upstream API omissions. Phase 3. Targeted resolution. 1. Refactor the unnesting transformation SQL to explicitly carry the parent primary key down to the child array rows during flattening. 2. Update surrogate key hashing functions to handle null inputs gracefully by using a co-a-less fallback, for example, hashing a default string to guarantee a deterministic output. 3. Delete the corrupted null key rows and reprocess the batch, ensuring every row is stamped with a mathematically valid identifier. By completing these recovery steps, valid primary keys have been safely regenerated for all records, restoring downstream referential joins and preventing orphaned facts. Phase 4. Long-term prevention. 1. Enforce physical not null and unique constraints directly on the data warehouse table schema, making it impossible for the database to ever accept a missing primary key. 2. Implement the right audit publish pattern to quarantine any staging dataset that fails a count with primary underscore key is equal to the count function validation test. 3. Establish automated monitoring on the surrogate key macros to alert engineers if the entropy or distribution of generated hashes drops unexpectedly. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer fixes the lateral flatten SQL logic, updates the surrogate hashing coalesce conditions, and enforces table-level not null constraints. 2. Data quality engineer configures the primary key completeness assertions in the staging audit layer and monitors downstream join success rates. Pro tip: a table without a primary key is not a table. It is just a pile of data. Never rely purely on pipeline transformation logic to ensure primary keys are populated. You must apply physical not null and unique constraints at the database level. If a query tries to insert a null primary key, the database itself should forcefully reject the transaction.
Scenario 80. You are migrating analytics off a legacy application onto a new microservices platform. Suddenly, historical fact tables throw millions of foreign key FK violations. Orders point to customer IDs that simply do not exist in the new platform's dimension table. How do you resolve this?
Answer: when an application migration triggers massive historical foreign key violations, the root cause is almost always the difference between legacy soft deletes and new platform hard deletes, bypassing cascade logic. To isolate the root cause, rescue the orphan facts, and restore referential synchronization, I follow a structured production response like: Phase 1. Detection and validation. 1. Execute a left anti-join to isolate the exact list of customer IDs present in the historical orders fact table, but missing from the newly migrated customers table. 2. Check the legacy application's database to visually verify if these missing customers physically exist there, or if they were flagged with an is underscore deleted equals true boolean. 3. Measure the total revenue associated with the orphaned historical orders to calculate the analytical impact of the missing dimension records. By completing these validation steps, you have verified the anomaly, measured its business impact, and classified it as a referential synchronization and structural integrity incident. Phase 2. Investigation root cause. 1. Inspect the migration extraction scripts to determine if the team applied an intentional where clause filtering out deleted users from the initial payload. 2. Audit the new microservice architecture to see if it utilizes hard deletes, physically erasing records under GDPR rules, erasing parents without cascading to the warehouse facts. 3. Review the warehouse ingestion framework to see if it expects append-only history, but was fed a point-in-time snapshot missing historical context. By completing this investigation, you have isolated the root cause and determined whether the orphan facts were caused by legacy soft delete filtering, new platform hard deletes, or snapshot extraction mismatches. Phase 3. Targeted resolution. 1. Extract the missing deleted customer profiles from the legacy system and inject them into the modern warehouse dimension table, flagging them explicitly as archived. 2. If the legacy profiles are permanently lost, generate dummy unknown customer records matching the orphaned IDs to instantly repair the broken SQL joins. 3. Re-execute the referential integrity tests to mathematically prove that 100% of the historical fact rows now successfully map to a dimension anchor. By completing these recovery steps, the orphaned historical facts have been safely re-anchored to the dimension table, restoring referential integrity and historical revenue reporting. Phase 4. Long-term prevention. 1. Enforce slowly changing dimensions SCD Type 2 in the warehouse so that even if a source application hard deletes a record, the warehouse retains it historically. 2. Implement referential integrity unit tests in the migration CI/CD pipeline, strictly blocking any snapshot load that orphans existing downstream facts. 3. Establish a data contract with the new microservices team, dictating that soft deletes tombstoning must be used instead of hard deletes to preserve analytical history. By implementing these preventive controls, this incident evolves from a one-time production fix into a continuously monitored quality safeguard, significantly reducing the likelihood of recurrence. Role, perspective, and boundaries. 1. Data engineer extracts the archived records from the legacy system, implements the SCD Type 2 logic, and generates the dummy anchor records. 2. Data quality engineer defines the referential mapping tests, validates the historical revenue totals, and audits the new microservice deletion patterns. Pro tip: software engineers love hard deletes to keep operational databases clean. Data engineers hate hard deletes because they destroy historical reporting. If an operational system hard deletes a customer today, all the orders that customer placed last year instantly become orphaned. You must design your warehouse to capture and retain history independently of the operational source state.
Category 8 Conclusion and Key Takeaway: Validation and Data Integrity.
In Category 8, we establish that a pipeline can execute perfectly and possess a flawless schema, yet still deliver mathematically impossible or logically corrupted data. We mastered systematic investigation techniques across 10 integrity failure modes, ranging from chronological paradoxes and age anomalies to referential integrity breaks and alphanumeric geographic bounds. Key takeaway: data integrity is the discipline of ensuring that data is not only structurally valid, but also logically correct and business compliant. In production platforms, integrity is enforced through 10 complementary capabilities: temporal validation, statistical profiling, mandatory attribute enforcement, pattern validation, reference standard validation, geographic validation, mathematical boundary checks, business rule validation, entity integrity, and referential integrity. Mastering these capabilities ensures that downstream analytics are built on data that accurately reflects real-world business behavior.
Part 1 Conclusion and Key Takeaway: Mastering the Core Pipeline.
You have now completed Part 1, mastering the first 80 scenarios across completeness, idempotency, accuracy, semantic quality, system consistency, freshness, schema evolution, and data integrity. These 8 categories represent the absolute bread and butter of modern data engineering. Key takeaway: modern data engineering is not just about building pipelines. It is about building trusted, resilient, and observable data platforms. The best engineers do not simply move data from one system to another. They ensure that every dataset is complete, accurate, consistent, fresh, structurally resilient, and business trustworthy before it reaches analysts, dashboards, machine learning models, or executive decision makers.
Transition from Part 1, the core pipeline and business reality, to Part 2, the modern stack, Gen AI, and staff-level boss fights.
This completes Part 1 of our Data Quality Production Scenario series. In Part 2, we will move beyond foundational data quality disciplines into advanced production engineering topics, covering modern challenges such as observability, governance, security, privacy, AI and ML data quality, lakehouse architectures, streaming resilience, enterprise-scale reconciliation, and other senior to principal-level production scenarios that power today's data platforms.
Part 2, the modern stack, Gen AI, and staff-level boss fights category overview.
These first 80 scenarios will easily get you past standard technical rounds, but if you want a senior, lead, or staff-level offer, you must master the modern edge. In Part 2, we tackle the hardest 75 scenarios covering Category 9, Lakehouse and Storage Quality 81 to 90, Category 10, Data Observability and Monitoring 91 to 100, Category 11, Privacy, Security and Governance 101 to 108, Category 12, AI and ML and Gen AI Data Quality 109 to 120, Category 13, APIs, Streaming and External Systems 121 to 130, Category 14, CICD. Deployment and Change Management 131 to 140. Category 15. Production Incidents, RCA and Staff Level Architecture 141 to 155. Next step, please check Part 2 link in the description below to master the remaining 75 scenarios in this series.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.